In this section of the course, we'll see how we can use polymorphism and inheritance to provide us with the power to create reusable and flexible programs. We'll start by understanding the different types of polymorphism available in C++, and then we'll focus on dynamic polymorphism in this section. Then we'll learn how to use base class pointers to really take our class hierarchies to a new level and see how we can now think more abstractly and not have to worry about details. Throughout this section of the course, we'll see examples of static and dynamic binding of function calls, and we'll understand the pros and cons of each. Then we'll use virtual functions to achieve polymorphic functions, that is, functions that are bound at runtime. We'll see how important it is to have virtual destructors. And use the C++11 override and final specifiers. Then we'll see how we can use base class references to also achieve dynamic polymorphism. Finally, we'll learn what pure virtual functions and abstract classes are and why we would want to use them as is and in interfaces. There's a lot to cover, but I think you'll find this section pretty easy to grasp since you have a pretty solid foundation already. So let's get started with polymorphism. In this video, we'll learn what polymorphism is and how it can help us better develop our object-oriented applications. Polymorphism is a fundamental part of object-oriented programming. There are several types of polymorphism in C++, and we've already learned about two of them, when we overloaded functions and when we overloaded operators. These are considered forms of compile-time polymorphism. You might see the terms compile-time, early binding, and static binding. These terms all mean the same thing. They simply mean before the program executes. In other words, something the compiler takes care of way before the program runs. Runtime, late binding, and dynamic binding all refer to the association of what the programmer wants to do with how to do it, but at runtime, as the program executes. We'll see some examples in a few slides that will make this very clear. Polymorphism allows us to think more abstractly when we write programs. We can think deposit or print or draw instead of thinking in specific versions of deposit, print, and draw. So I can simply think deposit $1,000 to this account, and I don't have to worry about what kind of account it is. I'll be sure that the correct deposit function will be called depending on what type of account I have. And this is all determined at runtime. In C++, the default type of binding is static binding. This makes sense since C++ is all about efficiency and static binding is done before runtime, so programs can be as fast as possible. However, sometimes we want to defer decisions until runtime. In C++, we can opt into this behavior by using base class pointers or references and declaring our functions as virtual functions. We'll see the details and syntax of this later in this section. But first, let's look at the types of polymorphism that C++ provides so that we can put this section in context. Here is a simple chart that shows the types of polymorphism in C++. There are two types of polymorphism, compile time and runtime. Compile time polymorphism includes what we've already learned in this course, function overloading and operator overloading. We also have runtime polymorphism, and that's what this section of the course will focus on. We achieve runtime polymorphism by overriding functions and using inheritance, using virtual functions, and then having base class pointers and references. I think the best way to understand dynamic polymorphism is to use a simple example. First, let's look at a non-polymorphic example that uses static binding. In this case, we have an account hierarchy using public inheritance, as you can see on the right side of the slide. We'll assume that every type of account class has its own version of the withdraw method, and each withdraw method is different depending on the type of account. So let's create 4 objects, one for each type of account, and call their withdraw methods. When we call account A's withdraw method, it will call accounts withdraw. This makes sense since A is an account object. The compiler knows this and binds this method call at compile time or statically. The same applies to objects B, C, and D. In each case, the compiler is binding the calls to withdraw based on the information that it has about the objects when they were declared in the source code. So B withdraw calls savings withdraw, C withdraw calls checking withdraw, and D withdraw calls trust withdraw. So far, so good. It's what we've done and what we expect. But now let's take a look at the pointer P. P is a pointer to an account object. So P contains the address of an account object. Now we create a trust account dynamically on the heap and assign its address to P. Is this legal? Sure, P can hold addresses of accounts, and trust is an account. The inheritance hierarchy tells us so. So what happens when we call the withdraw method for the object pointed to by P? Well, we're using static binding by default, so the compiler doesn't really know what type of account object P is pointing to at runtime. It doesn't really care. All it knows is that P is pointing to an account, so it will call the account withdraw method. This is probably not what we expected. It certainly isn't what we wanted, since we want the trust object on the heap to use its own version of withdraw. Please be sure that you understand this simple example, since it's fundamental to understanding dynamic polymorphism. Remember, all the compiler knows is that P is a pointer to an account, so it will bind the withdraw method to the account class's withdraw method at compile time. Let's see another problem with static binding in the same context. In this example, we have the same class hierarchy, and let's suppose that each account class has its own version of a display method that displays account information based on the type of account we have. So let's create a simple C++ function called displayAccount, and it expects a reference to an account object. Since all our derived classes are accounts, we can pass any of them into this function, and this function will call the display method for the account object passed in. So you can see that the code creates 4 objects, A, B, C, and D, one for each type of account, and then it calls displayAccount and passes in each of these objects to the function. The behavior you get from the displayAccount function may not be what you expect, but by default, C++ is doing exactly what it's supposed to do, static binding. When the compiler sees the call to acc.display in the displayAccount function, it will bind the call to accounts display. So accounts display method will be called regardless of what object was passed in, and our display will only display whatever is in the account part of us. There is a way for C++ to ask the account object being passed in, hey, what kind of account are you? And then depending on that, we can have if-else statements that call the appropriate display methods. That's bad coding practice, and it also makes us program less abstractly, since then we've got to figure out what kind of object we've got and then call its functions. There's a better way. That's where runtime polymorphism comes in. Let's see how this same example works with runtime or dynamic polymorphism. Now let's see the same example using polymorphic functions. Here we see the same account class hierarchy, except that this time we've opted into runtime polymorphism. We'll see how in a few videos, but notice that the withdraw methods in the class diagram are now virtual functions. This allows us to use runtime polymorphism when using base class pointers or references. Let's look at the same example as before. Notice that the 4 account objects A, B, C, and D have exactly the same behavior. Since we're not using base class pointers or references, these examples are all statically bound, just like before. But now, let's look at the pointer P. In this case, when we call the withdraw method of the object pointed to by P, the trust withdraw method will be called. That's what we want, and that's pretty cool. The idea of using virtual functions tells the compiler not to bind the call at compile time, but instead defer the binding to runtime. And at runtime, a check will occur to see exactly what P is pointing to, and then that object's method will be called. In this case, the trust withdraw method. Let's see the other example. Again, now we have virtual display functions in our account class. So whenever we use a pointer or a reference to a base class, the binding is done at runtime, not at compile time. So now we create 4 objects, A, B, C, and D, each as a different type of account. Now when we pass these objects to the displayAccount function, the binding of acc.display will take place at runtime and call the display method based on the type of object being passed in. That's pretty cool and very, very powerful. I can now write functions, methods, and data structures that use pointers and references to base class objects and I know that the correct methods will be called at runtime. Remember that account class hierarchy we did in the last section's challenge? It used static binding since we hadn't learned about dynamic polymorphism yet. Remember all those utility functions that we wrote that were all pretty much the same? Now we can write just one version and they'll work with all the account types once we convert that account hierarchy to use polymorphic functions. Fantastic. In the next video, we'll go over how we can use base class pointers in a little more detail. Before we do the next video, let's go over here to the IDE and walk through this problem. This is the same problem we had with the account class. And what I'm doing here, I'm just creating a base and a derived class to absolutely show you and walk you through what's going on here. I'm in the section 16 workspace in the problem project. So what have I got? Well, you can see here, it can't get much simpler than this hierarchy. I've got a base class right here, and it's got one public method called sayHello. That's all. And all it says is, hello, I'm a base class. Then I've got a derived class that's derived publicly from base, and it's got the same method, void sayHello, but it says, hello, I'm a derived class object. That's it. Then I've got this function right here that I've written. This is not a member function. This is just a regular C++ function. It's called greetings, and it expects a base object by reference. Now remember, a derived is a base, so I can pass in either a derived object or a base object to this function. And this function is simply going to say greetings, and then it's going to call the specific object's sayHello method. So what do we expect here? Well, the idea would be that if I have a derived object and I pass it into this function right here, I'd say greetings and then hello, I'm a derived class object. But that's not what happens because we're doing static binding. So let's walk through this example. It's really important that you understand the static binding version before we start talking about the dynamic binding version. Here's my main. Let's create a base object. We'll call it B, and we'll simply call b.sayHello. What do we expect here? Exactly what you would think, right? Let me just scroll up just a little bit. And I'm the compiler. I'm looking in here. There is no virtual. We haven't really talked about virtual yet, but you'll see the word virtual in here when we buy into dynamic polymorphism. So the compiler sees this class hierarchy. It doesn't see anything virtual, so there's not going to be any dynamic polymorphism here. It knows that it needs to bind everything statically. And also, we're not coming at this with a base pointer. We have to have a base pointer. And we'll talk a little bit about base pointer more in the next video. So this is really simple for the compiler, right? b.sayHello. Okay, which sayHello method do I bind? This guy right here. How does it know? Well, b is a base. That's all the compiler knows is this right here. So that's what it's using. And that's just going to say, hello, I'm a base class object. And let's do the same thing. Before we run it, we'll do it again, and we'll do it this time for a derived object. So let's do that. We'll say derived d, and we'll say d.sayHello again. Same exact thing happens. The compiler knows that d is a type of derived, right? Its type is derived. So in this case, it's going to bind this method right here. Again, there's no pointers. When there's no pointers and no virtual methods, everything is static. So if we run this, what we expect is we expect this sayHello to say, hi, I'm a base class object, and this sayHello here on line 29 to say, hi, I'm a derived class object. So let's run that. And there's the output. Hello, I'm a base class object, and hello, I'm a derived class object. Exactly as we expect. Okay, so now let's run into some of the issues that we'll run into when we start using base class pointers and references. Why don't we do this function first right here? So suppose that I want to call that function. Remember, this is a regular C++ function. I'm going to call greetings, and I'm pass in the base class to it. I can do that because b is a base. And then I'm going to call it again, and I'm going to pass in d. I can do that because a derived is a base, right? That's what my inheritance hierarchy is doing for me. So what I expect here would be for the b to say greetings, hello, I'm a base, and the d to say greetings, hello, I'm a derived. But that's not what happens because we've got static binding going on. So let's run this, and you'll see the problem. There you go. You can see that right there, those two greetings is right here. There's the output. Greetings, hello, I'm a base, and then greetings, hello, I'm a base again, even though I'm passing a derived into it. And we know now that the reason that this is happening is, I'll scroll up just a little bit, is right here's the problem. We're not using dynamic polymorphism, and as far as the compiler is concerned, obj is a reference to a base. That's all it knows. That's all it cares about. So right here, that will always bind to base say hello. And that's why we're seeing that behavior. Okay. The same thing happens when we've got a base pointer. And let's do that really quickly. So suppose we have a pointer, and we'll just call it PTR. And in this case, PTR is a pointer to a base object, right? An object of that type. And we can say new derived. Now, this sometimes confuses students, but this makes perfect sense, right? Because think about it. Sometimes you think about the hierarchy, you get all confused. Think about what this really says. This really says that PTR can hold the address of any base object, right? Well, derived is a base object. A derived is a base. That's what the inheritance is telling me. So what happens here is, here's PTR. Here is my derived object that I'm creating on the heap, right? And there's really nothing in there right now because there's no attributes or anything. But this guy's pointing here. And that's okay because this is a base. So that's valid. The compiler's happy about that. But the problem comes in now when I try to call PTR say hello. We've got no dynamic polymorphism, no polymorphic functions. So what's going to happen is the compiler sees PTR is a pointer to a base. It's all it knows. So it's going to bind this to base hello, always. So we'll always bind that to base say hello. And again, this is probably not what we want. We want dynamic polymorphism to figure out what I'm pointing to at runtime and call that appropriately. So let's run this one last time. And let's see if we get a run here. We do. So here we go. Let's walk through this one more time. Here's b.sayHello. Hello, I'm a base. There's d.sayHello. Hello, I'm a derived. That's all using static binding. That's perfectly fine. Now here I'm passing in a b and a d to this method greetings. In both cases, the compiler doesn't know anything except that that's a base. So it's binding it to the say hello right here on line 21 of the base class. And then here's my pointer, and I'm calling say hello through the pointer. Again, even though I'm pointing to a derived object, the compiler doesn't care. This is not being deferred to runtime, so the compiler's binding it right now at compile time. Okay, this also, you don't have to use raw pointers for this. We haven't talked about smart pointers yet, but we will. And suppose I include memory. That's where the smart pointers live. And I could scroll down here and I could say something like, let me just close this up a little. I could say something like std unique pointer. And we can have a unique pointer to a base. And we can call this PTR1. And then we could call make unique, which creates that pointer. And the pointer is a derived this time. And we'll just empty constructor right here. So that'll create a smart pointer. This, we'll talk about smart pointers later. And then we could just say PTR1, and we can call the say hello method there. Right now, obviously we've got a pointer here, so we really should free or delete that pointer just so we're consistent with best practices here. We don't have to delete smart pointers; they take care of themselves. So if we run this, you can see that even with a smart pointer, there's a regular pointer, there's a smart pointer. They're both being statically bound, just like you would expect. All right, so in the next video, we'll talk about this base class pointer and see a little bit more about how that works. We've already seen that in order for the C++ compiler to use dynamic binding of method calls, we must have an inheritance hierarchy, we must be using a base class pointer or a base class reference, and we must declare the methods we want dynamically bound as virtual. In this video, we'll look at the base pointer requirement and see why it's so useful and so powerful. We'll use the account class hierarchy on the right side of the slide as our example. Let's also assume that this class hierarchy is now using dynamic polymorphism. We'll learn how to do that in this section of the course. For now, let's just concentrate on the effects and the power it gives us. So we'll create 4 pointers to account objects. and we'll initialize each one to a different type of account created on the heap. So as you can see, P1 holds the address of an account object, P2 holds the address of a savings account object, P3 holds the address of a checking account object, and P4 holds the address of a trust account object. We've already seen that this is valid semantically, since they're all accounts due to the public is_a inheritance we're using. Now we can call the withdraw method using the base class pointers, and C++ will figure out which method to bind at runtime based on the type of the object being pointed to by each pointer. This is pretty cool. There's nothing else you need to do once the hierarchy is set up. Of course, we need to delete the storage allocated by the pointers when we're done with them. Okay, so now let's see a more compelling use case for using base class pointers. In this case, we have the same 4 pointers we created in the previous slide, but I've declared an array that holds pointers to account objects. These will be the base class pointers. I then initialize the array to hold the 4 pointers we declared previously. Now I can simply loop through the array and call the withdraw method for each element in the array, and the correct withdraw method will be called based on the type of the object that each pointer points to. You can see how powerful this is. It doesn't matter how many base class pointers I initialize the array with or what type of accounts they're pointing to. It will work as expected. Also, if we replace one array element for another, it will also work as expected. This is what I was talking about when I said programming more abstractly or more generally. Here I'm simply thinking, call the withdraw method for each account in the array. That's it, no more details required. Of course, this also works with other collections such as a vector. Here we have the same 4 pointers, and then we create a vector of pointers to account. So the vector holds base class pointers. We can then initialize the vector to P1, P2, P3, and P4. Then we can simply loop through the vector using a range-based for loop or an iterator and call the withdraw method for each vector element. Think about what would happen if we added another class to our account hierarchy, say a bond account. None of the code that we have that works with account objects needs to be changed. Since a bond account is an account, it will automatically work with our existing code. A little note here though, be careful when you're using raw pointers in collections such as vectors. It's better to use smart pointers in this type of example, but we haven't really learned about them yet. We will soon. So there you go. I hope you can see the power of the base pointer and how much more abstractly we can think when writing our code. Let's head over to the IDE and we'll run these examples so you can see firsthand. Okay, so I'm in the IDE. I'm in the section 16 workspace in the base class pointers project. Now let me explain what's going on in this project. I've already gone ahead and taken that account hierarchy, account, checking account, savings account, and trust account, and I've made it so that it works with dynamic polymorphism. So I've done the virtual functions, I've done all that already. I just want to show you how to use this and see how powerful it is. In the next video, we'll learn about virtual functions and we'll start implementing it ourselves. But let's take a look at the main. This is really what the point of this video is. If you look at the main, you can see that first we're going to do the pointers, then we'll deal with arrays and vectors, but let's just do plain pointers first. Here you can see that I've got the 4 pointers, P1, P2, P3, and P4. Each one points to a different type of account, but they are all accounts, right? Because we've got public inheritance in our hierarchy. And then what we're doing is we're calling the withdraw method for each one of those objects. And the idea is if we've done our dynamic polymorphism correct, P1 will call the account withdraw, P2 will call the savings withdraw, P3 will call the checking withdraw, and P4 will call the trust withdraw. Okay, so let's give this a build and run. And you can see the output right here. I'll just move it over so we can see it. We can see pointers. And then the withdraw methods are called right down here. And you can see that we're calling the accounts withdraw, then the savings withdraw, then the checkings withdraw, and then finally the trust withdraw. So exactly like what we expected, we've got binding now happening at runtime. That's really, really powerful stuff. We also have the cleanup here, and I'll show you what that looks like. That's just deleting those 4 pointers, so we free up the storage that we allocated for them. All right, so now let's take a look at how this would work with arrays. And I'll uncomment this out. And in this case, I'm just printing out a line that says array so we know what's going on. And what I'm doing here, I'm creating an array, and this is the declaration right here. I'm creating an array, that's what the brackets say, of pointers to accounts. So I'm going to create an array in this case, and it's going to have 4 pointers in it. Each one of these pointers is going to point to an account object. So that's what it looks like. P1 here, right? P1 is the account, so this will be an account. P2 will be a savings account. You get the idea, right? That's a checking account, and that would be a trust account. And then what I'm doing is I'm simply looping through this array right here, and I'm calling the withdraw method for each one of those pointers. So this will call the account, this will call the savings, this will call the checking, and this will call the trust withdraw methods. Okay, so the real powerful piece here is that as you can see, I don't have to worry about that in the loop. All I'm doing here is simply calling the withdraw method for each one of those guys, and whatever happens to be there will be dynamically bound, and it'll call the correct method, which is super, super powerful. So let's give this one a run, and we can see that here's the run, and you can see the array right here. And notice what's happening here. I put P1, P2, P3, and P4 in the array. Those are base class pointers. I'm not putting account objects in the array. I'm putting pointers to account objects in the array. And they all happen to be base class pointers. That's why this works. So in this case, I'm calling this 4 times, right? 0, 1, 2, and 3. And you can see here in account, in savings, in checking, and in trust. So we're getting the exact behavior that we want. So let's modify this just slightly. And what we can do is we can take, and I'll just copy this again so we can see that output one more time so we can separate it and keep it nice and clean. What I want to do here is I simply want to say, let's set array sub 0, that first item in the array, let's set that to P4. Right? P4 is a pointer to a trust account. And then let's just loop again and call the withdraw method for all of those guys. Now our output should be a little different now, right? Because our first array element, that one at index 0, is no longer an account like it was up here when we put P1 in there. Now it's a trust account. So what we expect in the output now would be trust, savings, checking, trust, right? So let's try that out. And let's see what we get here. Trust, savings, checking, trust. You see? That's exactly what we want. It really doesn't matter what these pointers point to. It will get bound correctly. And the real powerful thing here is I never really changed that loop, right? The loop was exactly the same as it was before. I didn't have to do any checking for anything. All right, so now let's take a look at the vector version. And as I mentioned in the slides, be really, really careful when you use raw pointers and any kind of collection, but especially a vector. What you want to do is, if you're going to use them this way, where you initialize the vector this way. Don't put like something like new account or something in here, because that could be problematic when it comes to destroying those objects. You'd have to loop through the vector and destroy them yourself. But anyway, we'll just go look at this example real quick. So here's my vector. What am I doing? Well, in this case, I'm creating a vector. And what is the vector of? Right? My template parameter is a pointer to an account. So what have I got? Just like we had an array, right? We have a vector of pointers to accounts. That's my base class pointer. I'm initializing it to P1, P2, P3, P4. And at this point, all I'm doing is a range-based for loop right here. And I'm just using the auto keyword. It's going to figure out that that's an account pointer. And I'm looping through there, and that's it. I'm just calling the withdraw method for each one of those pointers that's in the vector. Again, what we expect here, because we've got P1, P2, P3, P4, we expect count. Let me go back up and make sure I get this right. We expect account, savings, checking, trust. That's the order we're putting them in. So when this runs, that's what we expect. Let's give this a run. And there's our vector case right here. And in here, we've got account, savings, checking, trust, exactly like we wanted. All right, so let's just do one more little quick change here. And what we can do is let's add 2 more items to that vector. And what we can do is we can add that trust pointer again. We can add it 2 times at the back. So why don't we do that? Let me copy this again, just so we have some separation in the output and we can better follow it. So what we'll do here is we'll just say my vector is called accounts. So I'm going to say accounts.pushback, and let's push back P4. So we're adding P4 at the end. And let's do it again. And we'll add P4 again. So now when we loop through that vector this time, we expect those first 4 output statements to be the same, but we expect 2 more output statements at the end for the trust withdrawal being called, right? Because now we've got 6 items in this vector. So let's give that a run. And here we go. You can see 1, 2, 3, 4, 5, 6 items in the vector. We're calling the withdrawal for each one of them, and you can see how the last 3 are trust, right? The 4th one was one that was already in there, and then the 2 that I just added right here. As I said, be really careful when you're using raw pointers in these things. It's better to use smart pointers. We'll talk about smart pointers in the next section. We could have used a shared pointer here, or even a unique pointer, which would make things a lot more safe. All right, so there you go. Hopefully you can see the power here. Remember, if I come up here and I've got my accounts and I decide to add a new account here, like I said, a bond account or something, any kind of account, as long as I tie it into this hierarchy and make sure that the methods that are being called are virtual there as well, then I can create an account object right here, P5, that's a bond account. And all this will work, right? All these loops, everything will work exactly the same. I won't have to modify any code because that's the point. I can think generally, I can think abstractly. If you think of this vector right here, this code right here, what does this say? It's basically saying loop through the vector and call the withdrawal for everything in the vector. That's pretty high level thinking, and that's pretty powerful. If I've got a drawing program that's drawing shapes, I could just loop through all my shapes and ask each shape to draw itself or move itself or transform itself. So I'm really able to think abstractly and not get bogged down with details. And that's the power of dynamic polymorphism. In this video, we'll learn about the virtual keyword, virtual functions, and how to declare them in your own class hierarchies. When we derive a class from a base class, we can redefine the base class's functions behaviors in the derived class. This creates a specialized version of the function specific to the derived class. If we don't use the virtual keyword with these functions, then they're statically bound at compile time, as we've already seen. Overridden functions are bound dynamically. We do this by declaring the function to be virtual. So virtual functions are overridden functions, and they allow us to think abstractly by treating all objects in the hierarchy as objects of the base class. Let's see the syntax for declaring a function as virtual. First, we declare the function we want to override in our derived classes as virtual in the base class. You can see in the code snippet that we're in the account base class, and we declare the withdraw method as virtual by preceding the function's prototype with the virtual keyword. This makes withdraw a virtual function, which means it can be overridden in derived classes, and it will be bound dynamically at runtime when we use a base class pointer or reference. Once we declare a function as virtual, then that function is virtual all the way down the class hierarchy from this point forward. Here we can see an example of overriding the withdraw function and the derived class checking. The derived withdraw function will be implicitly virtual, so we don't have to use the virtual keyword again, but it's best practice to do so. It's important to understand that in order to override a base class's function, the function's signature and return type must match exactly. If you don't match it exactly, the compiler will treat it as a redefinition and statically bind it. That's it. It's pretty simple and provides so much power. Remember, virtual functions are dynamically bound only when we call them via a base class pointer or reference. Otherwise, they're statically bound. So let's head over to the IDE and make that simple account class hierarchy dynamically polymorphic with virtual functions. It's so easy to do. Okay, so I'm in the IDE, I'm in section 16 workspace, and I'm in the virtual functions project. All right, so here we've got the simple account hierarchy. You can see we've got an account class, a checking account, a savings account, and a trust account, and they're all accounts. And right now we've only got the withdraw method, and it's been redefined in every single class. And all we're doing is just displaying in account withdraw, in checking withdraw. You've seen this one before. This just tells you which one's being called so that we can better follow it. So there are my 4 classes, and right now you can see there's no virtual keywords in here at all. So this is not going to use dynamic binding. Here are our pointers, again, P1, P2, P3, P4, each one pointing to a different type of account. And we're just simply calling the withdraw method for each one, and then we're cleaning up our pointers. Now, since we don't have dynamic polymorphism when we run this, we expect all 4 of these methods to be bound to the account class's withdraw. So let's run that and be sure that that's our starting point. And that's exactly what we see here. Those are the withdraw methods executing right here, and we're executing account withdraw for all 4 of them because we're using static binding. All right, so now let's make this polymorphic. What do? So we go to our base class and we look at the functions that we want our derived classes to be able to override. And those are the ones that we want to make virtual. There's only one example here, but typically you would have several in a base class. In this case, this is the one, withdraw. So all you need to do is put virtual in front. That's it. That's a virtual function now. Whenever I come at any derived object via a base class pointer or a base class reference, it'll be dynamically bound. That's as simple as that. It's pretty powerful. Now, I don't have to put the virtual keyword down here, but it's best practice to do so because many times users will be looking at this function, at this class here, and it's nice for them to see that it is indeed virtual. So let's do this, virtual here. I'll just copy that. We'll do it here, and we'll do it one more time right here. So now every one of these classes has overridden the withdraw method. All right. That's it. That's all we really have to do. If we run this now, we'll get our polymorphic behavior, which is exactly what we want. You see that? In account withdraw, in savings withdraw, in checking withdraw, in trust withdraw. This is awesome. I mean, one simple keyword, you get a lot of bang for your buck here. There's a lot going on. Now you'll notice a few things. We're getting some warnings here, and we're getting 4 warnings, and they're all about destructors. Whenever you have a virtual function, you need to have virtual destructors. And that's what we're going to talk about in the next video. So you can see how simple this was to do and the power that it gives you. In the next video, we'll address these warnings and we'll talk about virtual destructors. In this video, we'll talk about virtual destructors. In the previous example, we got 4 warning messages when we compiled our simple account class hierarchy. These warnings were the compiler telling us that deleting a polymorphic object that doesn't have a virtual destructor could lead to unexpected behavior. In fact, if we have a derived class object that's destroyed by deleting its base class pointer, and that class does not have a virtual destructor, then the behavior is undefined by the C++ standard. That's not good. Remember, derived objects must always be destroyed in the correct order and starting at the correct destructor. So how can we address these warnings? Thankfully, the solution is simple and intuitive. If we have a class and that class has virtual functions, then that class must always provide a virtual destructor. Once we provide a virtual destructor in the base class, then all destructors in the derived classes are also virtual. We don't have to provide the virtual keyword again, although it's best practice to do so. Here's the code snippet for the account base class. Since this class has a virtual function withdraw, then we must declare the destructor to be virtual as well. That's it. Simple solution to a potentially serious situation. Let's head over to the IDE and see what happens on my system when we don't provide virtual destructors, and then we'll add them and see the difference. Welcome back. So I'm in the IDE, I'm in the section 16 workspace in the virtual destructors project. So we've got the same account class we've had all along. And what I've done here is I've added destructors. Now, these are not virtual destructors yet. They're just plain old destructors. So you can see here's the destructor for the account class, and it's simply printing out account destructor. The checking account displays checking destructor, savings destructor, and trust destructor. Okay. And now we've got our same example that we've been using. We're creating 4 pointers to a base class object. We're creating an account, a savings account, a checking account, and a trust account dynamically on the heap. And then we're calling the withdraw method. All that will work perfectly fine right now. The problem comes in right here. When we delete those pointers, right, we're going to free the storage for them. And when we build this project, we're going to run into the same 4 warnings that we had before. The warnings are about deleting object of polymorphic class type account, which has non-virtual destructor might cause undefined behavior. It sounds pretty ominous, and it's a potentially serious warning, actually. All the compiler knows is that we've got pointers to account objects, so it really doesn't know which destructor to call. And this is undefined in the C++ standard. If we run this, we'll get one behavior on this compiler. And this is pretty standard. You can see what's happening here. When I'm calling the delete right here on the 4 pointers, we're getting account destructor. So you can see that the base class destructor is being called. Now that's a real problem because P1, that's okay for P1, right? P1 is an account, but P2 right now points to a savings account, P3 is a checking, P4 is a trust. So there could be a lot of memory leaks going on. Those destructors maybe are closing files and writing buffers out, and none of that stuff is being called. So potentially we could have a serious problem here. Thankfully, the fix is really easy. All we need to do is provide virtual destructors, and it's really easy to do. We can just use the virtual keyword right in front of the destructor, and we only have to do it here in the base class. But as I mentioned, it's good practice to do it everywhere. So there are my virtual destructors. Let me just finish up. One more to go. And here we go. Now, if we run this now, if we build and run, you'll see we get no errors. And now watch what happens. This is more like it, right? Here we're deleting P1, which calls the account destructor as before. Now when we delete P2, P2 is a savings. So you can see that the savings destructor is being called, followed by the base class destructor, which is exactly what we want. So if we're freeing memory in those destructors, if we're closing files, writing buffers, taking care of resources, now everything's going to work as we want. You can see P3 here is doing the checking destructor followed by the account destructor, and then following the trust destructor and the account destructor for P4. Remember, we're only going 1 deep here in the inheritance hierarchy. If you're going 5, 6, 10 deep, then you've got a lot of destructors that weren't called. They will be called now. They'll take care of memory, take care of resources, and so forth. The rule is really, really simple. If you've got a class and it's got a virtual function, give it a virtual destructor as well. Sometimes students ask about virtual constructors. You can't have virtual constructors. They're not allowed, and they really don't make any sense at all. Okay, so that's it about virtual destructors. In the next video, what we'll do is we'll talk about the override specifier that gets the compiler to help us out just in case we make some errors. In this video, we'll learn about the C++11 override specifier. We know that we can override base class virtual functions in our derived classes. We also know that we must provide the exact function signature in the derived class, including the return type. But what if we don't? What if we inadvertently make a small change to the function signature by mistake? If this happens, then the function we intended to override doesn't get overridden at all. Instead, it gets redefined, and we know that redefined functions are statically bound, not dynamically bound. This type of error is really hard to find sometimes, since the function signatures may look very, very similar, and it may not be easy to spot the difference. C++11 addresses this issue by providing the override specifier. You can add this specifier to the method you're writing in your derived class, and the C++ compiler will ensure that you're indeed overriding and not redefining. This is a simple addition to the language, but a very useful one. Let's see what it looks like in code. Here we have 2 simple classes in a class hierarchy. The base class has a virtual function named sayHello. It returns nothing, expects nothing, and is a const function. In the derived class, I wanted to override this function, but when I wrote the function prototype, I forgot the const at the end of the prototype. Since the function signatures are not exactly the same, the C++ compiler considers this function redefinition and not overriding. It will compile just fine since this is perfectly legal. Let's see the difference between the methods. Here it might be easier to see that the function signatures are indeed different. So the sayHello function of the derived class will be statically bound, not dynamically bound as we expected. This will cause unexpected behavior when we use a base class pointer. Here we have 2 pointers to a base class object, P1 and P2. P1 is pointing to a base object, and P2 is pointing to a derived object. When I call sayHello via P1, this will be bound dynamically, and it will call base's sayHello. However, when I call sayHello via pointer 2, I expect it to display hello on a derived class object because I expected dynamic binding. But I messed up when I created the function by not matching the signature exactly. So the function call is statically bound to base say hello. We can easily prevent this error by using the C++11 override specifier. Notice the say hello function in the derived class. We can place the override specifier after the function prototype. This tells the compiler that you intend to override this function, and it should make sure that you do so. In this case, the compiler will produce an error, and you can add that const to fix the problem. Let's head over to the IDE and see this example in live code. I'm in the IDE, and I'm in the section 16 workspace in the Using Override project. You can see here that I've got a simple base class, and all it has inside is a virtual function right here called say hello. And notice that this is a const function. And all it says is, hello, I'm a base class object. Now I've got a derived class here that's derived publicly from the base class. And what I meant to do here was to override this say hello function right here. But I messed up and I forgot that const right there. So it should have had a const there, but it doesn't. So now as far as the compiler is concerned, this function right here in my derived class is redefining the base class function, not overriding it. So it's going to statically bind it rather than dynamically bind it. Okay, so let's take a look at the main, and we'll walk through this so you can see exactly what's going to happen. Okay, so here's P1, and P1 is a pointer to a base object, and I'm instantiating a base object and pointing right to it. So now, when I call say hello via that P1 pointer, obviously this is going to do dynamic binding, and it's going to bind it to my base class, since that's what I'm pointing to. So this we'll call base say hello. In this example, this is a little different than what we've seen. Here I have P2 as a pointer to a derived object, and I'm instantiating a derived object. So in this case, what's going to happen is, this is not a base class pointer. This is just a regular old pointer to an object. So in this case, it's going to be statically bound, and we're going to call derived say hello. This is the problematic one right here, P3. The problem here is, since we did not override, instead we redefined, this will not be bound dynamically, it'll be bound statically. So as far as the compiler is concerned, I've got a base pointer right here, so it's going to bind it to base say hello. But I really wanted it to bind to derived say hello. Right, so let's run this, and then what we'll do is we'll fix this with the override keyword. So let me run this, and here's our output, and you can see our main. Let me scroll up just a little bit right here. So you can see here P1 points to a base, and it's looking at a base, so hi, I'm a base class object. In the case of P2, we're statically binding because we're pointing to a derived object, and that's exactly what we have. So it's going to say, hello, I'm a derived class object. Here's the problematic one on line 30. P3 is pointing to a base object, and it's currently pointing to the derived, right? Here's where the problem is, because I redefined that function so it's going to be statically bound rather than dynamically bound. So it's going to call base say hello, and you can see right there, hi, I'm a base class object. That's not what I wanted. I wanted it to say, hello, I'm a derived class object, because I wanted it to use dynamic polymorphism. So how do we fix this? Well, the fix is easy, right? We just come up here and put const in there. But we can also use the override keyword in C++11, which is really handy. You really should do this every time that you're going to override a function in a derived class. Simply put the override word in there. Right there, you can put the override specifier right at the end of the function prototype. So now when you compile, let me just build this real quick. Now you get an error, and the error says virtual void derived say hello marked as override, but it does not override. That gives you a really good clue as to you're not overriding anything here. So you can come in here and say, oh, okay, I got it. There's my const. You can put your const in there now, and then when you run, you can see that now. Let me scroll up just a little bit. Now you can see that third statement. It says, hello, I'm a derived class object. That's what we want. So now we've got our polymorphic behavior. So real handy, really easy to do. Use it all the time, and it'll save you a lot of grief with debugging. In this video, we'll learn about the C++11 final specifier. We can use the final specifier in two contexts. At the class level, the final specifier prevents a class from being derived from or subclassed. Sometimes frameworks have final classes that can't be subclassed. In some cases, this is done for better compiler optimization. Other times, it may be done to ensure that objects are copied safely without slicing. When used at the method or function level, the final specifier prevents the method from being overridden in derived classes. This can also be done for better compiler optimization. The syntax for using the final specifier at the class level is pretty simple. We simply add the final specifier after the class name when we declare it. In the first example, my class cannot be derived from. And in the second example, derived cannot be derived from. If you try to derive a class from these classes, the compiler will generate a compiler error. Now let's see the final specifier in the context of a virtual function. In this case, we have a simple class hierarchy with three classes, A, B, and C. The base class A declares the function doSomething as virtual. Class B is derived from A, and it overrides doSomething, but it also marks it as final. So doSomething can no longer be overridden further down in the hierarchy. Notice that if class C tries to override doSomething, the compiler generates an error. In this video, we'll see how we can use base class references and dynamic polymorphism. In addition to base class pointers, we can also use base class references and have polymorphic function calls. This is very useful when we pass objects to functions by reference and the functions expect a reference to a base class object. First, let's see how we can use references directly and achieve dynamic binding of virtual methods. We'll use the same account class hierarchy that we've used throughout this section. So let's create an account object A, and then we'll create a reference ref that's a reference to an account. That's the base class reference, and we initialize ref to A. Now if we call the withdraw method using the ref reference, we're calling the account's withdraw method, but the binding is dynamic. Let's see another example with a trust account. In the second example, we create a trust object T, and then we'll create ref1 as a reference to an account object. That's the base class reference, and we initialize ref1 to T. Now if we call the withdraw method using the reference ref1, we call the trust withdraw method. You can see that this method was bound dynamically. Let's see a more useful example. Suppose we have a method called doWithdraw, and it expects a reference to an account object. Note, this is our base class reference. It also expects a double with the amount to withdraw. In the function body, we call the withdraw method of whatever account object was passed in, and we also use the amount supplied. So let's call this method with a few objects. First, we create an account object A, and we pass A and 1000 to doWithdraw. In the body of the doWithdraw function, we bind the withdraw call to account withdraw dynamically. Now suppose we create a trust account object named T, and we pass T and 1000 to doWithdraw. The withdraw method that will be called in the doWithdraw method is the trust withdraw, since we're binding it dynamically. You can see that functions expecting base class references allow us to think in the general again and not have to worry about details. So let's head over to the IDE and try some base class references. So I'm in the IDE, I'm in the section 16 workspace in the base class references project. And let's go through a couple of simple examples here. First of all, this is similar to what I did on the slide here. Let's take a look at these three lines of code right here. Here we're creating an account object A, and we're using the same account hierarchy we've been using throughout this section. So that creates the account object, and now I've got a ref, that's my variable name, and it is a reference to an account. That's my base class reference, and I'm initializing it to A right here. So when I call ref withdraw, that's going to bind it dynamically. And in this case, I happen to be referring to an account, so it will call account withdraw. Now in this case here on line 50 through 52, we've got a trust object now, which is a little bit different. So ref1, again, is a reference to an account. That's my base class reference. And I'm initializing it to T. T is a trust account, so that's perfectly valid. In this case, when I call ref1's withdraw, what's going to happen is that method call will be bound dynamically because it'll realize that ref1 is currently referring to a trust account. So it'll bind it to trust withdrawal because they're all virtual methods. Okay, so that's pretty straightforward, I think. Now let's take a look at this function call. I've got a C++ function up here on line 40. It's the same one we did on the slides. It's called doWithdraw, and it expects a reference to an account object. That's my base class reference right there. It also expects a double, which is going to be passed in. And then in the body of this function, I'm just calling account and withdraw. So the idea here is, since the withdraw function is a virtual function, this will be bound dynamically. And here's an example. We're creating 4 accounts, A1, A2, A3, and A4. They're all different types. One's an account, one's a savings account, checking account, and trust account, as you can see. And then I'm calling doWithdraw, and I'm passing in A1, A2, A3, and A4. These methods will be bound dynamically, and we'll see this behavior, which is exactly what we expect. Now, every compiler vendor is free to implement dynamic polymorphism using virtual functions however they wish, but most implementations are pretty similar. So let's take a look at this. Let's run the debugger. And I've put in a couple of breakpoints already. And what's important here is we'll look at all these variables here. There's a lot of variables here, but we're only interested in a couple. Now at this point, we have ref and we have ref1 and all that code already executed, but let's take a look at ref. You can see ref right here, and you can see that ref is referring to an account, right? That's the whole idea. Now, you also see this bunch of code in here. You see that vptr, that's your virtual pointer. So this tells you that there is dynamic polymorphism going on. But now take a look at ref1. Here's ref1, and if we expand ref1, here you can see that ref1, while it is a reference to a base class, it's actually referring to a trust account right now. And you can see it right there. So you can see the trust account has the account part of it. And so that's pretty cool that you can see all that information right in here. And it really gives you a good idea of what's going on. Now let's take a look at the doWithdraw. We're right here on line 59. And we're about to call doWithdraw, and we're about to pass that account A1 in with 1,000. So I'm going to step through it. And now I'm in the doWithdraw. So let's take a look at what account is all about. In this case, the account that was passed in is a reference to an account, right? Of course it is. That's my base class reference. But in this case, when I expand it, you can see that it's actually referring to an account object since it didn't expand out. Let's try it one more time, and we'll do it with A2. A2 is a savings account, so I'll step through that. And now if we look at account, you can see that account, while it is still a reference to the base class, it is currently referring to a savings account. And you can see that the savings account has the account part within it. So when we execute this, and I'll just step through it real quickly, we'll do the last two. And when we see the output, and here you can see the output. So we're doing account withdraw, trust withdraw, and then we're saying account savings, checking, and trust withdraw right down here. So it's exactly like we expect. So you can see that when you use a base class reference, you still get the polymorphic behavior, which is pretty cool. And writing functions like these that expect references to base class objects is really handy to do. And it saves you from thinking in detail again. So I'm thinking here, I want to deposit that amount to whatever account was passed into me. So I can think very, very abstractly. In this video, we'll learn about a specific type of virtual function called a pure virtual function and how it lets us create abstract classes. Before we learn about pure virtual functions, let's see what an abstract class is. An abstract class is a class that cannot be instantiated. So if we have an abstract class shape, then we cannot directly instantiate shape objects. You might be thinking, so what good is a class like that? Well, abstract classes are used as base classes in inheritance hierarchies, and they're often referred to as abstract base classes. So what do we call classes that you can instantiate from? These classes are called concrete classes, and those are the ones that we've been using all along in this course. All of their member functions must be defined. Examples of these classes might be a checking account and a savings account in an account hierarchy, of faculty and staff classes in the employee hierarchy, and enemy and level bosses in a player hierarchy. An abstract base class is usually too generic to be useful to directly derive objects from, but it serves as a parent to be derived from, and those could be concrete classes. So in an account hierarchy, we're providing savings accounts, checking accounts, and trust accounts. But do we ever provide just an account? Probably not. If a customer walked in and said they'd like to open an account, they'd be asked what type of account they'd like to open. So we would never really have account objects directly instantiated in our system. We would have checking accounts, savings accounts, or trust accounts. So the account class can be thought of as a general class that's the parent to all other classes. The same can be said for the player class in a player hierarchy and the employee class in a university personnel system. In order for a class to be an abstract base class, it must contain at least one pure virtual function. So let's see what a pure virtual function is. A pure virtual function is a virtual function that's used to make a class abstract. We declare pure virtual functions just like virtual functions, but we add the equals 0 after the prototype. Typically, pure virtual functions don't have any implementation since it's really up to the derived concrete classes to define this behavior, but it is possible to give them an implementation. In the code snippet in the slide, you can see that we declared a pure virtual function named function. Whatever class this function is declared in is now an abstract class and cannot be instantiated. So we see that a pure virtual function makes a class abstract, which means we can't directly instantiate them. But when we derive a class from an abstract class, we must override the pure virtual functions in the base class in order to be a concrete class. If we don't override all the pure virtual functions in the base class, then the derived class will also be abstract. This is very useful when it doesn't make sense for a base class to have an implementation, but it does make sense in concrete classes. For example, suppose we have a shape hierarchy. The concept of a shape is too general or too abstract to have shape objects in our system. So we can define the draw method as a pure virtual function in the shape class. And that not only makes it an abstract class, but it also forces all derived classes to implement the draw method if they want to be concrete classes. And we can say the same thing for the defend method in a player class. Here we see an example of a shape hierarchy. Suppose we're creating a simple application that allows us to draw and manipulate shapes on the screen. The shapes that we would be drawing and manipulating would be lines, circles, squares, and probably many others. So we will have circle objects, line objects, square objects, and so forth. Would we ever have a shape object? No, a shape object is just an abstraction that we can use as a base class. If we declare two pure virtual functions, draw and rotate, in that shape class, then all derived classes must override these methods or they will also be abstract. You can see in this class hierarchy that shape, open shape, and closed shape are all abstract classes since their names are italicized, and line, circle, and square are concrete classes. Here is the partial code for the shape class. Notice the declarations for the pure virtual functions. It makes no sense to provide implementations for draw and rotate in the shape class, since we have no idea how to draw or rotate the abstraction shape. We'll leave that up to our concrete classes. In this example, we derive a circle from a shape. If this class overrides the draw and rotate virtual functions, then it becomes a concrete class and we can instantiate circle objects. In this case, we're overriding the pure virtual functions, so the circle class is a concrete class. So remember, abstract base classes cannot be instantiated directly. If we create a shape object, shape, the compiler will give us an error. Also, if we create a shape object dynamically on the heap, we will also get a compiler error. But we can use base class pointers and references, as we've already learned, to achieve dynamic polymorphism and have some very powerful, reusable, and flexible class hierarchies. Notice that PTR is a pointer to a shape, and then we create a circle object on the heap and point to it from PTR. Now we can call draw and rotate via the pointer. How do we know this will work? Well, it has to, because all concrete classes derived from shape must have overridden the draw and rotate methods. That's pretty awesome. Let's head over to the IDE and see an example that uses pure virtual functions and abstract base classes. So I'm in the IDE, I'm in the section 16 workspace in the Pure Virtual Functions project. What I've done here is I've created a shape hierarchy, And I'm using pure virtual functions to establish an abstract base class. So let me walk you through this, and then what we'll do is we'll run some examples when we write a main, and we'll create some shape objects and call some of the methods so that you can see exactly how this works. Okay, so here's my shape class. Notice that the shape class has these two pure virtual functions. One is called draw, one is called rotate. That makes this class shape an abstract class. In this case, it's going to be an abstract base class because I'm going to derive from it. I cannot instantiate shape objects. I can't say shape S. Okay, I can't even go at it through a pointer. I can't say pointer P equals new shape. Okay, right there I'm trying to create a shape object directly. I can't do that. So both of these will give me compiler errors. An error will say something like you can't instantiate an abstract class or something like that, which is a good error. It makes sense. So that's my abstract base class. Notice the virtual destructor, always use that when you've got virtual functions. Perfect. So now let's create an open shape. An open shape would be a line, a spline, things like that. And closed shapes would be circles and squares and so forth. So here we're creating a class called open shape. Notice it's derived publicly from shape. Also notice that I did not override those two virtual functions. So that makes this class abstract. I cannot instantiate open shape objects. Same idea here. Here I've got a closed shape that's derived publicly from shape. I am not overriding those two methods that you can see in the base class in here. So this class, again, is an abstract class. Okay, so now let's look at our concrete classes. Those are the ones that obviously know how to do things. It makes no sense for me to write code here that draws a shape or rotates a shape. I have no idea what a shape is, right? This is just an abstraction for a shape. Rotating a square versus a line is very different. And drawing a line versus a square is very different. So the concrete classes are the ones that take care of that. Okay, so let me scroll down just a bit till we to concrete classes right here. So these are my concrete classes right here. You can see I've got a line, I've got the circle, and I've got the square right here. So in this case, I'm not deriving directly from shape. A line is an open shape, so I'm taking advantage of that. It's a concrete class this time because you can see right here, I'm overriding both of those pure virtual functions. That makes me a concrete class. So now I can have line objects. Same with circle. You can see here, circle is a closed shape. And right here, I'm overriding those two pure virtual functions. And then down at the bottom, you can see exactly the same thing with the square. Right here, you can see that square is a closed shape, and I'm overriding those two pure virtual functions so I can have square objects out there. Okay, so this is the same hierarchy that you saw in the slides that was displayed in the UML diagram. Now, let's write some code that will allow us to use these. Okay, so let's write some code in the main. We can start off by just trying to create a shape object, right? We can create a shape object S, or we can come at it with a pointer just like we did a little bit ago. We'll just call it P as a new shape. And you can see that if I try to compile this, it's not going to compile. There's my compiler error. It says cannot declare variable S to be of an abstract type shape. And same thing here with this new shape. I'm not allowed to instantiate shape objects, okay? So we've seen that before, and that's a function of those pure virtual functions. The fact that they're in there makes the classes abstract. I'll comment these two lines of code out, and if we also try to instantiate open shapes and closed shapes, we'd also get the same error because they are also abstract classes. Now, suppose we create a circle, right? We can certainly do that. We can say circle C, and we can call c.draw. We know it's there. Now, in this case, you can see it says drawing a circle, right? But this is not coming at it with a base class pointer. This is all being statically bound. We're not using dynamic polymorphism here, and that's okay. Sometimes you want to do that. But the real purpose of creating that abstract base class is so that we can come at this class hierarchy with base class pointers or references. So let me comment that code out as well. And let's create a base class pointer. So the base class in this example is shape, right? So we'll create a shape pointer, and we'll just call it PTR. And what we'll do is, remember, I can't say new shape here, but I can certainly instantiate derived concrete classes. So what I'll do is I'll create a circle. And now if I do PTR draw or PTR rotate, So you can see now that if I call the draw and rotate methods through the base class pointer, what's going to happen is we're having dynamic polymorphism, so the function call will be bound at runtime. And we're going to call the draw and the rotate for the circle because that's what I'm pointing to. So if we run this, we can see that we're drawing and rotating the circle, which is pretty cool. Okay, so now this is exactly like we've been doing before. The only difference here is that we're using those pure virtual functions to define an interface, if you will, at that base class level. And all our concrete classes must implement those pure virtual functions, otherwise they are abstract themselves. Okay, so let's look at a couple of other examples, and let me comment this out again real quick so it doesn't clutter up our display. And let's just create a few shape objects. So let's create a few shape objects through pointers. So let's say S1 is a new circle, S2 is a new line, and finally we'll just say S3 is a new square. Okay, now remember, we've got all shape pointers here, right? All base class pointers. And what we're actually pointing to are our concrete derived classes. So that's pretty cool. Now what we can do is, let me write the code here to delete these guys down at the bottom, so we definitely don't want to leak. Okay, so I've written the code to free up that allocated storage down at the bottom, and now we're free to use these guys. So what do we want to do? Well, why don't we put them in a vector and then loop through the vector and call each one of their shape methods, let's say the draw method. So let's create a vector. And what is that vector? A vector of? What's my template parameter there? Well, it has to be a shape pointer, right? It can't be a shape coming at it from a base class pointer. So in this case, I have a shape pointer. And again, I'm using a raw pointer here in the shape, so you've got to be really careful when you do that. In the next section, we'll learn about smart pointers. You should probably be using a unique pointer here or a shared pointer, but in this case, this will work just fine. So there's my shapes, and let's set it to S1, S2, and S3. So there's my vector. It contains pointers to shapes, and I've got all three of them in there. And now what do? Well, let's loop through that vector, right? So we'll use a range-based for loop, and we'll say for, let's say const auto p. P is going to be the pointer to the shape in shapes. And when I'm here, I can just simply call p's draw. That's it. Simple as that. If I run this now, I should get 3 lines of output, one for each of those objects. So in this case, I'm calling drawing a circle, drawing a line, and drawing a square. So you can see that's pretty cool. Imagine you have a collection of base class pointers, and they're all pointing to objects on the screen, right? All of those objects are going to be concrete objects. And then let's say you want to refresh your screen. What do? Well, you just loop through that collection and say draw, 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 draw for each one of those objects, right? And each one of them knows how to draw itself. Makes it super easy to think abstractly and think in the general. So why don't we actually do that? Why don't we write a function, just a basic function right here. We'll call it, let's say it's void. Let's call it screen refresh. Okay, so it's called screen refresh, and what are we going to do? Well, we're just going to pass that vector into here and let the vector do its thing. So const, again, it's a std vector of shape base class pointers. And we'll pass it by reference so we don't copy it. That's it, right? That's pretty cool. So now I'm going to say std cout. I'll just say refreshing, just so we know it's being called. And now we'll just loop through that vector, right? So I'm going to say for, again, same thing we did before. For const, we'll use auto p again. And shapes is my collection. And right here, all I'm doing is p draw. That's awesome. I mean, think about the power that we have here, right? Remember, we're coming at this with a vector of base class pointers. So we know we've got dynamic polymorphism kicking in. We know that each one of those derived classes that are concrete must have implemented draw. So I can simply call this without even worrying about what I'm pointing to, so I know it'll be bound correctly at runtime. And all we need to do now is, let's comment this loop out here, and let's just call that. We'll call screen refresh, and we'll pass in the shapes vector. And there you go. Refreshing, drawing a line, circle, drawing a line, drawing a square. That's pretty cool. So you can see the real power here. And again, the real power of the pure virtual functions is to really force all your derived concrete classes to implement those methods. Now you know that they must be implemented, so you can create base class pointers and just call any of those guys, and you know that they're there. They have to be there. In this video, we'll see how we can use abstract classes as interfaces in C++. An interface class in C++ is a class that has only pure virtual functions. These functions provide a general set of services that users of the class can use. In order to be useful, these pure virtual functions must be declared as public. Any class that wants to be a concrete class and support the interface provided by the interface class can override the pure virtual functions and implement these services as needed. Remember, every service must be implemented, and C++ will strictly enforce type information, so when overriding, the function prototypes must match exactly. Unlike Java, C#, and other languages, C++ does not provide a specific keyword or way to create an interface as part of the C++ core language. So in C++, we use abstract classes with pure virtual functions to achieve the concept of an interface. Suppose we want to be able to provide any user-defined object the ability to be printed on a stream like cout. We can do this by creating a printable interface class that provides the service in terms of a pure virtual function. And then our user-defined classes can simply be derived from printable and override this pure virtual function. Let's see an example. Here you can see that we have a class named printable, and it has a pure virtual function named print. This makes this class an abstract class. The printable class also adds a friend function that we'll use to allow us to print any type of object that conforms to this interface. You can see that the overloaded operator function at the bottom of the screen, and it calls obj.print. This will dynamically bind to the print function of whatever object type was passed in, since we know that that object is printable and we have a reference to it. That's pretty powerful stuff. At the end of these slides, we'll head over to the IDE and I'll show you how we can use this interface with the account hierarchy, as well as with non-account classes. So for any class to be printable, it must be derived from printable, and it must override the pure virtual function print that's in the printable interface. That's it. So in this case, you can see that any class is derived from printable, and it does override the print pure virtual function. Now, any class is a printable. So let's create some any class objects and print them. First, we create ptr as a pointer to any class and create an any class object. Then we dereference the pointer to get that object, and we use it in an output statement. This will call the overloaded insertion operator, which will in turn call the function print of any class. And this will display hi from any class. Now, suppose we have two functions, function 1 and function 2. Function 1 expects an any class object by reference, and function 2 expects a printable object by reference. Well, we can call both these functions and pass in the object ptr is pointing to. Why? Because that object is an instance of any class, and because that object is a printable. In both cases, we get the same output. The print function in any class is bound dynamically. Let's see another example. Here we have a shape class that only has pure virtual functions. So it's an abstract class, and it can also be used as an interface class. What we're saying is, if you want to be a concrete shape, then you must be derived from shape, and you must override the draw and the rotate pure virtual functions. So let's do that. Here we declare a circle class derived from the shape class. We know that if we want a circle to be a concrete class, then we must override draw and rotate. And that's exactly what we're doing in this example. Sometimes you'll see classes that are intended to be used as interface classes named with a capital I preceding the class name. This makes it easy to know just by the name that the class is intended to be used as an interface. As you can see in this example, shape was renamed to iShape. Now, when you see circle being derived from iShape, you know that iShape is intended as an interface class. This isn't a requirement, but you tend to see that out there. So we can now use pointers to iShape objects to use dynamic polymorphism. Here we create a vector of pointers to iShape objects, And then we create 3 pointers and initialize them to point to 3 different types of shapes. In order to call the overridden functions in the concrete classes, we simply loop through the vector and call the functions. You might be thinking, isn't this the same as we did before? Yes, since we must use inheritance and pure virtual functions as interfaces in C++. But there's another difference, and I'll show you that example in live code. Let's head over to the IDE now and we'll see. Okay, so I'm back in the IDE. I'm in the section 16 workspace in the interfaces-start project. What we're going to do eventually is to implement that printable interface so that we're able to print any kind of class objects on a stream, any kind of class objects that conform to the printable interface. So let's use this account hierarchy as a starting point. This is similar to what we did in the previous section's challenge. I've gotten rid of a lot of the other stuff that's not necessary, but let's just look at the key elements here. Here we've got a class account right here. And you can see that we have a friend function that overloads the insertion operator. It expects an output stream and an account object by reference. Perfect. Now, we're going to implement that. We're going to implement that right here. And you can see that it's obviously a friend. It's not a member of the class. And it expects an account. So if we have an account object and we put it on a stream, this should fire and print it out. And that absolutely works. And all it does is just says account display. Okay, so now let's look at a checking account. You can see the checking account is doing the same thing. We're duplicating this code all over the place. And it's right here. There's my checking account. It is an account. Well, I've got to do this now with a checking here. So I'm implementing it over here. So this definitely works with the checking account. And it displays checking display. The reason that we have to do this is because friend functions are not inherited. So even though I've got this guy up here, I'm not getting him down here or further down the hierarchy. So that's one issue. The other issue is that in order for us to implement this operator, the insertion operator, it really doesn't make sense for it to be a member function. Remember, if it was a member function, I'd need the object on the left, followed by an insertion operator, and then the stream. Well, that's not how we do it, right? We're doing something like stream object. So this really would work for sure, but it would feel really clunky and nobody would ever use it. So we're running into a problem now. We're doing the same for the savings account class right here and the trust account class right here. So that's all we're doing is we're just creating these 4 classes, overloading the insertion operator for each one of them, and each one of them will display, savings display, trust display, and so forth. So we can have a simple main, and this is what main looks like right here. Give me an account A, put it on the stream, give me an account C, same thing. You get the idea. ACST, we should see account display, checking display, savings display, trust display. So let's run that and be sure this works. And that's what we get. We've got our 4 objects, the account, the checking, the savings, the trust, everything works like it should. But it really doesn't. There's one problem here. And let me copy some code that I've already written in here just to save a little time. So here's the code we've got now. We've got P1 is a pointer to an account, right? That's a base class pointer. And I'm creating an account and pointing to it from P1. And then I'm going to put the object, right? So I need to dereference P1 because P1 is a pointer. So I want the object it's pointing to, and I want to put that on the stream. This will call the overloaded operator for the account. Now I want to do the same thing with P2, except P2 this time is actually pointing to a checking account. Although, again, we're coming at it through a base class pointer. And I want to dereference P2 and put it on the stream. So what we expect is to say account display, checking display. But that's not what happens. And let's see what happens. You see what happens is account display, account display. Why does this happen? Well, it happens because we've got no virtual functions going on, right? The only virtual functions we've got are, let me close this down so you can see it exactly. Let's go up to my account class. And the only virtual functions we've got are withdraw, right? That's it. That's the only virtual function we have. We have no virtual function that's going to allow us to work with any kind of account object in the context of this operator here. And it's really clunky to do so because of the syntax. So what we could do is we could certainly add some kind of print function to this account class, and it's inherited all the way down and make it virtual. And that's kind of what we'll do. But what we'll do is we'll create a separate interface class rather than put all this stuff in account. And what that buys us is that not only am I able to use that printable interface class that we're going to create with this account hierarchy, I can use it with any kind of class, not just these account classes. So let's do that. What I'm going to do is I'm going to switch over to the interfaces-complete project. Right now it looks just like this one, but what we'll do is we'll modify it and get this working with the printable interface. Okay, so I'm back in the interfaces-complete project. And you can see that right now it's exactly what we did earlier. I haven't changed this code at all. So this is exactly what was in interfaces-start. So what we want to do is we want to create an interface class called printable or iPrintable. We want to define a virtual function in there, and then we just want to extend this so it makes more sense and it works better. So first thing we're going to do is we're going to clean up this mess that we've got going on here. So I'm going to delete all these friend functions right here, and I'm going to delete their implementations as well. So I'm going to get rid of the account one, and this will definitely clean up our code a lot. I'll get rid of this guy right here. I'll get rid of that implementation for the checking account. I'll get rid of the one in savings, and I'll delete the implementation for the savings. And then finally, we'll do the same for trust. So I'll get rid of that, and I'll get rid of this as well. Okay, so now we've got a much cleaner look. Let me scroll all the way up here. So all we have now is the account class with its virtual void withdraw, virtual destructor, checking with its virtual void withdraw, virtual destructor, and so forth. So we're at a really clean place to start. So what do we do? Well, the first thing we want to do is we want to create that printable class interface. So let's do that. And of course, you would normally do this in .header files and .cpp files, but I'm going to do it all in one just so it's easier and I don't have to switch between files to be able to explain this. So let's do that. So we'll create a class called, let's just call it iPrintable. You can call it with or without that I, it's really up to you. So that's my class, and I'll close it off down here. Now, what do I want in this class? Well, I need a friend, right? I have to have a friend because of the way that insertion operator works, where the left side is the stream and the right side is the object. I really can't have member functions that do that kind of thing. So what I want to do is I want to have a friend function that's very similar to the ones we had before. So let's say friend, and it's going to return a std_stream by reference. We're going to overload the insertion operator. And the two parameters are the std_stream and the printable object. That's where things really change. So let's create the std_stream by reference and a const iPrintable object by reference. We could just call that obj or our right-hand side, whatever you like. So that's my function prototype. And now what we want is we want to have a public pure virtual function that all classes that conform to this interface must implement. That's the one that's going to allow them to put whatever they want on the stream, however they want. So in this case, it'll be virtual, let's say void, and we'll call it print. We can call it anything we like. And we're going to put stuff on an O stream. This should be const since we really don't want it modifying any objects. And here's the important piece. That's a pure virtual function now. Okay, so now let's implement that friend function. I'll copy this so I don't have to type it all out again. And what we want this function to do is really pretty straightforward. All we want this function to do is do, let's say, obj, right? That's the object. And we want to print onto that stream. That's the virtual function that all of my concrete classes must implement. And then I just simply return the stream. That's it. Now notice what's happening here. This function gets called with a printable or an iPrintable. And it's going to call print on that object. So this we're coming at it with a base class reference, right, if you will, because they're all going to be printable. And we're going to use dynamic polymorphism to match the appropriate one. So that's really all we need to do here. So that's a really, really simple class interface. We only need to do this with the account class because we've got a hierarchy here, but I'll show you another way to do it as well in a second. So we could say public iPrintable. Okay, so now we're saying that that account class conforms to this iPrintable protocol, which means that it must implement this guy right there, that virtual void function. So we can do that right here. We could say virtual void print, right? It expects a std_stream by reference. We can call it OS, and it is a const method, and I want to override. I want to definitely put that in there so that the compiler can help me in case I messed up. That's it. And what do we do here? We just simply say OS account. Let's just say display. That's it. That's all we have to do. Now, for all the other classes that are derived from this account class, what we need to do is implement that virtual function in them in whatever way makes sense to display a checking account. In this case, I'll just say checking. Right? In this case, I'll just say savings. But again, whatever makes sense. You want to display interest rates, whatever makes sense for a display of a savings account. And here we'll do the same thing with the trust account. Okay, that should do it. So now if we build and run, you can see that we got what we wanted, right? There's the 2 pointers. So P1 now points to an account, and I'm displaying accounts display. And P2 is pointing to a checking, and I'm getting checking display. That's pretty cool. Okay. And obviously these guys will still work too, since it's doing static binding, so that's easy. But here's the difference. Again, you might still be wondering, so far, so what? Well, the difference here is that suppose we want to create a class called dog. And that dog class wants to be printable. So it is derived from printable. So all this dog class has to do is implement that interface. So let's do that right here. I'll say public. And the interface is right up here. I'll just copy this guy to save myself a little time because it's the same function. And how does a dog display itself? Well, maybe the dog says woof woof. Simple as that. So now what I can do here is I can create a dog object. And I can do it dynamically, right? So I need to put a pointer in there. That's it. And now I can simply put that dog object on the stream. So I can cut and paste. I'll copy from here. And rather than P1 this time, it's dog. So I'm dereferencing dog. And when I run now, there you can see woof woof right there. So that's pretty powerful. Okay. Last thing is, we can take it a step further, and what we can do is we can actually write a function, and I'll just copy it here so you can see what it would look like. Right here, this is just a regular C++ function, and it's called print. And what does it expect? It expects an iPrintable. So it'll take anything. It'll take a dog object, an account object, a savings account object, because they're all printable. Okay. So again, we could pass all of those guys into there. So if, let's say I'm right here in my dog, I could say print, and I can pass dog into it. And if I run that, I should see woof woof twice, and there you can see it right up here. And you could do the same thing with the account objects. This is where this is different from just regular inheritance from a base class. In this case, I can use this printable across hierarchies, across anything I want. I can just say that whatever I'm creating is printable, overload that print pure virtual function, and I'm good to go. I'm a printable. So remember, in this case, dog is a printable, an account was a printable, a savings account was a printable, a savings account was also an account. And this is a really good use case for it. Welcome to the Section 16 challenge. This challenge is all about polymorphism. I'm in the Section 16 workspace, and there's going to be a couple of projects here. First, we've got the challenge project. This is the base source code that I'm providing for you. Then we'll break this up into a few parts in several different videos so that we can take this step by step. So right now we're in the challenge project, and I'm in the description.txt file which describes this challenge. So what's the idea? I think you know what you're going to have to do, right? You've got the solution that we had for last section's challenge where we have the account class and it's all working great. Well, now we need to modify that so that it's polymorphic, so that we're using dynamic polymorphism, so we can use base class pointers and get this all working using dynamic polymorphism. It's going to be pretty cool, but it's going to be some work. So let's see where we're at. We've got the source code that I provided, and your challenge is as follows. Remember, the source code right now has no virtual functions in it. Therefore, it's all being bound statically. That's what we want to change. So here's the challenge. Part one of the challenge is modify the account class so that it's now abstract. How do you do that? Pure virtual functions. We want two of them, and they're right here. I'm giving them to you right there. Deposit and withdrawal will now be pure virtual functions. Remember, we can implement these in the account class if it makes sense. In this class, it does make sense. So you may want to consider implementing a simple deposit and a simple withdrawal in the account class. Even if you implement these in the account class will still be abstract because it's got those pure virtual functions in it. That's going to take some work because you've got to revamp your class hierarchies. You've got to think about what you're doing. Remember, once you put virtual functions in there, like we are here, don't forget about the virtual destructors. So there's a lot of little things that you'll have to do along the way. Great. Now, part 2. Create the iPrintable class interface, similar to what we did in the class. The idea is that all accounts are going to be printable. So I've given you the class right here. I haven't implemented this guy. You guys can do that. And obviously, the account class can be derived from iPrintable. So now it's printable. And all those concrete account objects can implement that guy right there. And they should be printable, which is pretty cool. One little hint here. You'll notice this destructor right here. Obviously, we need virtual destructors. We can use equal default. It tells the compiler, just generate a simple destructor for me. So this is really the same as you writing that kind of code, but you don't have to do it at all. Just say equal default and let the compiler do it for you. Then the last part of the challenge is to modify the functions in that account.util file that I gave you. Remember, that one had a display, deposit, and a withdraw for an account. And then it had a display and a deposit and a withdraw for a checking account. And it just had a lot of code in there. What we want is we just want one version of each. So we want one display function, one deposit function, one withdraw function that will work with any kind of account. And you'll notice what's going on here. There's our base class pointer. That's why this is going to work. So in this case, when we create these vectors in our main, we're going to create a vector of base class pointers. And that's what we're going to pass into these functions here. Finally, test your code both with base class pointers as well as local objects. I've given you a main driver that gets you started, but I'd suggest that you just take it one step at a time. It's really the best way to do it. What I would suggest that you do for the very first thing is take that account class and make it abstract. Add those pure virtual functions to it and start from there. And then work your way down the class hierarchy and see what you have to override, what you don't have to override, and so forth. That's it. Have fun. This is a very, very challenging exercise. There's a lot going on here. So again, take it one step at a time. Don't think that you'll be able to do this in 15 minutes. This will take some time and some thought because there's a lot going on, a lot of little pieces to this. All right, so give it a shot. I'm sure you can do it. Take your time, think about everything you learned in the class, and put it all together in this challenge. I'll see you in the next video where we'll do part 1 of the solution. Part 1 is taking that account class and making it abstract. Welcome back to the Section 16 Challenge Solution. This is part 1 of the solution to this challenge. This was a very, very challenging exercise. I hope you're able to finish this, and I hope your solution worked. As usual, your solution could be different from mine. Very likely it is. So let's get started. First thing we want to do is we want to make this account class an abstract class, and we know that we can do that with the pure virtual functions. So that's what I'm going to do right here. I'm coming down right here to my deposit withdraw functions, and I'm going to say virtual, and I'm going to make it pure virtual right there. My class is now abstract. I'm going to do for both of them. And again, I've got a pure virtual function here as well. Okay, so that was easy, right? That's cool. Eventually we'll get rid of this guy and we'll replace it with a printable interface, but we'll leave that for later. So we've got those 2 pure virtual functions. So if I try to create an account object, I won't be able to any longer. So let's take a look at the account implementation file and see if there's anything in here we need to change. Our constructors are fine. You might be thinking, why do I need a constructor if I'm never going to create these things? Well, you are, right? You are through the derived classes. Remember the constructor calling up the chain. So it's important that we have constructors here. There's our deposit and there's our withdraw. Now, these are pure virtual functions. Can we implement them? Absolutely we can. And in this case, it makes sense. We've got a really simple deposit, really simple withdraw. In the case of the examples I gave you with a shape, and how do you draw a shape in the base class? You really can't. But here, we can say that deposit and withdraw, this is the simplest case, and I'd argue that we would leave this in here. Now, there's one little thing that's missing. That's our virtual destructor. That's really important. So let's do that. We'll say virtual. The destructor is the name of the class with the tilde in front. And we could implement this thing, or we could just simply say equals default. And that's good enough. That tells the compiler, hey, just give me a default destructor in this case, and that's fine. I don't need any special behavior in the destructor, so that will be just fine. All right, so now what are we going to do next? Let's look at one of the derived classes. So let's start with checking. So let's look at the header file for checking account. You see here it's derived from account, that's fine. So remember, I've got two pure virtual functions in my parent that I need to implement here. So I'm implementing one of them right here. So I want to make sure that this is virtual, and I want to be sure that I'm overriding this. That way the compiler is going to help me out if I rename something incorrectly or if I change one of the parameters or something. Now what about this guy, this deposit method? We want to implement this guy in here ourselves as well. So we'll just say virtual bool, and this is the deposit method. So we're going to implement this ourselves, and it expects the double. And again, I'm overriding here. So I want to be sure that the compiler is helping me. Okay, perfect. What else do I need here? You guessed it. I need a virtual destructor for a checking account. And I'm going to let the compiler give me a default version, which is fine. Okay, now this guy wasn't here before, so we're definitely going to have to implement that in the CPP file. So let's go into our CPP file for checking account. And here's our withdraw. We're calling our parents withdraw, which is fine. Here's our constructor. That looks good as well. Again, these output operators, we'll get rid of them later, but we need to implement this guy, our deposit. And it's going to be a checking account deposit. That's the class we're in. We don't need the override here. We already have it in our header file. And we do need a name for this parameter. So what do we do here? Well, we're simply going to return and call our accounts deposit method and pass in the double. That's it, right? I have nothing special to do here, so I'm just calling my parent. So that takes care of checking account. Now let's go down to savings account, and we did put the destructor in there, right? Yes, we did. So let's go to savings account. Same idea here. We've got a virtual function here that we're going to override. That's my deposit. And we'll say override right here. And then we've got the withdraw. So I also want to take care of that one here. So I'll say bool, we'll call this withdraw, and it expects that double amount. And again, we're overriding. This is one we'll have to implement because we were not implementing it before. And then we also need a virtual destructor here. And the name of the class is savings account. Let the compiler give us one by default. Okay, now this withdraw method is the one we have to write. So let's go to our implementation. So I'm opening up savings CPP. My constructor looks fine. My deposit looks fine. We'll get rid of the insertion operator later, but let's implement this method here. So this is bool for a savings account. And all we are doing here, again, we don't need the override here, only in the declaration. And what we're doing here is we're just simply returning our parent, which is the account, and we're asking it to withdraw that amount. That's it. And then the last one we've got is the trust account. So let me go to its header file. And let's see what we've got here. We already have deposit and withdraw. That's good. We've already implemented them. So let's just be sure that we implemented them correctly and we didn't just, that we are overriding them and not redefining them. So we'll put override over here as well as on the withdraw. Okay, that's it. Let's take a look at the CPP file. All that looks good. And the last thing we need here is our destructor. So we'll create a virtual destructor for our trust account and let the compiler give us one. All right, so that's the first step. So now let's go to our main, and you'll notice I commented out all the driver code that I provided for you because I just want to start really fresh here. And the first thing I want to do is let's just do this right here. Let's just create an account and call it Joe. Real simple. So let's build and run. And we have an error. I forgot a semicolon there, so let's try that again. And I spelled virtual wrong. Okay, let's get all those errors out of the way. There's account Joe, finally. So now we have a clean compile and it says variable Joe is abstract, account abstract. I can't do this. So this is good, right? This is a real good thing. We now know that our account class is abstract. We can't create any. So let's comment that out and let's create a checking account. Remember, this is not using a base class pointer. This is just a regular old local variable. And we're going to create a checking account and let's just use the default. So now let's test this out. We've created the C object, which is a checking account, and let's display that and see what we get. Now this should still work because we overloaded those insertion operators when we did this previously, and as long as we're not coming at this with a base class pointer, they should all still work. So let's try that out and let's see what we get. There we go. We've got a checking account, unnamed checking account with a 0 balance. That's exactly what we expected. So let's create a savings account object. We'll call it S, and we'll initialize it to Frank with $5,000 balance and 2.6% interest. And let's display that and see what it looks like. All right, let's try that out. Here we go. We've got a savings account object, Frank 5,000, 2.6. Perfect. So this all seems to be working perfectly. So now why don't we create a base class pointer? So the base class is the account class, right? So we'll create a pointer called PTR. And let's create a new trust account. So we'll create a new trust account on the heap, and that will be, let's say, Leo with $10,000 balance and 2.6% interest. So that should create that object on the heap, and the pointer will point to it. This was perfectly valid since a trust account is an account. Now let's display that and see what we get. Now we can't display PTR here because that will display the address of that pointer. We need to display the object. So we need to dereference PTR. We need to go to where PTR is pointing and an end line here. Now this won't work as we expect. The reason is we haven't really handled the insertion operator to work with dynamic polymorphism. So as far as the compiler is concerned, that insertion operator, compiler knows that PTR is a pointer to an account. It really doesn't care what type of account it's pointing to. So it's going to bind this statically and it'll slice that object. It'll slice the trust account stuff away and just keep the account part. So this should still display Leo and 10,000 though, because all accounts have the name and their balance. So let's give that a try and see what our output is. And that's exactly what happens. You see right here, account Leo 10,000. We're not getting the trust part of us, right? It's not even displaying trust account, it's just displaying account. We'll fix that when we implement that iPrintable interface. That'll be pretty cool. So we can see that this seems to be working. Let's test this out, and let's just test it out with S right here. Let me comment out this Leo part here, and let's just say that we want to deposit, let's say, $10,000 into S. And then I want to display S again. So let's try that out. And you can see here, I have my savings account Frank with 5,000 and I just deposited 10,000 into it. It's a savings account, so it's going to use that interest rate to give me a little bonus, and that's exactly what happened. So that looks correct. And then finally, let's withdraw. So now let's say we want to withdraw $10,000 from S. And again, we'll display S. And we'll test out our withdraw functionality here. We'll give it a run, and we can see that we have savings account 5,000, then we deposited 10,000, and then we withdrew 10,000. So it's all looking good. So you see, it wasn't too much work to get this to work with dynamic polymorphism. The next step now is let's get rid of all the overloaded insertion operators that's in this code, and let's create that printable interface and get that working. And then the last thing we'll do is we'll take care of those functions in the account util file and clean that up because there's a lot of duplicated code in there. Okay, so welcome back. This is part 2 of the solution to the section 16 challenge on polymorphism. If you recall, in the last part, what we did was we took the account class and we made it an abstract base class by adding those 2 pure virtual functions for deposit and withdraw. Then we went through all the classes, gave them all virtual destructors, made sure our deposits and our withdraw methods were running correctly, and so forth. So everything was working great. And right now, the source code that you see in Challenge Solution Part 2 project, which is the active project right now, is exactly where we left off in Part 1. And this is the only test case I'm really interested in right now. I've got a base class pointer. I'm creating a new trust account, and I'm displaying that object on an output stream. And when I run this, I don't really get what I want. I get the account part of the object. You remember what we talked about last time. So what that means is that this is being statically bound, not dynamically bound, and the object is being sliced, so the trust account part of it is being discarded. And we're displaying account instead of trust account, the account name Leo, the account name balance, which is part of that account part of me, but the interest rate is not displaying. And the same will be true for savings and checking accounts. So what's the fix? Well, there's a lot of ways to fix this, but the way we're going to fix it is we're going to create an interface class called iPrintable, and we're going to let account be derived from iPrintable, and then all of the concrete classes will implement how they want to be displayed. Okay, so let's get started with that. So the first thing we want to do is we want to create the iPrintable class. So you can right click here on source and select new class and give it the name iPrintable. You could just call it printable if you like. I'll name it iPrintable. And the block guard I'll use is just I_printable_H_, just like we've done before. You can choose to leave this blank and CodeLight will generate one for you. That's it. I'll select OK. So there's my iPrintable class. You can see right now it's a real simple class, and what we want to do is implement this. So let's look at the header file first. We need to include IOStream since we're going to use an OStream. So we'll do that right away. And there's my class iPrintable. We don't need a constructor, and we want our destructor to be virtual because we're going to have a pure virtual function in here. So we want this to be virtual, and we want the compiler to just generate one for us. We don't need anything special. We won't have raw pointers. We don't have any resources that we have to clean up. Okay, so there's my virtual destructor. Now I want to have another function. This is going to be a pure virtual function, and it's going to be called print. We can call this anything you like, and it expects a pseudo stream. And it's going to be by reference, and I'll call it OS. It's a const virtual function. We don't want it to modify anything, and it's pure, so I'm going to add the =0 at the end. Okay, so now we also need to create a friend function here. And the reason we're creating the friend function is for the syntax, right? Remember, when we're using the insertion operator, we want the stream on the left side and the object that we want to display on the right side. I can't do that with a member function, so I'm going to use a friend function. So we'll say friend, and it's going to return a pseudo stream by reference. What are we overloading? We're overloading the insertion operator. And what are the parameters? Well, the first one is a pseudo stream by reference, again, and I'll call that OS. And the second parameter is a const iPrintable. It's really important that this is an iPrintable, not an account, not anything else. Since an account will be derived from an iPrintable, everything in that hierarchy will also be an iPrintable and conform to this interface. And we can call this object or right-hand side or whatever you like. I'll just call it object. That's it. That's our class. Now what we need to do is we need to implement this function right here, and we'll do that in the iPrintable implementation file right here. We'll get rid of all of this. And I'll include IOStream up here. Perfect. So let's implement this function right here. So what is this function all about? This is the function that really runs everything. We're going to get an iPrintable object here by reference. So we know that that object has already overridden print. It must have, right? Otherwise it wouldn't have compiled. So what we can do here is we can simply call obj.print and that reference to the output stream. Okay. That's pretty cool. And you notice that that matches this guy right here, right? There's print and there's the OStream. Now remember, all the classes in our account class hierarchy are going to override this virtual function. So they'll be printable. It's really as simple as that. So that's it. We're going to put that, we're going to call the objects print, and then we're just going to return OS. And we are done. It's a real simple interface. Perfect. Now let's go to our account. And what are we going to do here? Well, you know what? We're going to leave taking this guy out for last because we really do need to take him out. But for now, let's just leave them in. But what we need to do first is we need to be printable, right? So let's come over here and we will include iPrintable. So now we've got the header file, and we want our accounts to be derived publicly from iPrintable. So what does that tell you now? An account is an iPrintable, right? And iPrintable has this pure virtual function. So that account needs to override that function, and then it becomes printable. All right, so let's come over here. And what's the function? The function is virtual void print. It expects a stdo stream ref. It's const, and I'm overriding it. So you're telling the compiler exactly what's going on here. This guy is a pure virtual function in the iPrintable interface class. You're telling the compiler that you plan to override it. Please check this signature and make sure I get it right. So I'm going to copy this because we need to do that in all our classes in the class hierarchy. So this is account.h. I'm going to go to checkingaccount.h and I'm going to put it right in here. I'm going to go to savingsaccount.h, put it right in here. And finally, I'm going to go to trustaccount.h and put it right in there. Perfect. So now what do we need to do? We actually need to override that function, do what we say we were going to do. So where do we do that? Well, we do that in the CPP file. So here's my account header file. This is the function that we want to override. And what we want to do is we want to say, okay, if I'm an account, this is how I'm going to print myself. If I'm a checking account, this is how I want to print myself. So it's very similar to what we did earlier with this friend function right here. And we can, or I'm just about to get rid of that. We can actually get rid of it now, but I like getting rid of it at the very end. So we'll do that. So here's my account CPP, and let me copy this since that's the one that we need to override in here. So I'm going to come right over here, and you notice this line right here, we're going to reuse that line because that's how we want to print an account. Let's override this function. This is the print function for the account class, and we can get rid of the override. We don't need that here. So what do we do here? Well, let's just set the precision for the output stream. Since we're printing numbers, we'll just print them to 2 decimal places. And what we'll do is we'll also display fixed point. That way it looks nicer as well. Okay. Now what do we want to do here? Well, we want to do what we said we were going to do, right? We want to display the account information. This is how we do it. So we just need to copy that right in here. Now there's only one little thing. This is now a member, right? So we don't need to do account dot. We could just get rid of all that. We did that. We had to do that before because it was a friend. But now we could just access those members directly since we're members. And now we can get rid of this guy. Don't need him anymore. And we can go back to our header file and get rid of the friend. That's it. So now this account class is using that overridden functionality to print itself. So let's do that for the other ones. Well, we'll go to checking account. There it is. So it's good to go here. We'll go to the implementation. And what we'll do is we'll implement this function again. Again, we don't have to say virtual here. We can simply say this is the checking account print method. We can get rid of the override. And then we can write the same code that we wrote before. And finally, we just display how we want to display it. Okay, pretty easy. And now we can get rid of this guy, and we can come to the header file and get rid of our friend. Okay, so you can see the steps involved. I'll go ahead and do the last two. Okay, so I've gone ahead and implemented that print function in all of these classes. So here's the print for account, and you can see it's just printing the name and the balance. Here's the print for a checking account. You can see it's printing out checking account, name, and balance. Here's the print for the savings account, which is printing savings account, the name, the balance, and the interest rate. And finally, for the trust account, it's printing out the name, the balance, the interest rate, and the number of withdrawals on that account. That's it. Before we had that trust account Leo, and it only printed account Leo 10,000. Now we've got dynamic binding, so we should get what we want. So let's give this a run. And that's exactly what happens. That's pretty cool. Now we've got trust account Leo, 10,000, 2%, 2.6% interest rate, and 0 withdrawals. All right, so we're almost done. The last step is to deal with those functions in account util and clean that up. And we had a lot of duplicated code in there. Once we've got that, then challenge is done. Welcome back. We're in the last part of the solution to the challenge for section 16. The only thing we've got left to do is clean up those account util files so that we don't have all this duplicated code. So I'm in the challenge solution project, and this challenge solution project right now is exactly like we left off part 2. So the first thing we want to do is we want to look at these helper functions, and we really want to get rid of all of them except what we absolutely need. And what we absolutely do need is, remember, we're going to come at these things now with base class pointers, so that way we can just use dynamic binding and only have one version of them. So that's what we're going to do. We're going to keep display, deposit, and withdraw, but instead of having a vector of account objects, we're going to have a vector of pointers to account objects. That's my base class pointer. That's what really gives me the power of dynamic polymorphism. So that's what I need to do. All of these down here I can get rid of. I don't need specialized versions of these things, because the whole point of dynamic polymorphism is to let the runtime system figure out which one to use. So this is what we want to reduce it to. I'm going to modify that to say pointer classes, because that's really what we are. And also these include files. Notice that the only thing we really care about is account. So we don't need all these include files. We can get rid of them. We only need the account. Okay, so that's where we're at now. Now the implementation for all of those functions, let's go to that file. So in the account util cpp file, we only want to keep the first 3, and we're going to modify them slightly. The rest of them we can just get rid of, because those are the specialized versions for savings, checking account, and trust account. And those were assuming static binding. So we're not doing static binding anymore, so we don't need them at all. So let's get rid of them. And this is what I've got now. I've got 3 functions: display, deposit, and withdraw. Now we do need to modify them slightly, because our prototypes now expect pointers right here. So that's a pointer. And I'm just going to say account object pointers, because that's really what we are. So let's take a look at this for a second and understand what's going on here. In this case, I've got for const auto, there's my account, right? Now this needs to change a little bit, because I don't really want a reference. I already have a pointer, so I don't need that at all. I just need to get rid of that. And then now, since auto will be a pointer, I just need to dereference the pointer here. That's an object, and that will call the overloaded operator that we just created, the insertion operator. So that's just a really precise change, but that's all we need to do here. The same with deposit. In deposit, we've got account pointers again. So we'll change that, because the vector is a little different. And we don't need the reference here, because we've got a pointer. But what do we do now? Well, we've got to call the deposit method, right? But we have a pointer, so we just need to change the operator to the arrow operator. That's it. And then here with withdraw, last step, again, we've got pointers to accounts in the vector. So what do we do here? Same idea, get rid of the reference, because we've got pointers there, and we call account withdraw from the pointer. We also need to make a couple of changes right here. We need to dereference that pointer to get the account here as well. That will also call the overloaded insertion operator. We need to dereference the pointer here to get the object, and here as well. And that should do it. You can see how much code we got rid of. We got rid of a ton of code, and we've simplified our project. We've simplified our thinking. We can come at these now with base class pointers and let the runtime system figure out which method to bind. All right, so now let's go to our main and take a look. Here's our main. There's a whole bunch of stuff in here. Let's give it a run and see what happens. There we go. There's our run. You can see here, I'm creating a checking account. Again, this is not a pointer, so this is just creating a plain object on the stack. Frank with 5,000, there it is. Now I'm creating a trust account, and I'm creating that account dynamically through a base class pointer. And there's James. No balance, no interest, and no withdrawals. And notice how we were able to print that on the stream, just because we're using our overloaded operators and it's printing it correctly. Now we're creating Larry, Mo, and Curly as 3 pointers to accounts. And again, We're instantiating a checking account, a savings account, and a trust account. And then we're adding those 3 pointers to this vector accounts. Now we're calling display accounts. That's that function that we just updated in the account util. And it's going to display the 3 accounts. And I expect dynamic binding. And that's exactly what happens. You can see right here, checking, savings, and trust. That's pretty cool. And then we deposit $1,000 into each one of those accounts. So you can see right here, I'm depositing $1,000 to checking, to savings, and to trust. Finally, we're withdrawing $2,000. That's this code right here. You can see the last one fails because there's not enough balance. And then finally, we display the accounts one last time, and we see the balances. We clean up our pointers, and we're done. Now we're done. The challenge is over. I hope you had a fun time doing it. If you had trouble with it, don't worry. This was not an easy challenge. This was a very, very challenging exercise. Go back and understand what I did, compare it to what you did. Maybe you just forgot to dereference a pointer and it was as simple as that. For example, if you're in the account util cpp file, and if we forgot to dereference these pointers right here, let's just do the withdraw, and you'll see the difference when I run this again. You'll see the difference when I run this again. Look what prints out here on the withdrawal right there. You see that? That's the pointers. Those are the addresses. So that's a clue, right? I'm printing the pointer. Oh, of course I'm printing the pointer. I don't want to print the pointer. I want to print what it's pointing to. So that's where you have to go back here and now dereference that pointer and get what it's pointing to. And that'll get you exactly what you got. All right, so congratulations on finishing this section. This was a very complex section, and this really takes your C++ knowledge to another level. What we'll do in the next section is we'll talk about smart pointers, and we'll be able to finally get rid of all these raw pointers. In modern C++, we need to understand raw pointers. We must understand raw pointers, but we really want to develop using smart pointers and never ever having to worry about deallocating storage with delete. In this section of the course, we'll learn about the various types of smart pointers in C++ and how to use them. First, we'll understand why we need smart pointers at all. After all, there must be an issue with the way that raw pointers work that motivated the need for smart pointers. So we'll review some of the problems associated with raw pointers. Then we'll see what smart pointers are and understand how they address the issues with raw pointers. One of the most important concepts to understand in this section is that of ownership and RAII, or resource acquisition is initialization. I'll go over this idiom since it's central to understanding not only smart pointers, but resource management in general. Then we'll look at each type of C++ smart pointer and see how they work and how to use them. Ultimately, we want to write code that has no news and no deletes, so all the memory management is handled by C++. If C++ can automatically clean up the heap whenever a pointer is no longer needed, then we'll never leak memory, and we don't have to worry about needing to know when a pointer is no longer needed. That's the idea anyway. Smart pointers aren't perfect, but they can certainly make our code better in most cases. First, we'll learn about the unique pointer, which is exactly what it sounds like. A unique pointer to heap storage that is not shared and the ownership is clear. When you know who owns the pointer, then you know who needs to delete the pointer, or at least C++ knows. Then we'll learn about shared pointers. Shared pointers are pointers that share common heap storage and can be very useful. Then we'll learn about weak pointers and how they can help us avoid a problem associated with shared pointers. Finally, we'll see how we can use custom deleters so that C++ can call a specific version of delete that does exactly what we want. Smart pointers are a very important part of modern C++, and we want to use them whenever we can to help us manage memory. We've already seen during this course that raw pointers are extremely powerful in C++. They allow us to have absolute flexibility with memory management. With this flexibility, however, comes complexity. We must explicitly allocate and deallocate storage for heap dynamic variables as well as manage their lifetimes. And that's where we often see problems. In fact, most defects in programs written in programming languages that provide raw pointers are pointer-related defects. We've already discussed some of these errors in this course. Errors such as uninitialized or wild pointers that could be pointing anywhere in memory, and if you store data to where they're pointing, you could have a potentially catastrophic result. Another error is when we don't deallocate the storage that we previously allocated on the heap. In this case, we'll leak memory. We've also seen dangling pointers. That's where one pointer is pointing to storage that it thinks is valid, but in fact has already been deallocated. Using this invalid memory can lead to all sorts of problems that are sometimes very, very difficult to find and fix. And finally, even if we do everything correctly, our program could throw an exception and the code that releases our allocated memory never execute and we leak memory anyway. We'll talk about exceptions and exception handling in an upcoming section of the course. That's where smart pointers come in. Smart pointers can help us prevent these types of errors. They can help us be more clear about who owns the pointer and when a pointer should be deleted to free up allocated memory. And the good news is that they're pretty intuitive and easy to use. In the next video, we'll see what a smart pointer is and the types of smart pointers provided by C++. So, what are smart pointers? Well, smart pointers are objects. In fact, smart pointers are implemented as C++ template classes which we can instantiate. Smart pointers can only point to heap allocated memory, and they automatically call delete when that's no longer needed. Also, very importantly, smart pointers adhere to RAII principles. As previously mentioned, C++ has several types of smart pointers: unique pointer, shared pointer, weak pointer, and auto pointer. Auto pointer has been deprecated, so you shouldn't use this going forward, and we won't discuss it in this section. So now let's see how we can create a smart pointer. First, we need to include the memory header file since it defines the smart pointer classes and functions we'll use. As previously mentioned, smart pointers are implemented as class templates, very similar to the way that the vector class is implemented, and we create them using a template parameter, much as we did with vectors. Smart pointers are basically wrapper classes that contain and manage a raw pointer. The actual implementation of smart pointers is compiler dependent and is beyond the scope of this section. Once we create a smart pointer, we can use the smart pointer much in the same way as we use the raw pointer. The smart pointer classes provide overloaded dereference and member selection operators, as well as methods to get the raw pointer and more. However, you can't do pointer arithmetic on smart pointers like you can with raw pointers. Finally, we can have custom deleters with smart pointers where we can explicitly define the exact behavior we want when the pointer is about to be destroyed. Now let's see the syntax for declaring a smart pointer. Here's an example of how you might create a smart pointer variable. Of course, you would replace smart pointer with one of the C++ smart pointer types like unique pointer, shared pointer, or weak pointer. In this case, the smart pointer PTR will manage an object of type some class that's been allocated on the heap. Once we create a smart pointer object, we can use the dereference operator, the member selection operator, or any of the other smart pointer member methods. Notice that we don't have to explicitly delete the pointer when we're done with it. In this example, when the pointer goes out of scope, the smart pointer's destructor is called automatically, and it takes care of deallocating any heap storage that was used. That's pretty cool. You can see how powerful smart pointers are. They can prevent memory leaks, make your code easier to read and write and maintain with less errors. Now let's talk about a common idiom or design pattern used in C++ programming. It's called RAII or RAII, and it stands for Resource Acquisition is Initialization, a complicated acronym for a pretty simple concept. First, RAII objects are allocated on the stack. The resource acquisition part is pretty straightforward. It means that RAII objects will acquire some sort of resource. That could be opening a file, allocating memory, acquiring a lock, and so forth. The initialization part is also straightforward. This means that the resource is acquired at object initialization time. So in other words, it happens in the object's constructor. Now at some point we need to relinquish that resource that we acquired, and that happens in the destructor. Here we can close the file, deallocate any allocated memory, release locks, and so forth. Smart pointers are examples of RAII classes, since this is the idiom they follow with regard to memory resources. A simple concept, but a very powerful concept. So let's start our exploration of the C++ smart pointers with the unique pointer in the next video. Let's start by exploring C++11 smart pointers with the unique pointer. The unique pointer is a simple smart pointer that's very efficient, and it can be a drop-in replacement in many cases for your typical pointer use case, where you allocate storage, use it, and then free it in the same block. A unique pointer declaration uses a template parameter, which is the type of the object that the smart pointer will manage on the heap. So this allows us to declare unique pointer objects that point to any type we need. As the name states, unique pointers are unique, so you can't have multiple unique pointers pointing to the same object on the heap. This implies a strong ownership relationship between the pointer and what it points to. Unique pointers can't be copied or assigned, so their copy constructors and copy assignment operators are not available. If you try to copy or assign them, you'll get an error. But unique pointers can be moved, so they're great for placing in standard template library containers such as vectors. And since the ownership is unique, you're guaranteed that when the pointer goes out of scope, the object that it points to will automatically be cleaned up from the heap. That's pretty powerful stuff. So let's see one way we can create a unique pointer. Here you can see that we're declaring P1 to be a unique pointer to an int. We're also initializing it to point to a new int that we create on the heap, and that integer has been initialized to 100. Now, P1 owns that object on the heap. When P1 goes out of scope, the int on the heap will be deallocated. You don't need to call delete with the smart pointer. Now, as far as using the pointer, the syntax is pretty much like using a raw pointer. You can see that if we dereference P1, we get the integer that it points to, in this case 100, and we display it. We can also modify the integer we're pointing to in a similar manner. There's another better way to initialize a unique pointer, and I'll show you that in a little bit. It's also possible to create a raw pointer variable and then initialize a unique pointer variable using that raw pointer. I'm not going to describe that since it's not good practice to do, since you're referring to an object on the heap from a smart pointer and from a raw pointer, not something you typically want. The unique pointer has many methods, but here are some useful ones. In this case, we again have a unique pointer P1 that points to the integer 100 on the heap. The get method returns a pointer to the managed object. You won't often need to use this method, but it can be useful when you're working with libraries that use raw pointers. The reset method sets the pointer to null pointer, and the memory it points to will be released. Also notice that we can check if a pointer is initialized using a simple if statement, as in if P1. In this example, the if block won't execute since we just reset the pointer to null pointer. We can also compare unique pointers using relational operators. Of course, unique pointers as well as other smart pointer types allow us to point to user-defined types. In this example, we're creating a unique pointer that will point to an account object, and we initialize it to point to the Larry account. Notice the syntax is as you would expect. We use account as the template argument in the unique pointer declaration. What this says is that the unique pointer P1 will manage an account object on the heap, and we're creating that account object in the initializer list. Now we can use this pointer as we would use a raw pointer. We can dereference to get the account object, as well as access the account object member methods via the member selection or arrow operator. And again, when P1 goes out of scope, the heap storage associated with the account object is deallocated. As we said, unique pointers can't be copied or assigned. In this example, we create a vector that will contain unique pointers to integers. And we also create a pointer, which is a unique pointer to an int, and it points to the integer on the heap which has been initialized to 100. We can't simply push back that unique pointer to the vector, because that implies a copy of the object, and since unique pointers can't be copied, this will give you a compiler error. However, we can use move semantics to move the pointer. In this case, ptr gives up ownership of the pointer, and it's moved to the vector. The vector now owns the pointer, and ptr will be set to null pointer. When the vector goes out of scope, it will deallocate all its elements and the integer on the heap will be deallocated correctly. Now let's see another better way to initialize unique pointers. Since C++14, we can use the makeUnique function. This function returns a unique pointer of the specified type, and it allows us to pass initialization values into the constructor for the managed object. So in the first example, we declare P1 as a unique pointer to an integer, and use makeUnique to initialize the pointer and create the managed object all in one step. Notice that in this case, we're not using the new keyword. In the second example, P2 is a unique pointer to an account object, and again, we use makeUnique and provide the template argument account, as well as the initialization values, which will be used by the account constructor. Again, in this case, we don't use the new keyword. The last example works the same way, except we're using the auto keyword to let the compiler deduce the type of P3 based on what makeUnique returns. In this case, a unique pointer to a player object. The auto keyword can be very useful here, since it makes the code more readable and more writable. Now let's head over to the IDE and go through some examples of using unique pointers in live code. Okay, so I'm back in the IDE. I'm in the section 17 workspace in the unique pointers project. Now there's a lot of stuff going on here, but let's start it out slow. You can see that in the source tree here, we have our account hierarchy, including our printable interface. So this is the one that's using dynamic polymorphism with that abstract base class account. And we're going to use that in a minute using unique pointers in a vector. But before we get there, let's just play around with a real simple class called test that I wrote right here. It starts on line 12. You can see that I've got a class test, and it's got an integer as an instance variable. It's got a couple of constructors. One just initializes data to 0. That's the noargs constructor. And the other constructor just initializes data to whatever is passed in. I've got a getData method that returns that data and a destructor that just says, hi, I'm a destructor. Real simple. So let's create a test object just to be sure that this works okay. So let's create a test object called T1, and we'll initialize it to 1,000. Now, when we run this, because it's on the stack, we should get the constructor and the destructor being called. And you can see that's exactly what's happening here. Test constructor with 1,000, test destructor with 1,000. Perfect. Now let's do it with a pointer. And what we'll do is we'll just modify this slightly. We'll say prints T1 is a new test, and we'll still use 1,000. Now, obviously, if I don't delete it, I'm going to leak memory. So you can see that's exactly what happened here, right? My test constructor was called, but the destructor was never called. So as we've already learned, what we have to do is we have to say delete T1. And now when we run, we'll have both the constructor and the destructor called, and we're not going to leak any memory. That's exactly what we want. This is using raw pointers. What we want to do now is use different kinds of smart pointers in the next couple of videos. In this video, we're using a unique pointer. So I'm going to comment this code out, and we'll do the same thing using a unique pointer. So the first thing we want to do is we want to declare the unique pointer. Remember, so we're going to say stud unique pointer, and now we need a template parameter. This is the type of class that we want to reference. So in this case, it's test. Later on, we're going to use account, but it can really be any class you want. And what do we want to call our pointer? Let's call it T1. And now we'll use the new way of creating it. We'll say new test and give it the constructor parameter. All right, so what's that going to do? Let's walk through this one. We're creating a variable called T1, which is a unique pointer to a test object. And we're instantiating that test object right here and initializing it to 100. So in this case, we've got that unique pointer pointing to this heap object right here. Notice there's no delete T1 necessary. What's going to happen here is the constructor will be called, and then the destructor will be called automatically, like we've seen. So let's run that. And you can see right here, test constructor for 100, test destructor for 100. We never called delete. We did call new because that's the style that we use to run that one. So now let's use the makeUnique function to do the same thing. So we'll say again, stud, and again, we're going to point to a test object. We'll call this T2, and then we'll simply say equals stud makeUnique. And the first thing we want to do is we want to pass in the template argument, which is test, followed by whatever constructor data we want to pass in. So let's say this is 1,000. Okay, now this syntax might look a little odd, but it really is pretty straightforward. Again, I'm creating a unique pointer to a test. It's called T2, and I'm using the makeUnique function to do it. Well, the makeUnique function can make any kind of unique pointer. So we have to tell it what kind of unique pointer we want, and that's what we're doing right here. Once we do that, the piece here inside the parens, we're here the 1,000, that is the argument that you want to pass into the constructor. That's going to call this constructor right here on line 17. So now what we'll have is we'll have two unique pointers, both on the stack. Both will be constructed, and when they go out of scope, the heap memory that they point to will be destroyed automatically. So we don't have to call delete. And let's run that. And you can see here, test constructor for 100, for 1,000, and then we're destroying both of them. So that's pretty cool. We really had nothing to do. In this case right here on line 28, with the make unique function, we didn't even have to use the new keyword at all. And that's one of the things that you'll hear about modern C++. You don't have to use new, you don't have to use delete. You can just use smart pointers and they handle it all. And for the most part, that's true, but there are some cases where you still have to use new. Okay, so that's a good example right here. Now let's do another example. Suppose that I want to create another unique pointer. And we'll call this one T3. And it will also be to a test. Let's just call it T3, just like that. And it's initialized. Remember, this is an object, so it's going to call a constructor for the unique pointer. It's just not pointing anywhere now. So now what do? Can we say T3 equals T1? Well, I can't do that because I'm not allowed to assign unique pointers. And you can see the error right here, use of the deleted function. It's a long-winded error basically telling you that that operator equal, you kind of see it over here in the error message. It's kind of telling you that that operator equal has been deleted. You don't have access to it. Same thing if you tried to copy construct. It won't let you because you're not allowed to copy or assign unique pointers. But you can move them. So what we can do is we can say std move T1. And what that's going to do, it's going to move the ownership of that test object on the heap from T1 to T3. So now T3 will be referring to it, owning it, and T1 will have a null pointer in it. So we can run this and you can see everything works exactly the same. And we can actually test right here. We could say if not T1, right? So if T1 is not pointing anywhere, in other words, if T1 is a null pointer, then we could just simply say cout and just something like T1 is null pointer. It's the only way that this is possible, right? And we'll end that line here and we should see that display. Oops, let me put that paren back in. And there you go. You can see the output right there. It says T1 is null pointer. That's exactly what we expect, right? Because when you move the ownership from T1 to T3, T3 now owns that object. T1 is now null. It can't own the object because we're not sharing ownership. Now let's create some unique pointers to accounts. And the way we can do that is really, really straightforward again. And let me comment this all out so it doesn't all keep displaying. And what we could say is we could say that we want a unique pointer to an account. Now remember, this is a base class pointer now, which is what we want because we want dynamic polymorphism. And what do we want to call it? Let's call it A1. And we'll use make unique. So now what are we pointing to? We can't say account because account is an abstract base class. So we have to have one of those types of account, one of our concrete classes. So in this case, let's say we want to point to a checking account. And now what are the constructor parameters for a checking account? Well, we can say mo and let's say $5,000. And that should do it. Now at this point, we can use that object however we want, right? But we have to get to the object. So if I want to display that object, I can simply say dereference A1. Remember, A1 is a pointer. So if I dereference A1, I get that checking account object. And it's going to call our overloaded insertion operator that we've defined. So let's see if it does. Let's get rid of that extra paren right here. And let's give this a run. And there you go. Checking account mo $5,000. Pretty cool. Of course, we can use the object in any which way we want. So we could say A1 and we could say deposit another $5,000. And let's display the object again. So you can see we're dereferencing and we're using the arrow operator here as well to access the actual object that we're pointing to. So now we can build and run and you can see that mo was 5,000 and now mo is 10,000. All right, pretty cool. Now let's do a couple of more. Let's create a vector. And what we could do here is we can create a vector. And that vector is going to be a vector of unique pointers. And those unique pointers will point to account objects. Okay, so again, it's a vector of unique pointers. And those unique pointers are going to be referencing account objects. And we could just call this accounts. Simple as that. And now what we can do is we can create some account objects, right? But in this case, we're going to create them on the heap because we've got pointers to them. And we're going to create a savings, a checking, and a trust. And I'll copy that code over just to save a little typing time. Okay, so I copied it over. You can see what I'm doing. I'm adding checking account James with 1,000 balance to the accounts vector. And I'm doing that using the pushback method. And I'm also using make unique because remember, this is a vector of unique pointers. So I'm adding James, Billy, and Bobby, a checking, a savings, and a trust account. So that's pretty easy. Now all we need to do is loop through that vector and display those account objects, right? So let's do that. We'll say for, and we can use a range-based for loop here, and I can say for auto, and let's just call that ACC in accounts, which is my collection. And at this point, all we really need to do is just say std out, right? Dereference ACC, which is my account, and display a new line. Now this won't compile. When I try to compile this, I'm going to get an error right here. And the problem is this is doing copy, right? We're copying each of those unique pointers that's in the account vector, but we're not allowed to copy unique pointers. So we have to do this by reference. And it's even better if we do it by const reference. So now we can run our program and you'll see that we're displaying James, Billy, and Bobby's accounts. Okay, and notice that we didn't do a single delete here, right? Memory's being cleared up automatically for us. If we really wanted to see those destructors called, we can go into our account classes and just change that destructor from the default destructor to actually just put some code in there that says, hi, I'm being destructed or something like that. But they are being called, and that's pretty cool. In the next video, what we'll do is we'll learn about shared pointers. Next, let's look at the shared pointer. The shared pointer is a smart pointer that provides a shared ownership model of the heap object. So like a unique pointer, a shared pointer points to an object on the heap. However, unlike a unique pointer, that heap object may be shared among many shared pointers. So we can have one heap object referenced by multiple shared pointers that manage it. Unlike unique pointers, shared pointers can be copied and assigned. This is exactly how we make them access the same heap object. For efficiency, shared pointers also support move semantics. While unique pointers can be used to allocate arrays of objects on the heap, shared pointers do not support this by default. So you might be thinking, we can have multiple shared pointers all referencing the same heap object. So how do we know when that object needs to be destroyed? And that's a great question. There are different ways that this can be accomplished. The most common technique is to use reference counting. The idea is simple. Every time we instantiate a shared pointer object and have it point or reference to the heap object, we increment a counter. This counter simply has the number of shared pointers referencing that heap object. When the reference count becomes 0, then we know nothing is referring to the heap object and it can be safely destroyed. It's a pretty simple but effective model, but it does introduce some overhead to the process. However, the overhead introduced is in most cases not a big deal compared to the benefits provided by having the system manage these shared objects for us. Let's see how we can declare and use shared pointers. First, we'll see the same technique we used when we created unique pointers, and then we'll see a more efficient technique using the make shared function. Here you can see that we're declaring p1 to be a shared pointer to an integer. We're also initializing it to point to a new integer that we create on the heap, and that integer has been initialized to 100. Now, p1 owns the object on the heap. When p1 goes out of scope, the int on the heap will be deallocated. That is, unless other shared pointers are referencing it. You don't need to call delete with a shared pointer. Now, as far as using the shared pointer, the syntax is pretty much like a raw pointer or a unique pointer. You can see that if we dereference p1, we get the integer that it points to, in this case 100, and we display it. We can also modify the integer we're pointing to in a similar manner. In this case, since we only have one shared pointer referencing the integer on the heap, when p1 goes out of scope, the integer will be deallocated from the heap. Before we see how we can create other shared pointers and have them reference the same heap object, let's look at a very useful method in the shared pointer class called useCount. The useCount method returns the number of shared pointer objects that are currently referring to the heap object. In this example, we'll have two shared pointers, p1 and p2, that both reference the same heap object. So first we declare p1 as a shared pointer that will manage an integer on the heap, and we initialize that integer to 100. Now we call the useCount method on p1 and we see that it displays 1. That's what we expected since p1 is the only shared pointer referencing the integer on the heap. Now we create another shared pointer p2. And we use the copy constructor to initialize it so that it refers to the same object as p1. Now we call the useCount on P1 and we display 2, since both P1 and P2 are now referencing that same integer. But notice that if we call useCount on P2, we'll also see a 2, which makes perfect sense. Now suppose that I call reset on P1. Recall that with a unique pointer, this destroyed the heap object and set the unique pointer to null. However, with shared pointers, this decrements the useCount by 1 and sets P1 to null. Now the useCount for P1 is 0 and the useCount for P2 is 1. So just because we reset P1 doesn't mean that we deallocate the integer on the heap. We can't in this case because P2 is still referring to it. Finally, when P2 goes out of scope, the integer on the heap is deallocated since it's no longer being referenced. So you can see that reference counting is pretty simple in concept. Of course, shared pointers also allow us to point to user-defined types. In this example, we're creating a shared pointer that will point to an account object, and we initialize it to point to the Larry account. We declare account as the template argument in the shared pointer declaration. What this says is that the shared pointer P1 will manage an account object on the heap, and we're creating that account object in the initializer list for P1. Now we can use this pointer as we would a raw pointer. We can dereference it to get the account object, as well as access the account object member methods via the member selection or arrow operator. And again, when P1 goes out of scope, the heap storage associated with the account object is deallocated. As you can see, this code looks exactly the same as the code that we used with the unique pointer. Unlike unique pointers, shared pointers can be copied, assigned, and moved. In this example, we create a vector that will contain shared pointers to integers. And we also create PTR, which is a shared pointer to an integer, and it points to an integer on the heap which has been initialized to 100. We can now push back that shared pointer to the vector. Remember, we couldn't do this with unique pointer since they don't allow copying. But we can do it with shared pointers. Also notice that if we display the use count for pointer, we'll see a 2. This is because that integer on the heap is being referenced from pointer as well as from the shared pointer in the vector. Now when the vector and pointer both go out of scope, we're sure that the last one referring to that integer on the heap will clean it up. There's no need to call delete or to figure out when and from where to call delete. This is a huge deal and makes writing this kind of code so much easier and less error prone. Now let's see a better way to initialize shared pointers. The makeUnique function was introduced in C++14, but the makeShared function has been around since C++11. The makeShared function returns a shared pointer of the specified type, and it allows us to pass initialization values into the constructor for the managed object. This is the preferred way to create shared pointers. Not only do we not have to use the new keyword, but the compiler will generate much more efficient code, since remember, the compiler has to generate a data structure that holds information about the reference count, the raw pointer, the actual heap object, and other data as well. So this creates all of this in one shot when the pointer is initialized. In this example, we create 3 shared pointers, P1, P2, and P3. P1 is created using makeShared, and we reference an integer on the heap and we initialize it to 100. Now we can create P2 as a shared pointer to an int and use its copy constructor to initialize it to P1. P1 and P2 refer to the same integer on the heap, and its use count will be 2. The third pointer, P3, is initialized as empty, so it doesn't point to any shared object yet. But it is initialized, it's null, so there's no chance that we can have an uninitialized or a wild pointer when we use smart pointers. Then we assign P1 to P3. Now P1 also refers to the shared integer, and our use count increases to 3. All 3 pointers now go out of scope. Which shared pointer is responsible for cleaning up the heap storage? Well, it's the last one that references it. In this case, it will be P1, since P2 and P3 will be destroyed before P1. But the point is that you don't have to worry about it. So now let's head over to the IDE and we'll see some examples of using shared pointers in live code. Okay, so I'm back in the IDE. I'm in the section 17 workspace in the shared pointers project. This project has 3 sections. The first section is all about using a shared pointer to an integer and sharing pointers so that we can see these reference counts moving up and down. The second section, we're going to create test objects now, and then the third section we'll use vectors. So let's start with this section first, and I want to walk through it with the debugger so you can actually see what's going on. So I'm going to debug this program, Okay, so we're going to start right here on line 31. You can see what we're doing here. We're creating P1 as a shared pointer to an integer, and we're setting that integer to 100. Now, if I step through that, you can see P1 over here. I'll refresh, and you can see that P1 has a reference count of 1. You can see it right there. I know it's kind of small, but I couldn't make this font any bigger on this window here. So there's the count of 1. So this tells you that P1 is pointing to that shared integer, right? And that's the only thing pointing to that shared integer right now. So on line 32, if I display the use count point for that shared pointer, I am going to get 1. So I'll execute that, and you can see up here on the display the use count is 1, which is actually the same thing we're seeing right in here. Okay, so now on line 34, what we're doing is we're creating P2 in terms of P1. So that's my copy constructor. Now we're sharing ownership. Remember, this is one of the things that we could not do with unique pointers. So in this case, let me execute that line, and you can see now that P1 and P2 are both referring to that same storage. So when I refresh here, you'll see that they both have a reference count of 2 right there. Okay, so again, P1 and P2 are managing that same area in memory. They have co-ownership. So at this point, when I display the use count, we'll see a 2. Now on line 37, I'm resetting P1. What is that going to do? Well, it's going to set P1 to point nowhere. So we're going to have that set to null pointer. And P2's reference count will go down by 1 because now P2 is the only shared pointer that owns that memory. So let's execute that line. And let's refresh over here. And you can see now that P1 is a null pointer basically. And P2, its reference count went down to 1. So if we display these last two statements, we'll see that P1's use count is 0 and P2's use count is 1. And the program is complete now. Okay, so now let's do part 2. Okay, so now let's execute the second section of this project. You can see the second section starts here on line 41. I've commented out the section 1 that we just ran. So let me walk through this with the debugger so we can see what's going on again with these reference counts. Okay, so we're here on line 42, and we'll step through that. All that's doing is creating PTR as a variable. It's a shared pointer to a test object, and we're using makeShared this time to create that test object. So I'll step through that, and you can see that right now when I refresh my local variables, PTR has a reference count of 1. So we've got 1 reference to that shared test object on the heap. Now we're going to call this function, and we're going to pass PTR into it. This function expects a shared pointer to a test, and it expects it by value. So what we expect is for it to make a copy of that shared pointer. Remember, we're making a copy of the shared pointer object, not of the test object on the heap. It's important to understand the difference there. So let's walk through this. Now we're in the function. You can see we're right up here on line 23 at the top of the screen. And right now we've made a copy. So if you look at P is a shared pointer to that same test object. So we expect P's use count to be 2 because we just created a copy. So let's take a look at that, and you can see the use count is 2. So now when P goes out of scope in this function, what happens is that the reference count again is reduced. So let's take a look at that. Now we're back here, right back to where we were. We're on line 44. And if I refresh, you can see that PTR now is back down to 1. Right? So we temporarily increased that reference count while we were in that function because we just made a copy of something else that's using that same resource. So now we'll print out the use count for PTR, which we expect to be 1, and that's exactly what it displays. Now notice what happens. I've created a block here, and then there's another block here. This just establishes scope so that we can see these inner shared pointers going in and out of scope. So in this case, we've got PTR1, and we're creating PTR1 based on PTR. So now we've got PTR and PTR1 both pointing to that shared resource. So let me execute that line. And what we expect now is the use count to be 2. And I'll refresh here, and you can see that the count right there is 2 for both of them, which is exactly what we expect. And we'll display 2 now, right over here on the output. What happens now is we create another block. So we're creating PTR2. Also referring to that same test object. So now we've got these 3 pointers, right? These 3 shared pointer objects, all referring to the same managed object on the heap. So if I execute this line here on line 49, what we have is we've got PTR, PTR1, and PTR2, all with a reference count of 3, which is exactly as we expect. And we can display that reference count. You can see the 3 right here. Now what we'll do is we'll reset pointer. Right? So this pointer right here will be nulled out, which means that that will become null, and then the reference count for the other two pointers, PTR1 and PTR2, will go down to 2, since now there's one less shared pointer. So let's execute that line and refresh, and you can see that now PTR is null. PTR1 and PTR2 have a reference count of 2, just as we expect. All right, so now PTR is going to go out of scope right now, and it just did. So now we're going to print out the use count for PTR in this case, which will be 0, right? Because we reset it. Okay, so now let's walk through this one more time, and we're right here right now. And let's step through this one more time. We're on this last statement, and what's the use count for PTR? Well, let's refresh here. You can see that PTR's use count is now 0, right? No, it's not referring to any managed object. So that's it. That's part 2. We'll do next is part 3, where we'll create a couple of shared pointers. Well, actually, we'll create 3 shared pointers to account objects, and then we'll put them on a vector and print out the vector. Okay, so let's wrap up this video by going over the 3rd section of the shared pointers project. In this case, you can see we're starting on line 58. And what we're doing is we're creating 3 account pointers, and these are shared pointers to account objects. We're using the same account framework that we've been using all along. This is the one that's using dynamic polymorphism. So we're coming at this with a base class pointer right here. And we're using std_make_shared here. We're creating a trust account Larry, we're creating a checking account Mo, and we're creating a savings account Curly. So there you go. At this point, we've created 3 objects. Then what we'll do is we'll take those 3 shared pointers and we'll put them in a vector. So notice this vector declaration here. A vector is a vector of shared pointers to account objects, and we'll call it accounts. And we'll simply push back ACC 1, 2, and 3. Remember, we're not pushing account objects. We're pushing shared pointer objects that point to account objects. And then we'll just loop through that vector and display them. Okay, so let's step through the debugger with this example and see exactly what's happening. Okay, so here we are. We're on line 59. What we want to do is we want to create those 3 shared pointers. So let's do that. We'll step through the first one, the second one, and the third one. I'll refresh my screen here, and you can see that account 1 is a shared pointer with a reference count of 1. Account 2 is the same, and account 3 is the same. So each one of them is pointing to its own managed object, right? In one case, it's a trust account, a checking account, and a savings account. Now what we're going to do is we're going to instantiate that vector of shared pointers to accounts. And we'll do that right now. I'll step through that one line right now. And there it is. There's nothing in there right now. Now what we want to do is we want to add those 3 shared pointers to the vector. Remember, ACC 1, 2, and 3 are shared pointers. They're not accounts. They're not raw pointers. They're shared pointers to accounts. So our vector holds shared pointers to accounts. That's how we declared it. So what's interesting here is, remember, these guys right now, all ACC 1, 2, and 3, all have a reference count of 1. But when we add them to the vector is going to make a copy. So now we have shared ownership. ACC 1 shares the ownership with that trust account with accounts, which has a vector that has a copy of that. Okay, so let's walk through this. I'll step 3 times through this code here, and we've just added all 3 accounts. I'll refresh, and you can see the actual accounts right here. You can see that it's got 3 entries, and notice the reference count for them, 2. If I look at ACC 1, 2, and 3, you can see they also have a reference count of 2 because we made copies. So now we've got shared ownership. Again, ACC 1, 2, and 3 have shared ownership to that trust account, checking account, and savings account, and so does the vector. Now let's loop through this and display them. So what we're going to do is we're going to use a range-based for loop here, and we're going to iterate over the accounts object, which is that vector. And we're just using const auto here, but remember, the vector is a vector of shared pointers, so this ACC variable is going to be a shared pointer. And if we want to display the account, we just dereference the pointer to get to the account. So we expect this to print out the trust account, the checking account, and the savings account, and the use count as we go. Now the use count should be 2. We're using a reference to a base class, so the dynamic polymorphism will be just fine. So let's walk through this, and you'll see that we've got right here, you can see up here, trust account Larry, and let's display the reference count for that, which we expect to be 2, right? Because ACC1 is managing it as well as the vector. Then we'll execute it again. We'll see the second object is the checking account. Use count is also 2. And then the last one is the savings account for Curly, and the use count is 2. Now, what happens when the vector goes out of scope? What happens when these pointers go out of scope? Well, the vector is going to go out of scope first, so it's going to be destroyed. But the objects, that the trust account, checking account, and savings account objects on the heap won't be destroyed yet. What will happen is that those shared pointers in the vector will be destroyed, and then the reference counts for those three objects will go down by 1. Then when ACC 3, 2, and 1 are destroyed, that's when the heap storage will be dynamically deallocated. And that's it. That's the program. It's done. You can walk through this and use the debugger. You can see the big difference here between using unique pointers and shared pointers. When we had a vector of unique pointers, that vector exclusively owned those resources. Here we're sharing those resources, and the use cases are different, obviously. It all depends on what you're trying to accomplish. In this video, we'll learn about the weak pointer. The weak pointer provides a non-owning or weak reference to a shared managed object. Like a shared pointer, a weak pointer points to an object on the heap, but unlike a shared pointer, it doesn't participate in the owning relationship. Weak pointers are always created from shared pointers. And since weak pointers are non-owning references, they do not affect the reference count for the managed object. So weak pointers don't affect the lifetime of the objects they're pointing to. There are a few use cases for the weak pointer. One is to prevent strong reference cycles between two objects. We'll see this visually in the next slide. Another use case is when we have a pointer that we use to temporarily reference another object. Something like an iterator pointer that traverses a list of nodes. It really doesn't own them, just visits them temporarily. Let's see the problem with strong circular references. Sometimes when we design programs, we may have two classes where each class refers to the other. This implies a one-to-one relationship between the classes, and this will be reflected in the class objects when we instantiate them. In this case, we have two objects, A and B, which were instantiated from two different classes. Notice that A has a shared pointer to B, and B has a shared pointer to A. Now we have a bit of a chicken and egg problem. When they go out of scope, they'll be destroyed from the stack, but their shared resources on the heap will not be destroyed and will leak memory. A keeps B alive and B keeps A alive. This is exactly where the weak pointer comes in. Let's see. Now we need to decide who owns who. Let's say that A owns B. Then we replace the shared pointer in B with a weak pointer. And now everything works as expected and we don't leak memory. In the next video, we'll complete this section with a brief introduction to custom deleters for smart pointers. But first, let's head over to the IDE and see this example in live code. Okay, so I'm back in the IDE. I'm in the section 17 workspace in the weak pointers project. And what we'll do here is we'll do that same example that we did visually in the slides, where I've got an A referencing a B and a B referencing an A, and we've got that strong circular reference that we can't break. So let's take a look at how we do this. First of all, you can see that I've got a class A declared right here on line 10 to 17, and the class A has a shared pointer to a B. Now, since we haven't seen the B yet, we need to put this forward declaration in here. I'm not sure if we've done that in class before or not, but since the compiler needs to know about a B, we're just simply saying, hey, you know what, compiler, I've got a class B, I'll declare it later, just assume it's here. It's similar to a function prototype in a sense that just tells the compiler, don't worry about it, you'll see this later. So in this case, again, the class A has a shared pointer to a B, and here's my set method that just sets that pointer. It's got a real simple constructor in this structure that just simply display, when they're called, so we can see them actually being called. And then my class B is defined down here. And the class B has a shared pointer to an A. So there's that relationship between the two, right? So an A owns a B and a B owns an A. So that's the problem that we have. And here's my set method that sets that A pointer. And again, my constructor. So really, really simple. Let's take a look at the main. And you can see the main here on line 31. I create that A shared pointer using make shared. And on line 32, I create the B shared pointer using make shared. Then right here, I'm going to say set the B part of A to B and set the A part of B to A. That's establishing that circular reference. So what happens here is, here's my A, here's my B. Remember, these are shared pointers. So we basically got a pointer here and a pointer here. Remember, it's a shared pointer, so this is just an object. And this guy is pointing to an A object on the heap. This guy's pointing to a B object on the heap. And what we just did here is we did this. He points to that one, and this guy points to that one. Okay, so you can see the problem. Now this guy has a reference count of 1 or use count of 1. This guy has a use count of 1. So what happens when A and B go out of scope? Well, A goes out of scope and it tries to destroy this piece here, right? But it notices that something else is referencing it. So it's not 0. So it's not going to destroy it. Same thing with B. So what ends up happening is what actually gets destroyed is A and B that are on the stack, right? The shared pointers, but not the area on the heap. And there's your memory leak, right? So all this is going to leak. And we've got no way to get to it. So that's the problem. And the problem is because of this implied shared ownership. So the fix is really simple. The fix is using a weak pointer. So we determine who owns what. Let's just assume that we're going to change this guy right here. And actually, let me run this so you can actually see the leak. Let me build and run. And there's the run. You can see I constructed an A, I constructed a B, but the destructors never got called because we leaked the memory. Right, so what we want is we want A's constructor, B's constructor, then we want obviously the destructors for both of them being called. Okay, so let's do that. So what we can do is, you can see the comment right here, make it weak to break that strong circular reference, and that's exactly what we're going to do. We're going to come right here and we're going to make this shared pointer a weak pointer. That won't affect the reference count. So now when we run this, you can see the A constructor, the B constructor, then the A and the B destructors being called. Now we're no longer leaking memory. So this is a real common use case for the weak pointer. And this kind of stuff happens more often than you would think when you've got very complex data structures and graphs and you're traversing and doing all kinds of manipulation. It's very possible you can end up with strong circular references like these. And the weak pointer is the solution. In this last section of the course, we'll talk about custom deleters for smart pointers. This isn't something you're likely to see very often, but I wanted to cover it for completeness since they are a feature that C++ smart pointers support. Sometimes when we destroy a smart pointer, we need more than to just destroy the object on the heap. Sometimes when we use pointers to C structures from C frameworks, we have to provide a specialized way of destroying them, since in many cases they don't have destructors. As I said, these are special use cases that you won't run into very often. But if you do, the C++ smart pointers allow you to provide custom deleters that will be called when the smart pointer is destroyed. If you use custom deleters, you can't use make shared or make unique when you create your smart pointer objects, since we need to provide our custom deleter and these functions don't support that. The idea is that if you need a specialized way to delete your objects, you probably need a specialized way to create them too. There are lots of ways to provide custom deleters. I'll show you 2 ways in these slides, first using a function and then using a lambda. In the case of a function, we write our deleter function that will be called automatically when the smart pointer will be deleted. This function will be provided with a raw pointer to the managed object that the smart pointer is referencing. Then in this function, you do whatever you need to do to relinquish your resources. In this example, I'm simply deleting the raw pointer. That's it. So now when you declare your smart pointer, you provide your deleter function. In this case, I'm declaring ptr as a shared pointer to some class. And in the initializer, I'm creating the managed object using new, but then I'm also passing in the name of my custom deleter function. That's it. Now when the pointer is destroyed, it will call my deleter. Let's see a real code example using the test class that we've been using in this section. So here we're creating a deleter function that will be passed in a raw pointer. In this case, it's a raw pointer to a test object. And that pointer is the pointer that the smart pointer is managing. In this function, I'm simply displaying in my custom deleter, and then I'm deleting the raw pointer that was passed to me. That's it. Now when I create the smart pointer object, in this case, ptr as a shared pointer, I pass in my deleter in the initialization list. It's as simple as that. This will also work for unique pointers. Now let's see how this works using a lambda expression. We haven't seen lambda expressions in this course since they're more of an intermediate C++ topic. If there's interest in learning more about lambda expressions, please let me know and I'll add a section to the course. In a nutshell, a lambda is an anonymous function. That is, a function that has no name and can be defined inline right where you expect to use it. There's a lot more to lambdas, but you can see in this example that the function name parameter has been replaced with a code block that looks very similar to what we originally wrote in the myDeleter function. The syntax might look a little odd, but now this code will execute whenever the pointer object is destroyed. That's pretty cool. We define right where we will use it and not need to write another function and have to worry about it. Well, that completes the section on smart pointers. I hope you can see how powerful smart pointers are. There are many opinions as to what types of smart pointers you should use when, and the answer is usually it depends. I would encourage you to use unique pointers as often as you can, since they're simple, efficient, and in most cases, they're drop-ins for many of the common pointer use cases. Then use shared pointers when you have more complex object management semantics involving shared ownership. In the next video, we'll do a simple challenge that uses a unique pointer to a vector of shared pointers. It should be fun. Okay, so I'm back in the IDE. I'm in the section 17 workspace in the custom deleters project. And in this project, what we'll do is we'll write a couple of different ways to have our custom deleters being called. And it's really straightforward. Let's do the function one first. We've got the same test class that we've been using throughout this section. You've seen it before, so it should be pretty easy to understand what's going on there. And now what we want to do is we want to create our own deleter that'll be called when our objects are deleted. This is it right here. This name can be anything you like. I just called it myDeleter. It has to return void. And what's being passed into here is the raw pointer that's being managed. So in other words, if I've got a shared pointer to a test object on the heap, we're going to get a pointer to that test, and it's going to be the raw pointer. If this was an account, we'd get a pointer to an account object. Again, a raw pointer. So that's the raw pointer that's being wrapped by that shared pointer. Okay, so what are we doing here? Well, this is going to be called with that pointer. We can do whatever we like. In this case, I'm just going to say using my custom function deleter, and then I'm actually going to delete that pointer. Right? I mean, the whole point is for me to delete that storage. Now, this gets much more complicated when you've got raw pointers to C structures that are used in C frameworks. They don't have destructors. So you've really got to manage that memory yourself, and this is a nice way to do it, and still be able to use unique pointers and shared pointers and so forth. So what do we do now? Well, now we can create our pointers. It's called ptr1, and it's a shared pointer to a test object. Remember, the test object's on the heap. We have to use new here to do this. We can't use make shared. And what we do is we pass in the regular information that we're used to, right, to create that object on the heap. And then we pass in the name of our deleter. In this case, it's myDeleter. You can see it's the same name. You don't have to put address of in front. It doesn't hurt if you do, but it's not necessary. The name of a function already defaults to the location of the function. So in this case, what's going to happen behind the scenes is that when this pointer is deleted and it has to clean up the memory, it's going to call this function to do it. And you can have complete control of how you do it. So that's the function method. The second way is using a lambda expression. And what you'll see here is you can see our output statement and our delete. And you can see here our output statement on our delete. The only difference is that it's being wrapped up in this construct right here. And this is called a lambda expression, which creates a closure object. And what's going to happen is when it's time to delete this, rather than call a function, this code right in here executes. So this is real nice because you can, write your code exactly where it's going to be used, not somewhere else. Obviously, this function could be anywhere. But this is all right here. It's real nice. So when you're reading this, you can see exactly what's going to happen, right? I mean, it's right there, rather than having to find a function to see what it does. And that's it. There's two different ways to do it. If we run this now, and actually, you know what? Let me change this to 1,000 here so we can see the difference. So what's going to happen here is, and I notice I've created this block right here. This is just an artificial scope here so that we can see that this PTR1 will be deleted right here, right? It'll be destroyed, and PTR2 will be destroyed right here. So we expect PTR1 to live inside this block and PTR2 inside this block. That way we can really see them, and we can really see these deleters being called. So let's execute this, and we'll build and run. And you can see right here, let me move this over here just a little bit. This is this block right here. You can see that we're constructing that test object with 100, and then we're using our custom function deleter, right? You can see that that output statement is displaying. We're deleting the pointer, and then we're calling the destructor. Same thing here. We're calling the test constructor with 1,000, and then we're using our custom lambda deleter, which is this line right here, and we're destroying our pointer as well there. And then we're calling the test destructor. So there you go. Real simple example of using custom deleters. You don't often need these, but it's nice to know that they're there, and they're pretty easy to use actually. Welcome to the Section 17 challenge. I'm in the Section 17 workspace, and you'll notice that I've got two challenge projects here. The first one is challenge-1, and that's the harness that I'm going to give you. That's basically you have to write 3 functions for this challenge, and I'm giving you the function prototypes, and you have to write the functions. There's also the challenge solution-1. That's my solution to this challenge, and we'll do that in the next video. Also notice that there is a challenge-1, so that implies there's going to be a challenge-2. I'm planning to put another challenge in this section in which we'll implement a doubly linked list using raw pointers, and we'll replace the raw pointers with smart pointers so that you can really play around with it. The best way to understand pointers or even smart pointers is just to play with them, to create examples, to try them out, make mistakes, understand why this doesn't work. You'll try to copy a unique pointer and it won't work, and you'll go, oh yeah, of course you can't copy unique pointers. So this is the idea, is just to play with this and get more experience using it. So that's what this challenge is all about. In this challenge, we're going to create a real simple main that's going to instantiate a vec pointer. And I'll show you this vec pointer right here, and then I'll talk about the challenge in more detail in a sec. But let's just get an overview of what's going on here. You can see here's my main, and these are the 3 function prototypes, and you'll have to implement those 3 functions. But let's talk about the main first. Main has vec pointer. Okay, so here's vec pointer. And what does vec pointer look like? Well, vec pointer is on the stack. And it is, and this may look a little complicated, this declaration here, but break it down into pieces and it'll make a lot of sense. Vec pointer is a unique pointer. Okay, so it's an object, and this is on the stack here. So what is a unique pointer? We know what a unique pointer is, right? A unique pointer is basically an object that manages a raw pointer. And in this case, it's a unique pointer. So I'm pointing somewhere. Where am I pointing? Well, I'm pointing to a vector. All right, so here's my vector. Remember, a vector can have multiple elements. So here's my vector. Now notice everything over on this side is on the heap, right? All of this stuff is going to be on the heap. The only thing that's on the stack is that vec pointer right here. So now we've got a vector. Okay, I know what that is. Well, what does the vector contain? Well, the vector elements are shared pointers. So each one of these guys is going to be a shared pointer, right? So I'll just put SP here so you'll know what I'm talking about. So what's a shared pointer? Well, a shared pointer is an object. And the shared pointer in this case manages a test object. And we've got a test class right up here. Same one we've been using in this section. So this guy now has a test object that it's managing. And this guy is managing a test object, and so forth. So this looks pretty complicated, and it's not that complicated when you really break it down like that. Again, all we've got on the stack is a vec pointer. That points to a vector on the heap. That vector contains shared pointers, and those shared pointers refer to test objects. Okay, so how are we going to do this? Well, we're going to do this really easily because the vector and the test class, the unique pointer class, and the shared pointer classes really do most of the work for us. And we're going to do this with no news and no deletes. Okay, we're not going to use new, we're not going to use delete. We're going to use make shared, make unique, and let the destructors be called automatically when the reference counts go down to 0 or when the unique pointer goes out of scope. So this is going to make our memory management really, really simple. We're not going to work with raw pointers at all. All right, so that's the big picture. So now what are we doing? Let's walk through this main, and I'm going to clear this out real quick, and let's walk through our main one step at a time here. So here we've got a vec pointer. That's just going to create that object on the stack. It is not creating that vector on the heap. We need to do that ourselves. So again, that vec pointer is just that simple unique pointer object on the stack. In order to create that vector that we're pointing to, we need to call this function make. And that's this function right up here. There's the function prototype right here. You can see make right over here. Again, this looks really complicated, but it's pretty straightforward again. What are we returning from make? Well, we're returning a unique pointer to a vector of shared pointers that manage test objects, right? So inside make is where we're going to use make unique. We're going to actually create that unique pointer and make it point to that vector. Okay, once we've got that, we're going to ask the user, how many data points do you want to enter? And let's say they type in 3. We'll read that into num, and then we'll call fill. And look what we're passing into fill. We're dereferencing vec pointer. Well, what is vec pointer? Vec pointer is a unique pointer to that vector. So when I dereference vec pointer, I get the vector that it's pointing to. So I'm calling fill with the vector and the number of elements. And you'll notice that here's fill right here. And all fill is going to do is it's going to loop as many times as the user wanted, in this case 3, and it's going to say, so what's the first integer you want to enter? You'll type in 10. What's the second one? 20. What's the third one? 30. And for each one of those integers that the user enters, we're going to create a shared pointer to one of those test objects with that integer they entered right here, and we're going to put that on the vector using pushback. That's it. Now we'll call display. Notice again we're dereferencing vec pointer. That gives me the vector, and display is right here on line 69. And all we're doing in display is we're just iterating through that vector of shared pointers and displaying whatever data those test objects hold. Sounds complicated. It's not so complicated. You just need to break it down into little pieces and take them one step at a time. Let me run this for you so that you can see what the output looks like. And I'll run it based on my solution here. And let's build and run. So the first thing it says is, I'm going to just slide this over here so that you can see the actual code next to it. So here's my main right here. How many data points do you want to enter? Let's say I want to enter 5 data points. Enter data point 1. Now, we're in that fill method. The fill method is the one that's going to loop 5 times in this case. Each time asking me for what data I want, it's going to make shared, right? And create that shared pointer to that test object that has whatever I type in. So let's say I want to type 10. Now you'll notice that over here on the right, we've got test constructor. That's just a little debug statement that I put in there to help you out. It's being indented so that you can see it. So what's happening here is we've just created a test object with a 10, which is what the user typed in. So let's create another one, 20. Remember, we're going to get 5 of these. So we'll do 30, 40, and 50. So at this point, our fill is done. Now we're going to display all those elements in that vector. So when I press enter now, that will be called display, and it'll display everything. There we go. It says display vector data, 10, 20, 30, 40, 50. Now look what happens. Test destructor, 10, 20, 30, 40, 50. Again, I've got a little simple print statement in the destructor for the test class. And you can see that these objects are being cleaned up off the heap, which is really cool. So no deletes necessary because we're using smart pointers. And this is the output that you should get from this main once you implement those functions. So there you go. It's up to you now. What you need to do again is implement make, fill, and display. And if you scroll up just a little bit here, and it's also in the description text, it tells you a little bit more about what those functions should do. So again, the function name make, it creates and returns a unique pointer to a vector of shared pointers to test objects. The fill function expects a vector of shared pointers to test objects and the integer for however many numbers the user wants to enter. And it prompts the user and creates those shared pointers as it goes. And then the display just displays everything in there. And if you look at the function prototypes that I provided, and you can change these to whatever you like. If you want to try it without the ref, with the ref, const, non-const, try it out. Change them around and see what happens. But these are the function prototypes I'm giving you. You can see that make expects nothing and returns a unique pointer. In this case, fill expects a ref to a vector. Now this one has to be a ref, right? It can't be by value, otherwise you won't add anything to the vector. And it can't be const because we actually need to change that vector. But display should expect a ref and it should be const. So in this case, I want to be efficient and not copy that vector. And at the same time, I don't want to change it accidentally. So there's my const. All right, that's it. Good luck. Have fun. Play around. Change these prototypes if you like. Use the debugger. I'm sure that'll help you a little bit when you're trying to learn this stuff. So those are the 3. You shouldn't have to change the main, and you should get the same output as I did. We'll come back to the next video, and we'll do the challenge solution. And you'll see that it's actually pretty straightforward. It's real nice to be able to have C++ manage all this stuff for us using smart pointers. Welcome back to the Challenge 1 solution for section 17. What I'll do now is I'll write these 3 functions and we'll do it together and we'll explain it as we go. The first one is the make function. That's the one that creates that unique pointer. And the way we do that is we use make unique. Now, obviously, we need to return it. So we'll say return std make unique. And what are we making? Well, we're making a vector. And the syntax is going to look kind of weird here, but we just have to deal with it because that's just the way it is. And it's not that hard once you break things up together, as I said. So we're returning a unique pointer to a vector, right? And that vector is of std shared pointers to test objects. And we'll have 3 greater than signs here to close that up. And then what we need to do is we need to call the constructor for that vector. That's it. That's all we really need to do here. Now we'll clean this up in a second and we'll make this even better than it is here. But that's one liner. That's all it's doing. We have to make that unique pointer. Remember, down here on line 89, we've got a constructed unique pointer, right? But it's not pointing anywhere yet. That's what we're doing here. Now we're actually creating that vector. All right, so now there's the fill. How do we do the fill? Well, the fill expects that vector. So it's pretty straightforward. I just need to read that integer from the user for each iteration, right? So we need a temporary variable here. Let's just call that temp. That's what we're going to read into. And now we're going to loop. How many times are we going to loop? We're going to loop num times, however many numbers the user wants to enter. So we'll say for int I equals 1, we'll start at 1 and we'll go I less than or equal to num. And we'll increment I each time. So that's my loop. We're going to use a for loop here because we know exactly how many times we need to loop. We need to loop num times. So what do we do here? Let's prompt the user. So we'll say std cout. And we'll ask the user to enter data point. And we'll just give them a little number here so that's easier for them to understand which one they're putting in. And we'll just surround that in brackets like that. That's it. And then what we'll do is we'll read from cin into temp. So we're going to do that 3 times, 5 times, 10 times, however many times they want. Now what we can do is we can create our shared pointer. We know the data that's going to be in the test object, right? That's this guy right here, temp. We just read it. So we can do this in a couple of different ways. Let's do it 2 ways. Let's do it in 2 steps, and then we'll do it in 1 step. So what we need to do is we need to have a variable here, and it's going to be a shared pointer to a temp object. So my template parameter is temp. And what do we call this? Let's just call it PTR. This variable name could be anything. And we're going to use std make shared. Again, test. And what are we going to construct it with? Well, we're going to construct it with data or temp, whatever the user entered. Now that we've got that pointer, remember we have a vector of shared pointers. We just created the shared pointer. So all we need to do now is just say vec.pushback, and we're going to push back the pointer. That's it. We're done. So that's exactly what's going on here. And we're going to loop that many times, create for each iteration, create that shared pointer, instantiate that test object, and that's it. Now, rather than do it in 2 steps like this, let's just do it in 1 step because it's much more efficient to use move semantics. So let's just say vec.pushback. And right in here, we'll just say std make shared. Right, so that's going to create that R value, and the R value ref will be moved over. So test and temp. All right, so again, 1 simple statement. And now the last thing we need to do is display this vector. So I've already got the header information here with the 2 couts. And what do we do here? Well, let's just use a real simple range-based for loop. So we'll say for const auto, we'll use a ref, we'll call it pointer, and we're going to iterate through that vector. And for each iteration, all I want to do is just say std cout, and we want to print the pointer's data, right? So we need to dereference that pointer and get its data. Something like that, and then an end line. And that should do it. Let's compile this. And there's our run. How many points do you want to enter? Let's say I want to enter 10 data points. And there'll be, let's say 2, 4, 6, 8, 10, 12, 14, 16, 18, and the last one is 20. There we go. We're displaying our vector data, and then you can see that our data is being cleaned up automatically. Our test objects are being destroyed. Pretty cool. And you can see that there wasn't a lot of code. to write it all. Now, let's clean this up just a little bit here. Remember, we can allow the compiler to deduce our types for us, so we can really clean this up a little bit. Since the compiler knows exactly what we're returning right here, we can simply replace this whole piece right here to auto. We'll just say auto right here. Let the compiler figure out what the type of that return value is, and it knows it based on this. And we can also change it up here in the function prototype. Get rid of all that and just replace that with auto. So we can replace this entire return type right here with auto. And now if we build again, we get the same compile, we get the same run. So let's put 3 data items in here, and we'll say 5, 6, and 7. There we go. We're displaying our data, our vector 5, 6, 7, and we're destroying those objects. Pretty simple. No news, no deletes, not worrying about who needs to delete what. And that's it. That's the solution to this challenge. I hope yours was close. If you had issues with the pointers and figuring out how they work, don't worry, just keep at it. It's just a matter of practice and understanding conceptually what's going on and what's pointing to what, dereferencing what to get what, and it's just a little process that takes time to learn. In this section of the course, we'll learn about exception handling in C++. Exception handling is definitely not a beginner topic, but I wanted to cover the basics so that you can understand exception handling and be able to move on to more advanced features in exception handling as you learn more C++. We'll talk about what an exception is, as well as how we can handle exceptions in C++. Then we'll look at a simple program that has a divide by zero error, and we'll add exception handling to it so that we can handle that error. Once we understand the basics of exception handling, we'll create a function that throws an exception when something goes wrong within it. And we'll see how to throw an exception from that function and also learn how to catch the exception outside the function and deal with it. Obviously, when something goes wrong in a program, the normal flow of control of that program cannot continue as if nothing has happened. So it's very important to understand how exception handling affects the flow of control of your program. Specifically, we'll learn about stack unwinding, what it is, and how C++ uses it. Then we'll create our own exception classes so that we have complete control over the exception types that we throw and handle. Finally, we'll look at the standard exception class hierarchy provided by C++, and we'll look at the types of exceptions that are already defined in C++. Let me finish off this section overview with a few thoughts. Writing exception-safe code in C++ is extremely difficult, and it's beyond the scope of this course. In this section, I want to introduce you to the basic concepts, the syntax, and the behavior of C++ exception handling. There are several schools of thought when using C++ exception handling. One is that it should only be used for extremely exceptional conditions, conditions that would prevent your program from continuing. Another is that it should never be used. And then somewhere in the middle is a school of thought that it should always be used even for not so exceptional situations. And then, of course, there's all sorts of opinion in between all of these. I've worked with C++ code where each of these scenarios was used, and they all have advantages and disadvantages. It really all comes down to how you define what an exception is. This section of the course will present a few C++ exception handling best practices, but it's very difficult to establish these best practices in C++ because when and how to use C++ exception handling is such a hotly debated topic. Okay, so let's see what exception handling is all about. In this video, we'll learn about some of the concepts, terminology, and syntax of exception handling in C++, and then we'll see a simple example that uses exception handling to deal with the divide by zero condition. Let's start with what exception handling is all about. First, exceptions in C++ should be used only for synchronous code, not asynchronous code. Exception handling is about dealing with extraordinary situations. How we define what an extraordinary situation is really dependent on the application and on the designer. We want to be able to detect when an extraordinary situation has occurred or is about to occur so that we can deal with it. Again, what does deal with it mean? It depends on the application. In some cases, we'll be able to recover and continue, but in other cases, maybe the only alternative is to terminate the program. But in this case, we can control how we terminate the program. Perhaps we can close files, save as much data as we can, and fail soft. So, what can cause these exceptional or extraordinary situations? One cause could be insufficient resources. Maybe we're out of memory or we have no external storage left and we need that to continue. Another cause is missing resources. Suppose we need to open and read a file, but that file doesn't exist. If this file is critical to our program, then we have to decide how we're going to continue, if it's even possible. Invalid operations, range violations, underflows and overflows, there are many causes for exceptions. Our programs are said to be exception safe when our code handles exceptions. This is very difficult to do completely in C++. Now let's learn about the terminology used in C++ when we talk about exception handling. This terminology is fairly consistent with many other popular programming languages that you might be familiar with. However, the way it works with C++ tends to be different. First, an exception is an object or a primitive type, such as an int, a double, a boolean, and so forth, and it signals that an error condition has occurred. In many cases, this exception object also contains information about what happened. When your code determines that something is wrong, then it can throw an exception object. Why can't the code just deal with the problem? Well, in some cases it can, and it doesn't throw an exception. It just handles it itself. However, the more common use case is that the problem is detected in one place in your program, but that part of the program doesn't know what to do about it. So it throws an exception and hopes that some other part of the program can deal with it. That's where catching an exception comes in. Some other part of the program could contain the code that catches the thrown exception and handles it. In some cases, dealing with this simply means displaying or logging an error message and terminating the program. That's okay if the program can't continue and we fail soft. In other cases, we may be able to handle the exception, recover, and continue processing. For example, suppose I want to allocate some memory dynamically, but there isn't enough memory available. The part of our code that allocates the memory would throw an exception since it couldn't allocate any more memory, but it doesn't know what to do. Then in some other part of our program, we can catch this exception and maybe we can clear out some buffers or caches and then release some memory and then try to allocate it again. Now, let's see the keywords that C++ uses to achieve exception handling. In C++, we use three keywords to work with exception handling. These are throw, try, and catch. The throw keyword is used to throw an exception object or primitive type, and it's usually followed by an argument, which is the exception that we're throwing. The try keyword is followed by a code block in curly braces. The code in the code block is code that could potentially throw an exception. So we place that code in the try block. If the code does not throw an exception, then the code executes as normal. However, if the code in the try block throws an exception, then the rest of the code in the block does not execute, and C++ looks for a block of code that can handle that thrown exception. That's the catch block, which is the catch keyword followed by the type of exception object that it handles. It also has a code block where the code that handles the exception executes. Catch blocks only execute if an exception is thrown and the type of the thrown exception matches the parameter in the catch block. We can write multiple catch handlers that expect different types of exceptions. The best way to understand exception handling is to really just look at some examples. Let's start with a very simple example that divides by 0. Here we have a code snippet that divides sum by total and stores the resultant average. Let's assume that sum and total have been declared and initialized. So what happens when total is 0? Does the program crash? Do we get an undefined result? The answer is yes, to all of them. It really depends. Because the result of a division by 0 depends on the types of the arguments in the division operation. Integer divide by 0 and floating point divide by 0 may provide different results. We'll see this in a minute in the IDE. Regardless, we can't let that statement execute, so what do we do? Well, that's pretty easy. We check to see if total is 0, and if it is, we don't do the division. And if it is not equal to 0, we go ahead with the division. That's pretty easy. The harder question is, what do we do when total is equal to 0? Well, that totally depends on the application, and this question becomes much more difficult if this code existed in a function, and that function calculates and returns the average. What do we return from that function if total is 0? So we can use exception handling to deal with this situation. This is an example to show you the syntax for exception handling. You wouldn't write code like this since we could print an error message easily with a simple if-else statement as in the previous slide. But let's look at this code together. Again, let's assume that sum, total, and average have been declared and initialized. First, we have a try block. Inside the code in the try block, we write code that could potentially throw an exception. In this case, if total equals 0, we throw an exception. The type of the exception in this example is an integer, and we set it to 0. Best practice is to throw objects, not primitives, but we'll get to throwing objects soon. Let's first look at the case where total is not equal to 0. In this case, the try block executes, the division occurs, and we can use the average and the try block as normal. When the code in the try block completes, we transfer control to the last statement that displays program continues. Notice that the catch block does not fire since no exception was thrown. Okay, now let's suppose that total is equal to 0. Now the code in the try block throws 0. No further code in that try block is executed, so the divide by 0 does not happen. Now we transfer control to a catch handler that expects an exception object of the same type as the one we threw, in this case an integer. The code in the catch block now executes, and when it's done, we transfer control to the last statement that displays program continues again. Notice that we prevented the divide by 0 error, and we handled it in a controlled manner. Now let's head over to the IDE and we'll see this example in action. Okay, so I'm back in the CodeLight IDE. I'm in the Section 18 workspace, and I'm the MPG project. MPG stands for miles per gallon, and that's what we're going to calculate. Apologies to my kilometers per liter friends out there. So what do? We've got miles, we've got gallons. We're going to ask the user for those two values. They're both integers. And then we're going to calculate miles per gallon, which is a double. Pretty straightforward stuff that we've done already. So in this case, notice on line 15 here, I'm calculating miles per gallon equals miles divided by gallons. Now, there's a problem here. We're going to get some truncation because you can see that miles right here and gallons are both integers. So this is going to be integer division, and we're going to truncate the decimal part, right? But the reason I'm doing it this way is to show you the error that happens when you do integer division by 0. Okay, so, but before we do that, let's run this with just some normal data. So let's say we have 13 miles and 3 gallons. Our result is 4. You can see it's not 4 point something because we're doing integer division, but that's okay. We can fix that in a minute. Now let's do a division by 0 and see what happens. So I'm going to run this again. And let's say I put in 13, and this time I put in 0 for gallons. Now when I press enter, it's going to try to divide 13 by 0, and it's going to crash. So I pressed enter, there's the crash on Windows. Okay, I'll cancel that, and close the program, and I'll terminate this program. We don't want to crash, okay? Now if I comment this out, and we do a division by 0 with a floating point number. And what we're doing here is what we did a while back in the course where we had a static cast. Remember, these are both integers right here, miles and gallons. So I really don't want to do integer division. So I just need to make one of them a double, and then double division will occur. So I'm statically casting miles to a double. I could have statically casted gallons or both of them. So in this case, we're doing double division. And the behavior is different here. And I'll show you why. Let me run this again. Okay, so let's do something valid. Let's say 130 divided by 3 gallons. Result is 43.3 miles per gallon. That's fine. Now let's do it with a 0. So I'll get 123 this time, 0 gallons. So we're going to get a divide by 0 here. We're not going to crash though. You can see that the result that prints is infinity. And that's the standard in C++ when you do floating point division by 0. If I run this again and I enter negative for miles, and obviously we would have to do checks for all of this stuff, and 0, then I'll get a negative infinity. You can see that result right here. And the last thing, if we type 0, 0, so we do 0 divided by 0, we get not a number, and that's the error that you see here. All those are bad outcomes. We really don't want those. So the easy fix is not to execute line 16 if gallons is equal to 0, right? It's really that simple. So let's do that. Let's do an if statement. If gallons is not equal to 0, then we do want to execute this code, right? We're safe. And we'll use an else statement here. Let me see, CodeLight puts an extra curly in there for me. So else, we've got an error, so we want to display the error. And what we'll do is we haven't used standard error or C error yet. It's another output stream that's pretty much reserved for error messages or error logging. And I'll talk about that a little bit more when we talk about file I/O. By default, C error is your console, just like C out. So we should see this on the screen. And we'll do an end line here. Okay, so far so good. Again, nothing we haven't done before, but in this case, we're just handling this error. And we're not using exception handling here. We're just using a regular old logic to handle the error. So let me run this, and let's say 130 miles by 0. Now we should have, sorry, can't divide by 0, right? Just like what we'd expect. Okay, so now let's rewrite this program so that we use exception handling. And what we'll do is we'll load the MPG exception project right here, and I'll load that and I'll be right back. Okay, so I loaded the MPG exception project in the Section 18 workspace, and you can see that right now it has no exception handling and it has no if-else logic either. Now here's the commented code that does the integer division. I'm just going to get rid of that because I really don't want to clutter up, and I'm still doing our floating point division here. So what do we do to get exception handling working here? Well, we have to have a try block. So we're going to say right here, try to execute this code. And I'm going to wrap this code up right here inside the try. And I'll indent this. Okay. So what we do here is we try to execute code that could potentially throw an exception. And when do we throw the exception? Well, we throw the exception if gallons is equal to 0. So let's do that right in here. I'm going to say if gallons is equal to 0, that's where I want to throw. And what do I throw? An exception could be anything. It could be an integer, a character, a pointer, an object. Right here, we're just going to throw an integer. Later on, we'll use objects. Best practice is to use objects, but let's just use an integer here so it's easy to understand. So what do I want to throw? I could throw any integer. I could throw 0, right? I could throw gallons. I could do anything I want, but let's just throw 0. Now, what happens? If gallons is equal to 0, then we're throwing this 0. Okay. If gallons is not equal to 0, then our code executes as normal. But what if we do throw this 0 here? If we do throw this exception right here, this piece of code here is not executed at all. Okay, it's totally skipped. And then what happens is that the C++ system is looking for that exception that was just thrown. If you don't catch it, then the program will terminate. But if you catch it, then you can deal with it. So how do you catch it? Well, you catch it using a catch block. And you can put that right here. I'll say catch. And what's the type of the exception we want to catch? In this case, it's an integer. And you always want to catch by reference. That's the best practice. Name this thing anything you want. We really aren't going to use it. And now whatever code we want to execute in here is what's going to happen when the error is thrown, when the exception is thrown. And I'm just going to paste that same C error message that I had earlier. Okay, so now again, let me walk through this with you really carefully because in the next few videos, it'll get a little bit more complicated. So here's my try block. You can see it between lines 15 and 20. And here's my catch handler right here, or my catch block. I tend to use both names synonymously. So again, if the user entered 0, we throw it, right? This code is not executed, thankfully. Otherwise, we'd have a divide by 0 right here. We try to catch an integer. If there is a catch block, but it doesn't catch an integer, or even if there's no catch block, then our program will terminate right on the spot. Okay? In this case, it will, because we're right in our main. Then, if we do throw 0 and we do have a catch handler for it, we'll catch it right here. Now, I could print out EX if I wanted to, right? And it will print out 0 because that's what was thrown here. That's what this guy is right here. That's the object that was thrown, the exception. So in this case, there's my catch handler. In either case, my program will not crash because, let me walk again right through, let me clear this and this. If I do throw an exception, it's handled here. If I don't throw an exception, it's handled here. In both cases, this line will execute. My program will continue normally. It won't crash. All right, so let's give this a run. Let's say 130, and we'll do 0 again. Sorry, you can't divide by 0, so our exception is being handled. Okay. Now, you might ask, so what? Same thing I could have done with an if-else statement. Yes, And this is not typically the way that we do exception handling. This is just showing you the syntax and what's going on. Usually we do the exception handling when a function throws an exception, and that function has no idea what to do with it. And we catch that exception somewhere else. And that's what we're going to go into the next few videos. Okay, I'll see you there. In this video, we'll see a use case that's commonly seen in C++, and we'll see how we can use exception handling with it. Suppose we have a function. Of course, this will also work with methods. And that function is called calculateAverage. It expects a sum of integers that we can assume has already been calculated somewhere else, and the total number of elements used to get that sum. And what we want to do is determine the average and return it as a double from this function. Pretty straightforward stuff. Also notice that we don't want integer division, since we want to return a double, so we're using a static cast to convert one of the division operands to a double. Cool, so far pretty easy, right? Well, almost. What if total is 0? What do we do? What do we return? We could return 0, but 0 might be a valid average. We could return -1, but -1 might be a valid average. We could return some other double that represents an error, but which one, since just about any double could be a valid average? We could rewrite this function to return a Boolean, and that Boolean would indicate success, right? True if it worked, false if it didn't. But then how do we return the average? We'd have to use a reference parameter and do it that way, or use a tuple. Makes the function really clunky to use. So let's see how we can write this function using exceptions and exception handling. We can rewrite the function without changing its interface and still provide a guarantee that the function will not divide by 0 by throwing an exception. First, we check if total is equal to 0. If it is, we don't want to do the division. Instead, we throw 0. In this case, we could throw anything, and C++ allows us to throw just about any type. But let's use 0 again, which is an integer, and we've done it previously. If we throw the exception, the division will not happen and the function will terminate. Now, C++ will try to find an exception handler to catch that integer that the function threw. How does it do that? Well, the handler isn't in this function, so where else might it be? It may not exist at all, in which case the program will terminate. But if an exception handler exists, it must be in one of the functions on the call stack that called this function, right? And C++ will unwind the stack looking for it. We'll see how this works in a few videos. So let's see how this function might be called in a way that would allow us to deal with the exception. Now, this code could exist in any function anywhere in your program. Notice that we have a try block, and in the try block, we call the calculateAverage function. We know this function might throw an exception, and if it does, we'll deal with it in the catch block. But first, let's see what happens if no exception is thrown. Again, we're assuming that sum and total have been declared and initialized. In this case, average is assigned the return value from the function and we display it. Then we skip the catch block completely since no exceptions were thrown, and we execute the last statement that displays by. If calculateAverage does throw an exception, then the remaining code in the try block is not executed, so we do not do the division by 0. And C++ searches for a catch block that expects an integer, since that's the type of the exception that was thrown. In this case, it finds it. Notice that our catch handler expects a reference to an integer. Again, best practice is to throw by value and catch by reference. We'll talk more about that later. So in this case, the code in the body of the catch handler executes, displays an error message to the error stream. When the catch block completes, we transfer to the last statement and we display by. That's it. It's possible to have multiple catch handlers as well as catch-all handlers that will catch any type of exception. We'll do that in the next video. But first, let's head over to the IDE and we'll rewrite the miles per gallon example as a function and use exception handling with it. Okay, so I'm back in the IDE. Again, I'm in the section 18 workspace and I'm in the MPG function project. What I've done here is I've taken the calculation for miles per gallon and I've made it a function. So in this case, it expects miles and gallons, which are both integers, and returns the double, which is the miles per gallon. And I'm simply dividing miles by gallons. And again, I'm casting miles to a double so that we do double division and get an accurate result. That's it. My main is just like it was before. The user enters the miles, the gallons, and the only difference now is that on line 19 right here, you can see that I'm calling calculate miles per gallon, and I'm passing in the user entered values. So let's run this as is without any exception handling, without any error checking at all. So we'll run this, and let's say I entered 120 miles and I entered 0. There's my result, which is infinity. That's not what I want. And we'll deal with that in just a sec. So we know that we don't want to divide by 0. So what we can do up here in the function is we can say if gallons is 0, we want to throw an exception. And we'll just throw, again, we'll throw 0, which is a simple integer. Now, let's run this. You'll see something that's a little bit different now. When I call calculate miles per gallon here, and I use a 0 for the gallons, it's going to throw this exception. That exception is not being caught anywhere. So it's going to go all the way up to the top at my main. That's where I'm at now. And our program is going to terminate. It's going to terminate abnormally. So let's run this so you can see what that looks like. So again, I'm going to enter 120 and I'm going to enter 0 for the gallons. And you can see right there, it says, I'll cancel that. You can see it's terminate called after throwing an instance of int. This application has requested the runtime to terminate it in an unusual way. A bad termination, right? Basically, an exception was thrown that was not handled. That will always terminate your program. So how do we handle that exception? Remember, the calculate miles per gallon function up here has no clue what to do when gallons is 0. All it knows is I can't do a divide by 0. And should I just print an error message? I don't know what to do, so someone else do it. I'm just throwing the exception. So what we can do down here is we can write a try block around this code that could potentially throw an exception. So let's do that. I'll say try, and I'll close off the try block here, and we'll indent this area right here. So I'm going to try to execute that function. If the function works properly, then I just print out miles per gallon. If that function throws an exception, then we're not going to divide, right? Because it's thrown it before the division. It's not going to assign miles per gallon. Basically, the try block will stop, and it's going to look for a catch handler, right? So let's write the catch handler. Our catch handler looks kind of like this. What am I going to catch? Well, I'm going to catch an integer by reference. And right here, I'm simply going to print stood Sierra tried to divide by 0 or something like that. Okay, that's it. So you can see now that the error is detected in one place, and it's all in one file here just for instruction purposes, but this could be anywhere in your program, right? The error has been detected here and it's been handled here. Okay, so let's run this now. And we'll do it again, 120 and 0, try to divide by 0 by. Our program terminated normally. We handled the exception in a controlled manner, and that's really what it's all about. Okay, now, in this case, there could be some issues, right? We need to catch some other exceptions, and that's what we'll do in the next video. What if miles is negative? But that doesn't make sense. I traveled negative 100 miles per gallon. So we want to also throw an error if miles is negative, or if gallons is negative for that matter, right? How can you have negative gallons? So in this case, we're just doing a simple test so we don't divide by 0. But in the other cases, which we'll do in the next video, we're going to check to make sure that we've got valid values here. So if miles is negative or gallons is negative, then my calculation cannot be correct. So we'll throw another exception there, and we'll catch multiple exceptions. So we'll do that in the next video. In this video, we'll see how we can throw and catch multiple exceptions. Suppose we have a function such as the one in this slide. The function is called calculate miles per gallon, and it expects the number of miles and the number of gallons as parameters. And it just simply divides miles by gallons and returns the result. This function will fail if the number of gallons is 0 because we'd have a divide by 0 error. That's what we did in the previous video. But it would also produce incorrect results if either miles or gallons is negative. In this case, we can check for both of these situations and throw a different exception for each case. Let's see how we can write this function so it does just that. The code is pretty much what you would expect. We check if gallons is 0, and if it is, we throw an integer 0 exception. We also check if either miles or gallons are negative, and if they are, we throw a stood string object initialized to the string negative value error. Otherwise, we simply perform the division and return the result. Let's see how we would call this function. Notice that in the try block, we're calling calculate miles per gallon, and that function may or may not throw an exception. If it does not, then we simply assign the result of the function to miles per gallon, display it, and then we display by at the end of the program, and we're done. However, what if calculate miles per gallon does throw an exception? Remember, it could throw an int or a std string. So we create two catch handlers, one for each exception type, and we write our exception handling code in the catch blocks. If an exception is thrown, then one of these catch handlers will handle it. If we don't handle a particular exception type here, then C++ will terminate this function and proceed up the call stack looking for a handler until it finds one or the program terminates. It's also possible to have a catch-all handler. This catch handler will fire no matter what type of exception is thrown. If this is used, it's common to place it as the last of your catch blocks, since it really serves to catch anything that wasn't handled before. Notice the 3 dots or ellipsis in the catch-all parameter list. You don't have access to the exception object thrown in this case, but you can deal with the exception in the body of the catch-all block. Now let's head over to the IDE and we'll rewrite that calculate miles per gallon to throw multiple exceptions. Okay, so I'm in the Code IDE, I'm in the section 18 workspace, and I'm in the MPG function multiple exceptions project. What we've got is the same calculate MPG function that it's simply throwing an exception when gallons was 0. And what we want to do is we want to extend this a little bit so that we'll also throw a different exception when miles or gallons is less than 0. Okay, so right now we've got it throwing 0 if gallons is 0. And we can simply add another check that says if miles is less than 0 or gallons is less than 0, then we want to throw an exception here. Now it can't be another integer. We're already throwing an integer type. So in this case, I simply want to throw a std string, and I'll just initialize it to something like negative value error or something like that. And let me include string up here. That's it. So in this case, if we're going to get a division by 0 error right here with gallons equals 0, I'm throwing the integer. In this case, if I've got an illegal negative value, I'm just going to throw a std string that's been initialized to that string negative value error. That's it. Now, down here, if I run this now and throw a string, it's going to terminate, right? Because I'm not catching a string. So what I need to do down here is add another catch handler for that std string. So I can add that right down here, and I can say I'm catching a string. By reference, we can call it anything we like. I always call them EX for exception. A lot of people call them E. Whatever you like. It's just a variable name. And in this case, I'm going to display to standard error the actual exception, which is a string. So I don't really have to type anything here for the string. It's just going to display that string value that's in that exception object. That's it. So let's try this. Let's run it. And let's do something like 120 divided by 0, which gives us the try to divide by 0 error. And now we've got a by, so that's correct. And now let's try to throw on negative. So let's say -1 and 123, negative value error, just like we expected. And we'll test it with -1 for gallons, or negative anything actually. There's your negative value error. That's it. Simple as that. So you can see here we're throwing multiple exception types, and down here we're catching multiple exception types. Now if I had a catch-all handler here, if I didn't have this handler right here, and I simply had a catch something like this with the ellipsis, and not have this string here, then that would certainly catch the string. I just wouldn't have access to the object, that's all. Okay, so that's it for this video. I'll see you in the next video. In this video, we'll see how C++ looks for catch handlers when an exception is thrown. Suppose we have a function and it throws an exception. If the function doesn't handle its own exception, then the function terminates and it's removed from the call stack. Then C++ looks at the call stack to determine the function that's now at the top, since that function must have called the function that just terminated. If this function used the try block, then the catch handlers are checked for a match, and if one is found, it fires, and we keep processing as we've seen in the examples already. But if there is no try block, or there is a try block, but it doesn't have a catch handler that matches, then the function is removed from the call stack and the process repeats. This is called stack unwinding. If we get to the main function and the exception isn't handled there either, then the program terminates since the exception was not handled. Remember what happens when a function is removed or popped from the stack. All of its local variables are destroyed. This means that for local objects, their destructors are called. If we have to free memory with delete, then these statements may not execute at all, and we will leak memory. This makes it critical that you implement classes that require resources as RAII classes. We talked about RAII in the Smart Pointers section of the course. Make sure that you clean up your resources and your destructors, since you never know when they might be called, and you don't want to leak any memory or leave files or resources in unstable states. Stack unwinding is one of those things that's best understood with an example. So let's head over to the IDE and I'll show you an example of a program and how stack unwinding works. Okay, so I'm in the IDE, I'm in the Section 18 workspace in the stack unwinding project. And what I've got here is just some really simple function calls. There is no exception handling, there's no throwing, there's no catching, there's nothing special going on here. We will add that in a minute. This is our base case, so I just want to go over this to make sure that you understand what happens when we've got this function calling. So let's start here. Here's my stack. Remember, all this happens in the stack. So here's my stack. Remember, all the function calls happen on the stack. So I've got my main. So that means that I've got main on the stack. So main is activated on the stack. We print out starting main, and then we call function A. Well, function A is up here. Function A gets pushed on the stack. So this would be function A here, and it displays starting function A. Then it calls function B. So we go to function B now. Function B gets pushed on the stack. It displays starting function B. It calls function C, and function C is put on the stack. So you can see it's a real nice orderly process of function calling. It displays starting function C, then it displays ending function C, then it's popped off the stack. B completes now and it says ending function B, and it's popped off the stack. A says ending function A, it's popped off the stack. Finally, we're back here and we end up printing finishing main. Okay, so each function announces itself and then it says I'm done. And if we run this project, I'll clear the screen here. And if we run this project, what we'll get is exactly what I just said. Let me move this over here so we can see it. Here you can see we're starting main. Then we're calling function A, function B, function C, and now we're starting to unwind, right? Our program's finishing. So function C is done, function B is done, function A is done, and then main. This is what you would expect. This is normal control flow when there is no exception handling. Now what we're going to do is we're going to add a couple of throws in here and a catch so you can see exactly what happens when we're doing stack unwinding with exception handling. Remember, exception handling definitely could change the normal control flow of your program. So this is the normal flow of our program, assuming we've got no exception handling and no exceptions and no problems at all. All right, so let's say that function C throws an exception, and we'll just throw 100. We could throw anything. The point is we're throwing an exception. So I'm just going to throw 100 here. And in my main, where I call function A right here, I'm going to enclose that in a try block. So there's my try block, and I'll indent that. And then what I'll do is I'll put a catch handler here, and that will expect an integer. By ref, we'll call it EX, and we'll just write something like stood cout. Let's just say caught error in main. Okay, something real simple like that. Now let's walk through this and see what we expect to happen. We're here, main begins, and it prints out starting main. Actually, let me close this up just a little bit so I've got a little bit more room to work. Okay, perfect. Everything fits just right. Okay, so we're here in main, and we're going to print out starting main. Then we're going to try function A. Function A could throw an exception. So I'm coming over here, I call function A, and it prints out starting function A. And it calls function B. Function B begins, displays function B, starting function B, it calls function C, which displays starting function C. Now it throws an exception. What does that mean? That means that this function is now done because it's not catching its own exception here. So this code right here will not execute. We will never see this function complete normally because it's being pulled off the stack right now. Okay. Now what happens? Well, now we go back to whoever called function C, which was function B. So now we're back here, and does that have a catch handler for an integer? No. So this guy gets popped off the stack, right? So this won't execute either. We go back to A, right? Because A called B. It doesn't have a catch handler. This won't execute either. And now we finally get back to the main. The main does have a catch handler. This will fire, and our program will finish normally. But what's happened on the stack is real different, right? You'll notice these three functions got ripped off the stack immediately. All its local variables were destroyed. Destructors were called, if any. So you've got to be real careful with your objects here and make sure that their destructors are correct, because they just got called and they didn't get called as you expected them to be called. So let's run this and see the output now. Now notice the output, how different it is from before. We're starting main, we're starting A, we're starting B, we're starting C, right? Just as we said. Now C throws an exception right here on line 23. It doesn't catch it, so C's gone right now. Notice how the ending function C is never called. We go back to B, it doesn't catch an integer. It's gone. We never see the ending function B. We go back to function A, it doesn't catch it either. So notice what happens here, right? We never see the ending function A message. We finally come back to the main. Main catches the exception. There you go, caught error in main, and it finishes normally. Okay. So this is a good example of stack unwinding. You can see exactly what's going up that chain, right? Now, if I do something like, let's try in function B, let's say, right here. Let's say that we're going to call function C. Let's just try to call function C and see what happens. And in this case, we can catch the integer. And what I'll do is I'll copy that output statement that I created just down here in main real quick. And I'll paste it right in here. And I'll just simply say caught error in, this is function B. Okay, so now let's walk through this example and see what's going on. Let me close this up again, and I'll scroll up just a little bit so hopefully we can fit it all in here. Okay, that's function A up top. All right, so here's main. We're trying function A. Function A could throw an exception, or anything called by function A could throw an exception as well. So I'm calling function A. It says starting function A, and it calls function B. Function B displays starting function B, and it tries to execute function C. So what's going to happen here is function C executes, and it throws an exception. This will not execute. Function C is now gone. But now we come back, and function B is handling the exception. So now this will work, and this will work, and from now on, function B and then function A will all execute normally. Okay, so let's run this and see what we get. All right, look at this. What have we got? We've got starting main, then we're starting A, we're starting B, and we're starting C. Now C throws that error, right? So C is gone. Notice how the ending C is never printed. We catch the error right here on line 21. And then we continue normally because we've handled the exception. So we've got ending B, and then we come back here and end A. And finally, we finish off our main. So this is stack unwinding. I encourage you to play around with this example, put some throws and catches. It's really the only way to really understand it is to play with it, put some tries, some catches, throw in different places and see what's happening. And you'll be able to trace through this. And once you really understand what's going on, you'll definitely understand exception handling and stack unwinding. And it's critical that you understand that, because remember, things are going to get thrown off the stack. So you've got to be sure that you're handling your resources correctly. In this video, we'll see how we can create our own exception classes and throw and catch them. This has the advantage of making the type of the exception thrown very explicit and also very specific for our application. Best practice is to throw objects, not primitive types. Also, we want to throw by value and catch by reference or const reference. There are several other best practices that we'll talk about in a few videos, so let's see how we can create our own exception classes. Here we create two exception classes for our simple example. The first is a class called divideByZeroException, and the second is called NegativeValueException. That's it. Now when we throw an exception in our code, we create an object of one of these types and throw it. Of course, we can provide constructors, attributes, and methods for these classes, as we would for any other class. And sometimes it's a good idea to provide information about the exception in these attributes, but as I said, let's keep it simple in this example. So now let's see what our code would look like throwing these exception objects. Here's the calculate miles per gallon function that we saw earlier in this section. The code is pretty much what you would expect. We check to see if gallons is 0, and if it is, we throw a divideByZeroException object by value. We then check if either miles or gallons are negative, and if they are, we throw a NegativeValueException object by value. That's all there is to it. Now let's see how we'll call this function. Notice that in the try block, we're again calling calculate miles per gallon, and the function may or may not throw an exception. If it does not, then we simply assign the result of the function to miles per gallon, display it, transfer control all the way to the bottom, and display by. And we're done. However, what if calculate miles per gallon does throw an exception? Remember, it could throw a divideByZeroException or a NegativeValueException. So we create two catch handlers, one for each exception type, and we write our exception handling code in the catch blocks. If an exception is thrown, then one of these catch handlers will handle it. Notice how we're catching the exceptions by const ref. If we had provided attributes or methods in the exception classes, we would access them here. As before, if we don't handle a particular exception type here, then C++ will terminate this function and proceed up the call stack, looking for a handler until it finds one or the program terminates. Let's head over to the IDE and we'll see this example in action. All right, so I'm back in the IDE. And what I've got here is the Section 18 workspace, and I'm in the MPG function exception classes project. And what we're doing here is we're creating a couple of user-defined exception classes, which we're going to throw and catch. Same thing we did in the slides. You can see here that on lines 5 through 8, we're creating two classes. One is called divideByZeroException, the other is called NegativeValueException. Notice there are no attributes, no methods, no constructors, nothing. These are just plain old classes, and we're getting the default constructor, and that's good enough for me right now. We could provide attributes and methods and all kinds of good stuff, but the names of the classes in this case give us all the information we need about the exception. So what do? Well, we have to throw these exception objects when we have an error. So in this case, we check to see if gallons is equal to 0, and if it is, we throw a divideByZeroException object. This calls the default constructor. We check to see if miles is less than 0 or gallons is less than 0, right? So if either one of those is negative, then the result won't be valid. So we're going to throw a NegativeValueException object. If none of those is true and we're good to go, we simply do the calculation and we return miles divided by gallons. Okay, just like we've done before. So now down here, let's look at our try block. Here we're just grabbing the information from the user. They've typed in the number of miles and number of gallons. And here's our try block right here. This is the function we're calling calculate miles per gallon. It could throw an exception. If it does not throw an exception, we simply assign 2 miles per gallon the result of that function call. We print out the result, we're done, and then we come down here and we're finished with the program and we terminate normally. If it does throw an exception, calculate miles per gallon could throw a divideByZeroException or a NegativeValueException. So I've got two catch handlers here, one for each. If I get a divideByZeroException, it's coming in here. There's my exception object. If my class did have attributes and methods, I would certainly be able to call them and use them here. But in this case, I'm just saying, sorry, you can't divide by 0. At that point, I transfer control down to here. It says by, and I terminate normally. Same thing with NegativeValueException. If I get a NegativeValueException, I catch that object here, and notice I'm catching both of these by const ref. I display, sorry, one of your parameters is negative. The catch handler completes, and I come back here and I finish normally. So I don't have any abnormal termination in this case. So let's run this and we'll give it a test real quick. So let's do a normal test case, 123 miles, and let's say I use 13 gallons. So my result is 9.46, exactly what we expect. Let's run it again. This time we'll say 123 with 0 gallons, so we expect a divide by 0 message. Sorry, you can't divide by 0. Notice the by also happens, which means our function terminates, our program terminates normally. Let's run it one more time with negative for miles and something else for gallons. Sorry, one of your parameters is negative. And actually, we'll do it one more time for the gallons being negative. That's the last test case. And we'll say -3. Sorry, one of your parameters is negative. So that's handling all the cases that we've got. And we're basically creating our own user-defined exception classes. Now, this is pretty common, and you can see that it's real nice. As far as very readable, you're throwing an object as you're supposed to. You're catching it by const ref like you're supposed to. In a few videos, we'll talk about C++'s standard exception hierarchy, where it's possible for us to derive our exception classes from one of C++'s exception classes. If you're coming from the world of Java and other programming languages, that's pretty much what you do. In C++, you have the option of creating these standalone exception classes or buying into the standard exception class hierarchy that's provided by C++. But we'll talk about that soon. In this video, I'd like to briefly talk about exceptions in the context of a C++ class. Exceptions can be thrown from class methods, constructors, and destructors. Let's talk about the last one first. Do not throw exceptions from a destructor. The destructor is marked in C++ as no except by default, which means that it does not throw exceptions. If a destructor is called as a result of an exception being thrown elsewhere, and then the destructor throws an exception, then there's a problem since the original catch block will never be reached. This is a very bad situation. The only time a destructor might throw an exception is if it handles it itself, and that's a very unlikely use case. So remember, best practice is to not throw exceptions from a destructor. Okay, so now let's talk about methods and constructors. In the case of class methods, exception handling here works just as we've seen with regular functions. What about constructors? Constructors could certainly fail, and since constructors don't return values, we can't return a Boolean or an error code. Constructors may fail for many reasons. For example, suppose you're allocating memory dynamically and you're unable to allocate it, or if you open a file in the constructor but the file doesn't exist. In cases such as these, the constructor can throw an exception. The rest works just as you would expect. Let's see an example of throwing an exception from a constructor. In this slide, we're using the account classes that we've been using throughout the course. Suppose we cannot have accounts with negative balances. So in the account class constructor, we can check the balance, and if it's less than 0, throw an illegal balance exception object. In this case, we're assuming that we've created our own illegal balance exception class. That's it. Now let's see how we can catch this exception if it occurs. So here we have a try block, and in that try block, we're declaring a unique pointer to an account object and using makeUnique to create a checking account object for Mo with a negative balance on the heap. Since the account balance is negative, the account constructor is going to throw an illegal balance exception, which we're catching in our catch block. We display an error and our program continues. Now there's a lot more to class level exceptions, but for the purpose of this course, this is the basic information necessary to use and understand class level exceptions. In the next video, we'll look at the exception class hierarchy that the C++ standard library uses internally, and we'll see how we can tap into that hierarchy for our own exception classes. But first, let's head over to the IDE and let's throw a class level exception from our account class. Welcome back. I'm in the IDE and I'm still in the section 18 workspace, and I'm in the constructor exception project. And what I've done here is I've copied all those files that we created for the account class that we've been using throughout the term. So I've got accounts and checking accounts and printables and basically everything we've done. This is the latest version of it. But what I've done is I've added a new header file right here called illegal balance exception. And I don't need the CPP file because everything can be done in this header file. Notice what I've done here. I've created a class called illegal balance exception, which represents the condition where we've got an illegal balance, in this case, a negative value. This is the exception object we're going to throw. And then we've got a constructor and a destructor, and I've tagged them both as default. That way we're using just regular default constructor and regular default destructor. That's it. Now what we want to do is go to our account CPP file, and what we're going to do is in the account constructor right here, we're going to check to see if the balance is less than 0. If the balance is negative, then we're going to throw an illegal balance exception. That's that class that we just created. This will throw an object of that class. Okay. Now, I mentioned that there was a lot more to constructor level exception handling. One of the things that you can do with constructors is you can try, remember we have an initializer list here. We could try to execute some of that. So it's possible to put try statements in there as well. In this case, we wouldn't do that, but you might want to do that in subclasses. Again, that's a little bit beyond the scope of the class, but I just wanted to bring it to your attention in case you see that out there. So this is it here, right? We've got an account. If the balance is negative, we're going to throw an exception. So now let's look at our main and let's test this out. So here's my main. And notice what I've done in the main. I've got a try block right here. Let me grab my pen so I can mark this up and make it a little clearer. I've got a try block right here. And in the try block, I've got a unique pointer to the base class. I call it Mo's account. And I'm using std_make_unique to create a checking account on the heap. That checking account contains the name Mo. And notice that negative balance right there. Okay, that's going to throw an exception. We're using this in the try block because that constructor for the account class, in this case, remember it's checking account, but it's calling the base class constructor as well. And that's the guy that's going to throw the exception. So in this case, this will throw an exception. It'll throw a illegal balance exception, which I'm catching here by constref. If it doesn't throw an exception, then we simply dereference Mo's account and print it out to standard out. Okay. If it does throw an exception, we're going to catch it right here, and we're going to deal with it. How do we deal with it? We're just going to say couldn't create account, negative balance. That's it. But the point is our program completes successfully. This will execute. It doesn't crash. Okay. Now let's do this two different ways. Let's run this test case, and first let's create it with a positive balance, a $10 balance. So let me build and run. And the output says checking account Mo $10. Program completed successfully. Just what we'd expect. But now let's create the negative balance. And we'll build and run again. And notice the output now says couldn't create account, negative balance. And again, program completed successfully. That's pretty cool. So that works really, really well. And that pretty much does it. For the section challenge in this section, it's actually a pretty easy challenge. Although some of the things will be a little bit advanced, the challenge is pretty easy to do. What I'd like you to do for that challenge, and I'll talk about it in the challenge video, is to provide an exception when we've got insufficient funds. Okay, remember before we created right here this withdraw that was true false? Well, rather than do true false, let's throw an exception and catch it. But we'll get to that soon. In the next video, we'll talk about the C++ standard exception class hierarchy. In this video, I'd like to briefly talk about the C++ standard exception class hierarchy. C++ provides a class hierarchy of exception classes. These exception classes are used throughout the C++ standard libraries. The std_exception class is the base class, and all other exception classes are ultimately derived from it. std_exception provides a virtual function named what that returns a C-style string with a description of the exception that occurred. We can create subclasses of the exception classes and then implement the what virtual function so that it displays whatever exception message we want. Let's take a look at the exception class hierarchy. Here's the C++ standard library exception class hierarchy. The classes that are in orange are the C++ 17 additions to the class hierarchy. Notice that the common base class in the center is std_exception, and then we have many classes derived from it. exceptions that are runtime errors, logic errors, bad allocation errors, out of range errors, and many more. We aren't going to study these classes in detail, but we can create our own user-defined classes that are derived from these exception classes. This can be very useful in some situations, since by being derived publicly from std_exception, our classes are now part of this hierarchy and can be used wherever a std_exception is expected, since your class is an exception. Also, thanks to dynamic polymorphism, all you have to do is implement the what virtual function and it will be bound dynamically at runtime. Let's see an example of how we could create an illegal balance exception for our account class, but this time let's derive it from std_exception. Here's a simple example that shows how we could create our user-defined exception class named illegal balance exception, and this might be thrown if the account is created with a negative balance. Notice that we derive the class publicly from std_exception, and we simply provide a default constructor and a default destructor. Finally, we implement the what virtual function and return a C-style string describing the exception. This is a really simple implementation. We could provide all sorts of error information, codes, descriptions, and so forth as class attributes and initialize them in the constructor when we create and throw the object. There's a keyword here that I haven't talked about yet. That is the noExcept keyword. This tells the compiler that the method will not throw an exception. So don't throw exceptions from these methods. The destructor is noExcept by default. If you do happen to throw an exception from a no-throw method, the program will terminate. The exception will not be handled. Let's see how we might use the account class hierarchy that we've used throughout the course. Here's the code for our account constructor. We're checking to see if the account balance is less than 0, and if it is, we're throwing an illegal balance exception, which is our user-defined exception class derived from std_exception. This code should look pretty familiar, since it's more or less the same code that we wrote when we created our own standalone illegal balance exception class. Now we can try to create an account object. In this case, we'll create a unique pointer and create a checking account object dynamically. Notice that we're creating Mo's account with a -100 balance. This is not legal, so we expect that the account constructor will throw an illegal balance exception object, and that's exactly what we're catching in our catch handler. In this case, the catch handler fires, and we call ex.what, which will display illegal balance exception. That's pretty powerful and not too difficult to understand or use. Well, that's it for exception handling. The challenge exercise for this section is next, and although it involves some more advanced exception handling techniques than you'll find in most courses, I think you'll be able to do it just fine. Let's get to it. Hello, welcome to the Section 18 challenge on exception handling. Congratulations on finishing this section. This challenge is a very straightforward challenge, but it's going to be using some interesting techniques. One of the things that I want you to do in this challenge is to derive your own exception classes from the standard libraries exception class, and then integrate that into the account class, and then test your code. Now, I've got you started here. I've created a challenge project, and again, I'm in the Section 18 workspace in the challenge project, and under here, I've got all the source code for the account class that we've been working with throughout the course. This is the description.txt file, which is the one we're looking at right now, and I'd like to read through this in a minute, and then I'll talk about different exception classes. Okay, so for this challenge, what we want you to do is to integrate your own user-defined exception classes into the account class. The account classes are provided for you. You can see them over here. Also, the illegal balance exception class already has been created for you, but it does not derive from the std_exception class. You have to do that yourself. What I'd like you to do is derive the illegal balance exception class, like I just said, from std_exception and implement the what method. Okay, that what method is that virtual method that returns a character string, a C-style string, and provide an exception message there. Now, this exception object should be thrown from the account class constructor whenever we get a negative balance. Okay, so in other words, if you try to create an account with a negative balance, we want to throw this, very much like what I did in the slides. So that's one class. The second class is a class called insufficient funds exception, and you can see that right here. Again, I want you to derive this from std_exception, and implement the what method for it to provide a message. This exception object should be thrown if a withdrawal results in a negative balance, so you're overdrawn. Okay. You should throw this exception object from the account's withdraw method. That's it. Pretty straightforward. The harder part of this assignment is not so much implementing these classes, it's testing them. And you'll have to do that in your main. All right, so let me go over this illegal balance exception class right here. There's no CPP file, it's all in the header file. And I've created a class called illegal balance exception. It's got a default constructor and a default destructor. And I've got those curlies here. You could replace those with equal default if you like. I think I do that in the solution, but you don't have to. So that's it. Now, what I want you to do is public inheritance here, std exception, and then implement the what method. You'll notice that that's already there. And if you go to account CPP, in the account constructor here on line 3, I'm checking to see if the balance is less than 0. If it is, I'm throwing illegal balance exception. Okay, so that's part 1. The second part is I want you to create, let me go back to my description real quick. I want you to create another class called insufficient funds exception. Same idea as illegal balance exception. It's going to be derived publicly from std exception. You're going to have your constructor, your destructor, and you're going to implement that what virtual function again. And then that exception will be thrown here in the account CPP withdraw method right here. So you can see that if the balance goes negative, you want to throw that exception object. Okay. Now, where do you catch these things? Well, let's go to our main. This is where you want to test your code. This is where you want to create your checking account objects, your savings account objects, and so forth. Create them with negative balances. Put $100 in it and then withdraw $200 from it so you get an insufficient funds exception. So that's the kind of thing you want to do here. You want to be sure you do that in a try block, and you want to be sure that you're catching those exception objects here. Okay, so that's really it. It's not a lot of code to write. It's just writing them in precise locations and getting it to work just right. All right, so good luck. I'll see you on the next video where I'll show you my solution. Okay, welcome back. This is my solution to the Section 18 Exception Handling Challenge. I'm in the Section 18 workspace in the Challenge Solution project. And again, this is my solution. There's different ways to do this. If you did it a different way, that doesn't mean it's wrong. It's just different. Post it and we'll get some comments from everyone. So in this case, let's take a look at what I did. I've created the illegal balance exception that we had earlier, but I changed it a little bit because what we want now is we want the class illegal balance exception to be derived publicly from std exception. Okay, so that takes care of that part. So now remember, an illegal balance exception now is a std exception. I've got my public modifier here. Here's my constructor. I'm just using a default constructor and I'm guaranteeing no exceptions being thrown from it. I've got a destructor here, again, a default destructor. And here's my virtual what function. And here's the prototype for it. It's virtual. It returns a pointer to a character, which is a C-style string, and it's const. The function itself is const and won't modify anything. And again, I'm guaranteeing no exceptions being thrown from here. And all I'm returning here is any kind of C-style string, in this case, illegal balance exception. And this is what we're going to print out on the other side when we catch this exception and print out the message. So that takes care of illegal balance exception. Now let's take a look at insufficient funds exception, which is right here. And neither one of these needs a CPP file because we're doing everything right in here. So here's the insufficient funds exception, pretty much the same pattern. My class is insufficient funds exception. It's derived publicly from std exception. And I've got insufficient funds exception. Again, no except default constructor, default destructor, and there's my what virtual function, which simply returns insufficient funds exception. That's it. Now, if I go to my account CPP file, you can see here in my account constructor, if I'm trying to create an account object with a balance that's negative, I'm throwing illegal balance exception. And down here, my withdraw method, if the balance goes below 0, I'm throwing an insufficient funds exception. Okay, that's it. Pretty straightforward. Now, let's take a look at the main where we can test some of this. So here's the main, and What I'm doing here is I'm creating two unique pointers, one to Mo's account, one to Larry's account. And then the first thing I want to do is I want to try to create Larry's account with a negative balance. Right now, I expect this to throw an exception, and I want to catch it right here. I want to catch the illegal balance exception and just simply print out x.what, right? That's going to call my virtual function, and hopefully it'll say that I've got a negative balance or an illegal balance. So that's one test case here. In this test case, I'm going to try to create Mo's account as, they're both savings accounts, by the way. I'm creating Mo's account as a savings account with a $1,000 balance. And then I'm displaying it. I expect that to work. Then I'm withdrawing $500 and displaying it again. I expect that to work. Now I'm withdrawing $1,000. I don't expect that to work. I expect that to throw an exception because that would create an account now with negative 500. I'd be overdrawn. So I don't expect this to display. Okay. And this Larry's account here, we really don't need. Sorry about that. That was a carryover from before. Okay, so that's better. So in this case, we're going to catch both these exceptions, an illegal balance exception and an insufficient funds exception. If either one of them throws, then I catch them and just display their what. Okay, so let's run this. And here's my output. First one is I've got an illegal balance exception. That's what I expected because I tried to create Larry's account here with negative balance, right? Then down here, remember at this point, I don't display Larry's account because Larry's account hasn't been created. So what I do is I just skip down to here, and now I'm in this piece of code here. So the first thing I want to do is I want to try to create Mo's account with $1,000 and display it. And you can see right here, Mo's account with $1,000. There's no interest rate because I didn't supply one. Then I'm going to withdraw $500 from Mo's account and display it again. So now you can see Mo's account now has $500 balance right here. Now I'm going to try to withdraw $1,000. That should not work. So I shouldn't see Mo's account displayed again. Instead, I should get an insufficient funds exception being thrown. And that's exactly what happens here. This catch block fires the second catch block, and ex.what is displaying insufficient funds exception. That's it. Most likely your code is very similar to mine. Your test cases may be different, but that's okay. You can test this by using nested try statements as well. You can have one try inside another. You can try to create the object, and then once you've created the object, you can create try statements within that try statements that are exercising some of the withdraw methods. So that's it. I hope you had fun in this section and in this challenge. In this section of the course, we'll look at how C++ uses streams for I/O. First, we'll learn what streams are and how they help abstract the complexity away from working with different types of input and output devices. Then we'll learn about some of C++'s stream manipulators. These are functions that can affect how we read and write data to and from streams. Then we'll learn about some of C++'s stream manipulators. These are functions that can affect how we read and write data to and from streams. We'll learn about stream manipulators that affect Boolean, integer, and floating point values. And then we'll use some manipulators that work with any type of data to help us format our output. These manipulators give us the ability to align text, fill blank areas with specific characters, and set the width of output fields. Then we'll do a challenge where we'll use the manipulators to format a report containing information about tours to South America. After the stream manipulators, we'll learn about input files, how to open them, check to see if they were opened successfully, read from them, and then close them. We'll read from them using both formatted and unformatted I/O. And we'll do two challenges using input files. The first is to create an automated grader that will grade student quiz responses from a text file and produce a report of the results. For the second challenge, we'll ask the user for a word and see how many times that word appears in Shakespeare's play Romeo and Juliet, which is stored on a file and disk. Then we'll learn about output files and how they work. We'll learn to open them, write to them in both formatted and unformatted modes, and close them. And then we'll do another challenge that creates a copy of Romeo and Juliet but adds line numbers to the play. Then we'll wrap up this section by looking at string streams. This allows us to use in-memory strings as streams and use the same I/O techniques that we use with files with in-memory strings. It's very powerful. And we'll also see how we can use string streams for data validation. As you'll see in this section, IDEs differ in where they store files for use within the IDE. In the last video of the section, I'll show you how to set up external text files for reading in Visual Studio, CodeBlocks, CLion, and Xcode. Okay, we've got a lot to get to. Let's get going. In this video, we'll learn about how C++ uses streams and files for I/O. Writing an I/O library for any programming language is an extremely difficult task. There can be all sorts of devices providing data to your program, and your program can send data to many types of devices as well. These devices may be physical devices such as hard disks, the console, and the keyboard, or they can be virtual devices such as some connection to a web server. C++ provides a stream abstraction to work with I/O devices. A stream is an interface that's independent of the actual device. So from the programmer's perspective, we can code to the stream interface and not worry too much about what device is connected to the stream. A stream is exactly as you would expect. It's a sequence of bytes. C++ provides different types of streams, depending on whether we want input or output, but we can also use a stream that does both. Let's see what this looks like visually. In this slide, you can see that the C++ program is on the right side. The upper stream is an input stream that provides input to the program from some input device. This device can be the keyboard, a file, a connection to a web service, and more. The lower stream is an output stream that takes output from the program and sends it to the output device. Again, the output device can be a file, the console, a connection to a web service, and more. So let's see some of the C++ header files that we typically include to allow us to work with I/O streams. In this slide, we can see three of the most commonly included header files that allow us to work with stream I/O. There are others, but these three are the most commonly used. First, we've already seen and used I/O stream. I/O stream provides the definitions required for formatted input and output to and from streams. The fstreaminclude file provides definitions for formatted I/O to and from file streams. And the iomanip header file provides definitions for manipulators that allow us to format I/O streams in specific ways. We'll use the iomanip functionality first in this section. When we include these header files, we'll have access to many C++ classes that we can use for file I/O. So let's see a few of them. The iOS class provides basic support for formatted and unformatted I/O. It serves as a base class for most other classes in the I/O stream hierarchy. The ifstream class provides high-level input operations from files. So if you want to read from a file, you can declare your object to be an ifstream object. The ofstream class provides high-level output operations from files. And again, if you want to create a new file or write to a file, you can declare it as an object of ofstream. The fstream class provides high-level I/O on file-based streams. Fstream is derived from ifstream and ofstream using multiple inheritance. If we need to do both input and output to a file at the same time, we can declare an fstream object to do it. Finally, we have the string stream class. This is a very useful class that provides high-level I/O on memory-based strings. Just like we can use insertion and extraction with cin and cout, we can use them with strings to get input and provide output into a string in memory. That's pretty powerful stuff, and we'll see some examples later on. Finally, let's visit our old friends cin and cout and see exactly what they are. The fact that we've used them all along without worrying about how to create them, how to connect them, and so forth is a testament to the design of the C++ I/O library and the device independence model. cin, cout, carr, and clog are global objects. They're initialized before main begins to execute, and all you need to do is include I/O stream to use them. cin is the standard input stream and is by default connected to the keyboard. It's an instance of the iStream class. cout is the standard output stream, and by default, it's connected to the console. It's an instance of the ostream class. This class should sound familiar since we used it when we overloaded the insertion operator in the overloading operators section of the course. cin and cout are generally buffered streams. This means that input from cin won't be automatic until the user presses enter, and output to cout occurs only when the stream buffer fills up, or we provide a std endline, or we flush the stream. Now, cerr and clog are the standard error stream and the standard log stream respectively. By default, they're both connected to the console. They're both unbuffered, which means that we get input or output from them as we need it. Best practice is to use cerr for error messages and clog for log messages. Those of you who are familiar with the Unix terminal shell or the Windows command prompt know that we can redirect these streams easily, so input comes from a file or output goes to a file. I won't be covering this in this course, but if you're interested, do an internet search for redirecting I/O and you'll see how easy and powerful it can be. Okay, so that concludes this video. In the next video, we'll see how we can use the I/O manipulators to help us format our I/O. In this video, we'll learn about some of the C++ stream manipulators. C++ streams have many useful member methods that can be used to control formatting. There are methods that work on input and output streams, but formatting output is much more common. An important concept to understand is that when we manipulate a stream for formatting, sometimes the settings we make will be set for the remainder of the program, other times they'll only affect the next object placed on the stream, and sometimes their effect is immediate. When we go over the individual formatting methods and manipulators, I'll show you the effect each one has, as well as how long the effect lasts. Most of the stream formatters come in two versions, a method version and a manipulator version. The method version is simply a method call that you use with a stream object. For example, cout.width10. I'll explain what this does in a later section, but for now you can see the syntax. It's calling the width method on the cout object. There's also a manipulator version, which is designed to be used inline as a stream insertion. In this case, setw10. As you probably guessed, the manipulator versions are simply overloading the insertion operator to make this easy to use. To use the manipulators, you must include iomanip. The code we'll write will focus mainly on manipulator usage, but I'll also show you how to use the methods. In the next few videos, we'll go over some of the most commonly used stream manipulators. Here's a preview. We'll first start by looking at formatting Boolean types. We've already seen this used in the course in a few places. We can use bool alpha and no bool alpha to display Boolean values as either the strings true or false, or the integers 1 and 0. Then we'll look at formatting integer types. These manipulators allow us to display integers base 10, base 16, or base 8, as well as to decide whether we want the base prefix to show, and in uppercase or lowercase. We can also decide if we want positive numbers to show the plus symbol in front of the number. Then we'll switch over to floating point numbers. Again, we've already seen some of these manipulators used in the course. We can use fixed point, we can set the precision, we can show the number in scientific notation format, and again, we can decide whether we want trailing zeros printed and whether we want the plus symbol displayed. Then we'll learn how to output numbers and strings in fields of fixed width, and we can see how we can left or right justify them within that field. We'll also be able to fill empty space within the field to a specific character. Finally, there are several other formatters that can be very useful. Endline we've already seen and used. Flush can be useful when we want to be sure that we flush out any stream buffers, but it doesn't add a new line like endline does. The last few we really won't talk about much, but I'm including them here for your reference. Skip whitespace, no skip whitespace, and whitespace are typically used with input streams when you have very specific use cases about dealing with white space. Okay, so in the next video, we'll start with the Boolean formatters. I'll see you there. In this video, we'll see how to format Boolean types to output streams. Note that we're using cout in these examples, but any output stream will work, including file output streams, which we'll learn about later in this section. By default, a Boolean value is displayed as a 1 if the value is true, or as a 0 if the value is false. But sometimes we'd like to display the strings true or false, and we really don't want to write if-else logic all over our code every time we need to do that. Instead, we can tell our output stream to display Boolean values as 0, 1, or as true, false, whichever we want. First, let's see an example of the default behavior for Boolean values. First, we display the value of the expression 10 equals 10. Since this is true, a 1 will be displayed. Then we display the value of the expression 10 equals 20, which is false, and as you see, a 0 is displayed. Now let's use a stream manipulator to switch this to true-false mode. In the first statement, we're setting the output stream cout to bool alpha mode. This means that all further output to cout will display true or false as strings. And you can see the output from the same program now displays true and false. It's important to understand that with Boolean formatting, once we set it with bool alpha or no bool alpha, then all further Boolean values will be displayed that way. We can toggle back and forth as appropriate as shown in this slide. We can also set the format for Boolean types using the setF method. In this case, we have a bunch of flags that can be used to set and reset formatting directives. In this example, we can pass std ios bool alpha or std ios no bool alpha to the cout object to change its formatting. Finally, we also have a method named reset ios flags that expects the flag to reset. In this case, we can pass in std ios bool alpha, and it will reset the stream to whatever the default is for that flag. In this case, it will go back to displaying Booleans as 0s and 1s. Although you sometimes see this type of code in production, it's more common to see the manipulator version, and that's what I'll focus on in this section. So let's head over to the IDE, and we'll do a couple of examples using bool alpha and no bool alpha. Okay, so I'm in the IDE, I'm in the section 19 workspace in the manip_boolean project. And in this project, I've got a bunch of simple test cases here that just display certain values to standard out or cout. In this case, those values are Boolean values, and we're going to manipulate them using the no bool alpha and bool alpha manipulators. So here's the default. What we're doing here, we're going to use this same test case throughout. You can see what we've got here. We've got, is 10 equal to 10? That's either true or false. Obviously, this is true, so this will always display true. And 10 equals 20 will never be true, so that'll always display false. In this case, we're using an expression, but we could certainly use a variable, anything that evaluates to a true-false value. So by default, this will display true, which is a 1, and this will display false, which is a 0. Okay, so by default, that is the way that we display Boolean values, as we saw in the slides. So why don't we run this program, and then we'll start modifying it just a little bit so we can start displaying the actual string true-false. Okay, so let me run this, and you can see right here, I'll move this over here so you can see what's going on. No bool alpha is the default. I didn't set it, but it was just a default. You can see I've set nothing here. All I'm doing is those two cout statements. And I'm getting a 1 here, and I'm getting a 0 here, exactly what I expect. Okay, so now let's make a few changes here. So you can see what I'm doing here on line 14. I'm inserting std bool alpha onto cout. It's a manipulator. This will switch the default formatting in this case now to true false. Now it's important to understand, and we'll show you on lines 19 and 20 that this is true. Once we set that, everything else, whenever you need to display a Boolean value, this is the setting that'll stick. Okay, so if we need to go back to 0 or 1, we have to do that manually. All right, so what we expect here now is to actually display the word true and the word false. So let's give this a run. And here you go. You can see the original two statements, 1, 0, but now we're seeing true, false. Okay, so here, all we're doing is showing that once we set it, it's set, right? So here it's set to true, false, and we just displayed two statements to cout. Now we've got another 2, and we expect those to be true, false as well. There you go, true, false, true, false. It's going to keep doing this until you change it. And that's what we're going to do here on this lines 23 to 25. I'm using std no bool alpha, so this is toggling it back to the default of 0, 1. And at this point, we should be getting 0, 1. So I should get, again, 1, 0, true, false, and then 1, 0 again. And that's exactly what I'm getting. 1, 0, true, false, and then 1, 0 here. Okay, so that's pretty straightforward. And believe it or not, What you're seeing here holds for every one of the manipulators that we're going to see. So it's the same kind of behavior, not the part of once you set it, it's set. Some of them just work for one insertion, but we'll talk about those. But I'm talking about the syntax and the general flow here. It's pretty much the same for all of them. So let me comment out these lines 28 to 30. And in this case, I'm doing the same thing, except I'm not using the manipulator. I'm using the setf method. So you can see I'm saying stood cout dot setf. Setf is the method, and it expects a stood iOS bool alpha. Now that looks maybe kind of intimidating and nasty. It's not so bad. Stood is the namespace, iOS is a class, and bool alpha is a flag that's defined in that class. Okay, so C++ is doing exactly what it was expected to do. If you just type bool alpha, it won't know where to find it. So you have to say it's stood namespace, iOS class, bool alpha flag. If you're using namespace standard, then you don't need to put stood here or anywhere here that you see it lighting up, right? You could just use iOS bool alpha. Okay, so in this case, again, I'm setting it back to true false, but I'm doing it with this method now. So you should see those last two statements display the words true false. And there they are right here. You can see there's true and here's false. And then the last one is used to reset certain flags. All of these flags that we're going to use have default values. Okay, so when we talk about left and right justification and the way we display numbers or the way we display Booleans is in this case, they have default ways of doing it. We know the default for Booleans is the numbers 0 or 1, right? So there is a manipulator here called reset iOS flags. And again, it's in the stood namespace. So reset iOS flags. And then you pass into it whatever flag you want to reset. And it will reset that not to bool alpha, but it'll reset it to the default behavior for displaying Booleans, which in this case will be numbers, right? 0, 1. So when we run this, we expect that to be reset to the default. And what's nice about this is, suppose you've got a modifier that has, there aren't any like this, but suppose you had 8 different values, right? One of them is obviously the default. You don't have to worry about which one to set. You could just basically call this with the flag you want, and it'll reset it to the appropriate behavior. So let's run this, and now we expect that those last two statements to print out 1 and 0. And there you go. So that's it. The basics of everything else we're going to do with the manipulators are here. We can use them in line. We can use them with functions. And what we'll do next is we'll talk about integer output. So we'll be right back to do that. In this video, we'll see some of the stream formatting options available for integers. Integers have 4 basic formatting options, and let's see what the defaults are for those options. First, integers are displayed in base 10 by default. This makes sense since base 10 is what most people in the world use as their base system. However, we also have the option of displaying integers in base 8, which is called octal, and base 16, which is called hexadecimal. Remember, computers work in base 2 or binary, and that's difficult for humans to understand. So we need alternate base systems. Base 10 is what we learned in school, and that's the way we count and do math. But it's not so intuitive to convert decimal to binary. The alternate bases are often used in computing, since they allow us to group information more like a computer would. For example, since octal is base 8, we can group consecutive binary digits into groups of 3, starting from the right, and we can easily convert between octal and binary and back again. Hexadecimal is base 16, which allows us to represent locations in memory, since each hexadecimal digit represents 8 bits or 1 byte. If you recall, earlier in the course, when we displayed addresses, they were displayed in hexadecimal format. We also have the option to display the base as a prefix for hex and octal values. For hex, we start with 0x followed by the hex number, and for octal, we start with a 0. This clearly tells the reader that the number is hex or octal, since in some cases, it would be impossible to tell otherwise. The default is not to show the base. We can show the letters and hex numbers as well as the hex prefix in upper or lowercase, and lowercase is the default. And finally, we can choose to display the plus sign when we have positive integers. The default, as we've seen already, is not to display the plus sign when an integer is positive. This might sound complicated and intimidating, but it's easy as pie. let me show you how we can use the IOStream manipulators to change the way we format integers. First, let's see an example of displaying integers using different bases. Here we initialize num to 255. That is 255 in base 10, just like we're used to doing. Now we can use the base manipulators to change the way the integer is formatted. Remember, even though the output changes, 255 is still stored in num and we're not going to change it. First we use std_des, and that means decimal, and that displays the number in base 10. We really don't have to specify this at all since the default, but I wanted to show you how to do it, and this will display 255. The second display statement uses std_hex. In this case, we display FF, which is the hexadecimal value for 255. Also note that the F's are in lowercase, which is also the default. Finally, we have the oct manipulator, and we display 277, which is the octal value for decimal 255. Once we set the base using the manipulator, that base will be used for all future insertions of any integer on the output stream, so that setting will persist. Now, if we see 255 and 277 out of context, it would be virtually impossible to tell whether they were base 8 or base 10. So that's where the show base manipulator comes in handy. I'll show you that in the next slide. So in this example, we have the same code, except we're using the show base manipulator. Now, when we execute the same code, notice that 255 is unchanged, but the hexadecimal FF now has a 0x prefix, and it's in lowercase. Also, the octal 377 now has a 0 preceding it. Now it's very clear what the base of each of these numbers is. Also note that the show base is applied to all further integer stream insertions, so it also persists. We can toggle back to not showing the base by using std_no_show_base. Sometimes we want to be able to display hexadecimal digits in uppercase as well. And sometimes we want to display the 0x prefix in uppercase. We can do this with the uppercase manipulator. In this case, we're using show base and uppercase. And then we use the hex manipulator and display the number. Notice how we display 0xFF and all the letters are uppercase. Like show base, uppercase will be used for all further hex output, and we can toggle back to lowercase using no uppercase. Now let's see how the show positive manipulator works. If we use show pos or show positive, then we'll get a preceding plus sign on positive integers. You can see in the provided code that we have two integers, num1, which is initialized to 255, and num2, which is initialized to minus 255. Without using the show pos manipulator, if we display these integers, we get 255 and negative 255. Note that there's no plus sign in front of the positive 255. However, when we use the show pos manipulator, now we see the plus sign in front of the positive 255. This can be useful sometimes depending on the application. Some accounting software wants that plus sign in front of the number. Again, this setting also persists, so it'll apply to any other integer stream output. And again, we can toggle back to not showing the plus sign with the no show pos manipulator. That's it. I told you it was easy. There are also several variations using the setF method, and we can also reset to defaults using std_reset_ios flags and providing the flags we want. I encourage you to do as I do. That is, not memorize any of these things, but just know where to look them up. The C++ reference documentation is pretty good and everything's there. Unless, of course, you want to memorize them. That's up to you. Okay, so let's head over to the IDE and try some of these combinations out. Okay, so I'm in the IDE. I'm in the section 19 workspace in the manip_integer project. And what I'm doing in this project, just manipulating integers, just like we did in the slides. I'm converting them to different bases, and then I'm playing around with some of these manipulators. So let's start by, first of all, including IOStream and IOmanip. We need to do that in order to use our manipulators. And I've got an integer here that I've defined and initialized to 255. It's called num. Okay, so let's start right here. Here what we're doing is we're displaying num, and again, it's only the one variable we're going to use throughout this example. We're displaying it in decimal format. Again, we don't really need to do this here since it's the default. And then in hex, and then in octal. And so when we run this, we see 255 FF, which is the hex, and 377, which is octal, just like we saw in the slides. So that's pretty straightforward. And now, like I said, sometimes if you see those two integers or those two series of numbers, you really don't know what the base is. So we can use the show base manipulator right here, as I'm using right here on line 18. And now when I run it, we'll see the base. So now we're going to see the 0x right here in front of the hexadecimal number and the 0 in front of the octal number, which is pretty nice. That way you know exactly what the context, right? So you know this is hex and you know that this is octal. And obviously, you know that this is a decimal up here. Okay. I'll tell you a funny story. A couple of years ago, I was interviewing a candidate for a C++ programming position, and he was an entry-level position. You know, you ask him to write code and to ask him some questions about the language. So I asked him to write a program that accepted an integer and converted it to a hexadecimal number. And every other candidate that I've ever asked that kind of question to goes off and writes a function and does all kinds of stuff. This kid went over, wrote the program in like 30 seconds and told me he was done, and I couldn't believe it. So when I went over there and just ran it, his output was correct. And what he did was this, which was pretty clever, right? All he did was ask me for the integer, did a std hex, and printed it out. It was very, very clever. Very bright kid. I never would have thought about doing that in an interview. But anyway, he got the job, and he did really well in the end. So that's a good way to think outside the box. Sometimes you don't want to go for the fancy algorithms. Just do it the easy way. I'm all for that. But anyway, so here now, what we're going to do is notice that, let me run this again so that you can see that the 0x and the FF here and the hex number are lowercase. If you need to have them in uppercase, we can use std uppercase, just like we are here on line 25. And when I run that now, you'll see that, oops, let me put that comment back. So when I run this now, you can see that now it's a 0xFF, and those are capitalized. That only applies to hexadecimal numbers because the hex numbers are the only ones that have letters in them. Okay. The show pos or show positive modifier right here. So let me uncomment this code out. And what this does, it only works with decimal values. And if the number is positive, then it displays the plus sign in front of the number. By default, we don't display a plus sign in front of the number. So let's run this, and you can see that right here on the 255, you can see that plus sign right in front of it. And that's exactly what that does. Notice that it has no effect on hex or octal. It only works on decimals. And in this case, there's a method called setF. And what we can do, and this isn't a manipulator, this is a method call. So we're saying stdcout.setF. So setF is a method. And then we can pass in these format flags. And what this will do is it'll set it to show base or no show base or uppercase or no uppercase, whatever you really want here. So it's an alternate way of doing what we did up here. Okay, and you tend to see this style more often than this style, but you'll see this sometimes out there. I just wanted to show you. Okay. Also, we can use std reset iOS flags to set these back to normal. So for example, this one right here, std iOS base field, that'll set your integer base back to decimal. Okay. Show base will set it back to the default for show base, which is not to show the base, right? That's the default. Again, remember, this resets it back to the defaults. This one, show positive, sets it back to not showing the positive, and the uppercase, it goes back to not showing uppercase. Again, so don't let that confuse you. We're not setting it to those flags. We're just telling it to set it to the default. Okay, so in this last example, I'm just using a real simple input statement. Let me uncomment that code out. And I'm asking the user for an integer, and I'm putting it right back into that num variable that we had before. And I'm just using default to display it as a decimal, and then as a hex, and then hex uppercase, and then hex again. And the point here is so that you can see that these settings stick. So this uppercase will still be uppercase, even though we've already used it, because they are persistent. And then no uppercase. And then finally, octal hex, we're going to show the base, and octal at the end. So again, really, really straightforward. Let me run it. And we can use a number like, let's say 135. And there you go. In integers 135. The decimal value is 135. In hex, it's 87. And you can see the show base here because I've got no show base, right? Because that was my default. Right here, I set it back to the default to not show base. And that's why we're not seeing it. Notice that when we're not showing the base, this uppercase has no effect at all, which is exactly what you would expect, right? So that's it. In the next video, what we're going to do is we're going to look at the manipulators for floating point numbers and see how they work. In this video, we'll see some of the stream formatting options available for floating point numbers. Formatting floating point numbers focuses mainly on the amount of precision used to display the number. By default, the precision is set to 6 digits. We'll cover the specifics of what that exactly means in this lecture. We can also set the number of digits to display to the right side of the decimal point. By default, there is no fixed set size. We can also choose to show trailing zeros up to a certain number, and we can also decide if the floating point number 4 should be displayed as 4, or 4.0, or 4.00, and so forth. But by default, these trailing zeros are not displayed. And then we have some of the same options that we had when we used integers. By default, a lowercase e is used when we're displaying floating point numbers using scientific notation, and the plus sign is not displayed when we display positive floating point numbers. All of these manipulators persist once they're set. So first, let's take a look at how precision works. By default, the precision used to display floating point numbers is 6 digits, and rounding always occurs. In this example, we have the number 1234.5678. If we display this number, C++ will use 6 as the default precision and start at the most significant digit, which is the 1, and it will display 6 digits starting from there, rounding at the end. In this case, 1234.57 will be displayed. If C++ can't display the number in the given amount of significance, then it'll use scientific notation, and we'll see that in a bit. Here's another example. We have a large number, 123456789.987654321. I did it that way just so it's really easy to keep track of these digits. If we display this number, C++ will try to do it with 6 significant digits, but this won't work, since it will display 123456, and the number displayed wouldn't be accurate. So in this case, the number will be displayed using scientific notation. And notice 1.23457 has got the 6 digits of precision. That's the default. And notice that we're still using precision 6, but this time using scientific notation. Suppose we wanted to display the number using precision 9. We can use the set precision manipulator where the 9 is the argument to do just that. In this case, the number will display as 123456790. Note the rounding at the end. Also notice how no trailing zeros are displayed in this example. So that's the way precision works when we're not fixing the number of digits to the right of the decimal. When we use the fix manipulator, precision is handled differently. Now we're looking at precision starting from the right side of the decimal point. In this case, we still have a default precision of 6, but we're also using the fix manipulator. This will use a precision of 6 starting with the digits after the decimal, and will round as necessary. So in this case, exactly 6 digits are displayed after the decimal point, and zeros are added if necessary. As you can guess, set precision 2 and fixed are commonly used to display currency amounts. We actually did this in a few of the course lessons. In this example, we're still using that very large number, but we're setting the precision to 3 and also using the fix manipulator. So now this will display exactly 3 digits after the decimal point, and rounding will occur. So we've got a 0.988 after the decimal point. In this example, we want to set precision to 3 and also use scientific notation. You can see the manipulators being used, and the display is exactly as we expect. 1.23 times 10 to the 8th. Notice the precision is 3, and we see that with the 1.23. We can display the E in the scientific notation format as a capital E by using the uppercase manipulator. Remember, by default, it's no uppercase. Now let's see how the show positive manipulator works with floating point numbers. The behavior is the same as we saw with integers. If we use the show pos manipulator, then we'll get a preceding plus sign on positive floating point numbers. Note that we can toggle back to not showing the plus sign with the no show pos manipulator. With floating point numbers, we can also use the show point manipulator. This will display trailing zeros based on the level of precision used. For example, if our number is 12.34 and we display it using only the defaults, then 12.34 will display. We're using a precision of 6, but only 4 digits will display in this case. If we wanted to add trailing zeros up to precision, we can use the show point manipulator. Now you can see that 2 zeros are added to the number being displayed. Again, you can use the no show point to toggle back to the default behavior. Finally, if you want to reset the floating point format back to the general format, you can do that in one of 2 ways. You can use the unsetF method, or you can use the reset iOS flag manipulator. There are a bunch of other flags, but at this point, you know what you would need, so rather than list them all here, I'll refer you to the C++ reference docs. Now let's head over to the IDE and we'll format some floating point values. Then in the next video, we'll finish off formatting with setting field widths, justification, and filling. Okay, so I'm back in the IDE again, and I'm still in the section 19 workspace, and I'm in the manip_floating project. And what we'll do here is we'll play around with some floating point numbers. Now let's take a look at the numbers that we'll be using for this example. We've got 3 numbers right here. They're all doubles. And you can see I've got one that's going from 1 up to 9 and then from 9 down to 1 after the decimal point. That'll just make it really easy for us to see which digits are being rounded. I've got another one that's a little smaller, 1234.5678. And I've got this last one right here, 1234.0. Okay. And what we'll do first is we'll just do normal displaying these guys out to the console with absolutely nothing fancy, no manipulation at all, just using pure defaults. And that's what's going on right here. On lines 14 to 16, I'm displaying num1, num2, num3. Now remember, by default, we've got 6 digits of precision. We're not showing the positive sign. We're not showing trailing zeros. And we're not showing uppercase letters in scientific notation. Okay, that's the default. So let's run this first. Now, what do we expect here? We expect num1 to not be able to work, right? I mean, if you think about this for a second here, you can see that num1 has, let's assume we wanted to display 6 significant figures right here. We would display 1, 2, 3, 4, 5, 6, and that would really give us problems, right? Because that's not even close to being an accurate number. So C++ won't do that. What it'll do is it'll display that number in scientific notation, and it will still use 6 for precision. I'll show you how that works in a second. Now this guy can be, right? There's 4 digits right here and then 2. So we expect those 6 digits to display, and those last 2 will be rounded. And this guy here, remember, by default, we don't display trailing zeros. So that's just going to display 1, 2, 3, 4. So let's run this and we'll verify that we got what we expected. Okay, so let me move this window over here so we can see what's going on. Let me do that again. There we go. So in this case, we're displaying num1, right? And notice what happens. 1.23457. You can see the rounding. You can see all 6 digits being displayed here. But we're using scientific notation because there's no way that it can be properly displayed, or accurately displayed, I should say, in 6 digits. This next one, though, num2, right, 1234.57. That's exactly what we expect. Here you see the 6 digits. And then num3, 1, 2, 3, 4 digits displayed. There's no .0 or .00 unless we use a modifier, which we'll use in a little bit. So that's the default. And it's really important that you understand the default and how it begins. So that's using the default settings. Now let's try something. We're going to set the precision to 2. So what we're asking for is 2 significant digits. It can't do that with any of these, right? 1.2, 12, where's it going to stop? So what it'll do is it'll display all 3 of them in scientific notation using a precision of 2. So I'll show you how that looks. And you can see exactly what's going on. 1.2 for all of them. Those are the 2 significant digits of precision, right? Times 10 to the 8th, the 3rd, and so forth. So now let's set a precision of 5. Now we'll be able to do some of them with a precision of 5, but others it won't. So I'll uncomment this block out. And let's execute that. And now you can see what's going on. Num1 cannot be displayed in 5 significant digits here. So the precision is going to be 5 digits here, but it's going to be in scientific notation. The other number up here, I'll scroll up so you can see it, 1234.567. There are your 5 significant figures here, right? Your precision is 5. So what it's doing is it's rounding that 5th one, which is 0.56 to 6. And then again, the last one is 1234. We're not adding any zeros or anything. So that's the default kind of behavior. So that really gives you an idea of what's going on. In this case, we're going to set precision to 9. Everything will fit here. So let's try that. And you can see what's happening with precision 9. I get 1, 2, 3, 4, 5, 6, 7. Instead of 89, I'm getting 90 because it's rounding that. This guy's displaying all of it because it can display all of it, right? 1234.5678. And the 1, 2, 3, 4 still displays the same way because we're not adding any zeros. Okay? So now you understand precision. Now let's talk about fixed and how it changes precision. So what we're doing here is we're setting precision to 3. You can see that happening right here on line 40. And we're fixing the decimal point. So now the precision happens after the decimal point. Okay, so let's run this and take a look at the output. Okay, so take a look at the output here. Again, I'll scroll up so we can see these numbers up top. So now we're displaying 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We're displaying all of that. And the precision now applies after the decimal. So notice that all 3 of these guys are displaying 3 digits after the decimal because that's the precision. And we're fixing that size. So it's going to round. In this case, 9876 becomes 988. And 5678 becomes 568. And in this case here, you can see that it's displaying all the zeros on the end. Okay, because we set the fixed formatter. All right. So hopefully that makes sense. Let me stop that and we'll run a couple more. Let's take a look at this example. What we're doing here is we're setting the precision to 3, and we want to do a scientific notation. So this should be very similar to what happened before with the precision 2 when stuff wouldn't fit. So again, precision is 3 and scientific notation. So what we get is right down here, 1.235. Notice the precision is 3, right? But what happened? Because it's fixed, I set fixed up here, and fixed is persistent, so it carries down. Even though I didn't say fixed right here, it's fixed because I've set it up here. So in this case, I get the 3 decimals after the decimal point, the 3 digits, I should say, after the decimal point, and it's all in scientific notation. And then a couple more examples. You notice that that E in the exponential notation, in scientific notation, was a lowercase e. I can make it a capital E by simply using stood uppercase here. And let's just run that to be sure that we get it. And there you go, right down here at the bottom, you can see 1.23, and you can see the E is capitalized here, whereas it was lowercase here in the previous example. In this case, I'm using the show positive. And what I'm doing is I'm just setting it to precision 3, fixed, and show positive. So this will show a positive plus sign in front of positive numbers. Let's run that. And then you can see down here at the bottom again, I'll move this up just a little so you can see it a little better. You can see the plus symbol being displayed in front of all these positive floating point numbers. If they were negative, obviously the negative sign would show. Now, we can set these guys back to the defaults, either by doing an unset F, calling that method, and we can pass in scientific and fixed, setting them back to the defaults. And what we're doing here is just a binary or we could use the reset iOS flags manipulator here and pass in show position, and that'll unset that. All right, so let me clean this up here. Now notice what I'm doing here. I'm setting precision to 10, and I'm telling it to show point. Okay, what this is going to do is going to add these trailing zeros up to 10 spaces, all right, or up to 10 precision. So let's run that, and we can see num1, num2, and num3. There you go. You can see right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. It's rounding here. And then 1, 2, 3, 4.567, 8. We've got a couple of zeros on the end, but you notice all of them now are in precision 10, right? And in this case, we have 1, 2, 3, 4 point and then 6 zeros at the end. We'll set these guys back to the defaults, and I'll show you how to do that right here. And then we'll run one more time, and we should get that same behavior we got at the very beginning. So what I'm doing here is I'm setting this back to the general notation here. I'm setting the precision to 6, which was the default. And I'm setting show positive and show point back to their defaults. And then I'm just displaying num1, num2, num3 at the end. And what we should get back is what we got at the beginning. So down at the bottom, here you go. We get the scientific notation for this guy. We've got the 6 precision digits here, and we've got the 1, 2, 3, 4 right here. Okay, so that's it. That's a good example of these floating point formatters. They're pretty powerful. They're pretty easy to use. In the next video, what we'll do is we'll learn about setting field widths and justifying things left or right. And you can use those along with these to really format tables and get your format looking really nicely for output. In this video, we'll see some of the stream formatting options that are available that work with any type of data. These are very powerful and easy to use. They give you the ability to define a field width and then display the next data item either left justified or right justified within that field. We can also specify the fill character that will be used to fill up any unused space. By default, there is no field width defined, and all output occurs right after the previous output, as we've seen already in this course. If you do set a field width, then the next data item displayed will default to right justified within that field width. It's important to understand that if you set the field width and justification, they are only applied to the next data item placed on the output stream. When we set the fill character, that will persist until you change it. Again, this all might sound really complicated, but it's pretty easy, and a few examples will show you exactly how it works. But first, let's look at the defaults. Here's an example that uses absolutely no stream manipulators or methods. This is the default behavior when you put data on a stream. As you can see, we're displaying the floating point number 1234.5678 and then the string hello. The number will display with 6 digits of precision, and it will round. And then hello is displayed immediately following the number. If we modify this program slightly so that it prints the number and the string each on a new line, then we get the number displayed as before on the left side with no padding up front, followed by the string on the next line. So far, this is what we've seen, and it should be pretty clear. So now let's set the field width of the next data item placed on the stream using setW. In this case, we're using setW with a 10 as a parameter. This will create a field width of 10 for the next data item only. In this case, that data item is num. Notice that num will be displayed right justified by default in a field width of 10. I'm displaying a ruler of numbers just above the actual display so that you can see the alignment. This ruler isn't displayed by the code. It's only there so you can better follow the examples. Notice that the last digit in number, the 7 in this case, is displayed in position 10. That's the rightmost side of the field width we set earlier. But now look what happens when we display hello. It displays right next to the number starting in column 11. That's because the field width and the justification only apply to the next data item placed on the stream. In this case, that data item was num. So hello has no field width associated with it, and it uses just the defaults. In this example, we set the field width of each of the 3 data items to 10. And remember, when we have a field width, the default justification is right. So in this case, num is displayed right justified in a width of 10. The first hello is displayed right justified also in a field of 10. And the last hello is also displayed right justified in a width of 10. And you can see from the display in the ruler exactly what's happening. This example shows how the field width only applies to the next data item put on the stream. In this case, we set a field width of 10, and we want left justification for the next data item, which is num. And we get what we expect. Num is displayed in a field width of 10, and it's left justified. Now we want to display hello. Notice that hello has no field width associated with it, so it will display starting in column 11. In this example, we'll set the field widths for all 3 items displayed. Num will have a field width of 10, and it will be right justified by default. The first hello will have a field width of 10, and we're explicitly setting right justification. We don't have to do this since it's the default, but we can do it to be very explicit. And the second hello will have a field width of 15, and it will also be right justified. You can see the output is exactly as we expect. Num is right justified in a field width of 10. The first hello is right justified in a field width of 10, and the final hello is right justified in a field width of 15. Now let's take a look at the set fill formatter. This only works when a data item has a field width associated with it. We supply the character that we want to fill any empty space in the given field width. Here's a simple example. We're setting the fill character to a dash with the set fill manipulator, and we're setting the field width to 10. This will apply only to num, which is the next data item on the stream. So we expect num to be right justified in a field width of 10, and the remaining space in that field to be filled in with dashes. That's exactly what we see. But what about the hello that we display next? We said that set fill was persistent, but we don't see any dashes with that hello. That's because that hello doesn't have a field width associated with it. So set fill only applies when we've set the field width. So let's look at one final example. In this case, we're setting the fill character to an asterisk, and then setting the field width of num to 10. We expect num to be displayed right justified in a field width of 10 and asterisk to fill in the remaining space. And you can see by the output that that's exactly what we get. Now we set the fill character to a dash and the field width to 10 for the first hello. We expect hello to display right justified in a field width of 10 and the blank space filled in with dashes. Again, that's exactly what we get. Then finally, we set the field width of the last hello to 15. We expect hello to display right justified in a field width of 15. And since set fill is persistent and the last hello does have a field width, we expect that those blank spaces will be filled in with dashes, and as you can see, that's what we get. So you see, it's really not that complicated and the rules are very consistent. Using the formatting manipulators that we've seen in the last few videos, we can have a good amount of control over how our output looks. Now let's head over to the IDE and we'll see these stream formatters in live code. Okay, so I'm back in the IDE. I'm in the section 19 workspace and I'm in the manip_fields project. And what we'll do here is we'll play around with the field width, the justification, and the set fill. You'll notice on line 7 here that I've got a function called ruler, and all that function does is just display a line of numbers, and that way we can line up our columns easier when we see them. Okay, you don't have to do this, but it just makes it easier to learn exactly what's going on. And then I've got these 3 data items here that I'm using. I'm using num1, which is an integer, and it's 1, 2, 3, 4. I've got num2, which is a double, 1, 2, 3, 4, 0.5678, and just a simple string hello. First thing we'll do is, just like we did in the slides, let's just do the defaults. So all we're doing is we're putting num1, num2, and hello onto cout. And when we run that, you'll see everything just runs up together. So let me build and run. And then we see 1, 2, 3, 4, that's the integer. And then 1, 2, 3, 4.57, rounded 6 significant figures here. That's our precision. And then the hello, everything jumbled up together, right? One right after the other. That's exactly what we expect. Okay, we can obviously, let me comment this code out. We can obviously display 1 on each line, and sure, that'll help us read it a little nicer because now we'll see each 1 on each line. But remember, the defaults are being applied. So we're getting 1, 2, 3, 4 as the integer, 1, 2, 3, 4.57, which is rounding to the 6th precision for the digit, and hello again. Now let's play around with the field widths. And here's a simple example. What we're doing is, again, we're displaying the ruler, and then we're setting the field width to 10 for the next data item that's being put on the stream, which happens to be num in this case right here. So num will be displayed in a width of 10. And if you recall, num is that integer, 1, 2, 3, 4. So that will be displayed in a width of 10, and the default is right justified. But then when num2 and hello are displayed, there is no field width associated with them. That field width only associates with the next item. So these two should print right next to each other and right next to num1. So let's take a look. And there you go. You can see 1, 2, 3, 4 right here. And let me grab my pencil and I'll draw in white. I think it'll be easier to see. You can see right here the 1, 2, 3, 4 right there. That's our integer. And that's the 10th, right? The 10th column. So it's being right justified in the 10th column. But then after that, we're seeing our double and our string all printed, run right next to the other, no formatting applied. Now let's do one more example. Actually, let's do a few more examples. Let's do this one here. And the source code's available to you. I encourage you to go in there and play around and change things around. That's really the best way to learn it. Okay, so now look what we're doing. We're setting the width to 10 for num1 and for num2. So now we expect num1 to be right justified in a width of 10, num2 to be right justified in a width of 10, and then hello with no formatting, just put right on the end of it, num2. So let's run this. And here down at the bottom, you can see that that's exactly what happens here. There's my field width of 10, and there's 1, 2, 3, 4 right justified in there. Here's the other width of 10 right here, the next field, and you see 1, 2, 3, 4, 0.57 right justified in there as well. And there's my hello. I'm going to put a couple of new lines at the end, just so that it'll separate that time elapsed message a little bit, so it'll be a little bit easier to see what's going on. And there they are. I just had them commented out. So I'll uncomment them. Okay, so let's take a look at this example now. I will uncomment this code. And notice what's happening here. I'm setting the field width to 10 for each one of those items. By default, we're going to right justify everything. So num1, num2, and hello will each display right justified in a field width of 10. And let's give that a run. And there you go. You can see 1, 2, 3, 4, the integer in the field width of 10. 1, 2, 3, 4, 0.57 in its own field width of 10. And hello, you can see the 0 right there, right? That would be the 30th column, the third field width of 10, and it's right justified. Comment this out and see what this is doing. Now, this is doing exactly the same thing, except we're left justifying each one of these. Now, remember, we want to left justify them, we have to say it explicitly. Right justified is the default. I always like to put in left and right. That way, whoever's reading my code afterward understands exactly what's going on. Even though we know it's the default, somebody might have forgotten. So it's nice to see that there. So here, width of 10, left justified, num1, width of 10, left justified, num2, and width of 10, left justified, hello. So let's give that a run. And you'll see the difference between this guy right here where they were right justified and now down here where they're left justified. So you can see that 1, 2, 3, 4 is displaying in column 1, 1, 2, 3, 4.57 in column 11, and hello in column 21, just like we expect. Okay, so now let's do a couple with the set fill, and I'll comment this out and we'll walk through this in a minute. So notice what I'm doing here. I'm setting the fill character to the dash. Now this is a persistent setting. This will persist until I change it. And what I'm doing here is I'm setting the width to 10, left justified num1. Now num1 was only 4 digits, right? So the rest of the space in that field of 10 is going to be padded or filled with that dash character. And the same thing will happen to these guys. Remember, if we don't have a width set, then the set fill doesn't apply. It only applies when we're setting the field width. So in this case, we expect to see all 3 of these guys left justified in a field width of 10, and all the spaces that are left over, all the blank spaces in that field of 10, filled with dashes. So let's take a look. And there you can see right down here, you can see 1, 2, 3, 4, and then dashes all the way to the 10th position. And then 1, 2, 3, 4.57, dashes all the way to the 20th position. And then hello, and dashes all the way to the 30th position. Okay, had we right justified them, the dashes would have been on the left. It would have filled any empty space in that field width. And the last example is we're using different set fill characters. So we're setting the field width to 10 for each one of them again, and we're left justifying. And in this first example for num, I'm using the asterisk as the fill character. For num2, I'm using the hash mark or the pound symbol. And for hello, I'm using the dash. We should see 3 different fill characters filling up all that space. Remember, once this statement is done, this is the fill character that's set, so that's going to persist until I change it otherwise. All right, so let's run this. And there you can see that I'm using the asterisks for the first field, the pound signs or the hash symbols for the second field, and the dashes for the final field. Okay, so that's it for this video. In the next video, we've got a challenge where we're going to put some of this stuff together to display a table. Now you get a chance to play with them and put them together and understand how you can use your precision, your left, your right, your fixed, and so forth all together to create a table of tour prices for trips to South America. So that's the challenge coming up in the next video. Welcome to the first challenge for section 19. This challenge is all about using what you learned about formatting output to format a table of tours to different cities in South America, including prices and so forth. And we'll get to that in a second. But I'm in the section 19 workspace, and there are two projects. Challenge_1 is the source code that I'm providing for you, and challenge_1_solution is my solution to the challenge. So let's take a look at what the challenge is all about. Then I'll give you a sample run, and then you can try it out on your own. So as I said, it's about formatting output, and we're going to do everything to cout. We're going to display everything to the console. Later on, we can change that and display to files, and that's what we're going to learn next in this section. So let's start. I'm giving you the starter source code for the challenge, and I'll go through that in just a second. But the challenge is for you to display the provided data in a nicely formatted table. Your table doesn't have to match mine. You can do however you like. The point is for you to become comfortable with these manipulators. Play around with them. Don't just try to mimic my table exactly. Be creative. Do your own thing. So I'm going to give you three structures. We haven't really done these sorts of structures before, but they're really, really straightforward. They're not classes. We're going to use structures because we don't really need to model operations. We just want to model data. And when we're modeling data, it's really common to just use structures. Again, I'll show you what they look like in just a second. So the first thing is these structures work together to create a tours structure. And that's going to contain information about tours to South America. And the tours include the countries that you can visit, the cities within those countries, and those cities have population and cost data associated with the tour. I know population, I was thinking the same thing. I just wanted a really big number so that you could format it. Watch the challenge video, which you're obviously watching right now. But if you're looking at the code, I'm hoping that you come back to this video and watch it so that you can see what the expected output looks like. I tried to copy the output to this document here, but everybody's got different fonts, and some of the fonts aren't monospaced, and the document would look really weird. So I'll just run it for you so that you can see exactly what it's supposed to look like. In the code, I'm going to give you some starter code that displays all the data from these structures and vectors using tabs to kind of align things, and it looks pretty ugly. But your job is to clean it up, make it look pretty. Okay, so as I always say, have fun, create functions, constants, do whatever you think makes sense, explore, play around, do it, and then do it again a different way. That's how you really, really learn. Okay, so let's go to the source code. So again, I'm in the challenge_1 project, and I'm looking at the main code right here. And let's go over these data structures. First of all, what we've got is we're including our normal group here. We've got IOStream, we've got IOmanip, since we're going to use the manipulators. We've got a vector, and we've got a string. And we've got these three structures right here. Here's the first one. It's city, country, and tours. And let me start with city. Think of a struct. We talked about a struct a little bit earlier in the object-oriented classes and methods section. It's like a class, except everything's public. You can have constructors. You can have all kinds of stuff. But typically, we use structs like this to just model data. Sometimes you just want pure data, and you don't want to deal with constructors and methods, and you really don't need any of that. So this is just a good way to collect data together. So what we've got here is we've got a city. And each city has a name. So let's say the name for one of the cities is Bogota in Colombia. A population, which is a long, and I don't know how many millions there are. I made some of those numbers up. Let's just say 18 million or something like that. And the cost of taking a tour to Bogota from Miami. So that's $569. And again, I don't know what that number is. It's in the data you'll see in a minute. So that's a city. We're going to have many of these cities, right? We'll have Rio de Janeiro. We'll have Santiago, Chile. We'll have a whole bunch of places that we can visit in South America. Each one will be modeled by a city. Perfect. Now, let's look at the country. The country has a name. In this case, it would be Colombia. Right? And it has a stood vector of cities. Okay. So I might have 3 or 4 cities associated with Colombia. I might have 2 or 3 cities associated with Brazil and so forth. So this is how we structure our data using these structures, building one within the other. Finally, we've got our main object here, which is the tours, and it has a title. And that title, I don't remember exactly what it is, but I'll show it to you in a minute when I show you the data. It's something like tours to South America or something, some big title that'll be the header on our report. And the tours has a vector of countries. Okay, makes sense? So we could have the title, which is this guy. And then we could have, let's say, Colombia, and we could have Brazil as our countries, and we could have Argentina. And then the countries have cities within them. You can see them right here. So you may have Bogota here, and the population is 18 million, and the cost is $567 or something like that. Then you would display the next city and the next city. Then you'd go to Brazil and you'd display Rio and so forth. So this is what our report is going to look like. And the reason we structure this data is because it makes it so much easier to process that way. We don't have to just play around with hundreds of arrays and strings and so forth. So we're using what we should be using. We're using stood strings and we're using stood vectors. I mean, that's what modern C++ is all about. It's not using character pointers, and we're not using anything else, just real solid data structures. Okay, so how do we initialize these guys? Let me scroll down just a little bit. And here you see some of the initialization. And this is done for you. I've already written this for you. You could just use it. You notice that this piece right here, and this is using our uniform initialization, right? This is the kind of stuff we've been using all along, except we're doing it all in one shot here. So here is a city. Here's another city. Here's another city. Here's another city. These 4 cities are a vector. And that vector is the vector of cities in that country, Colombia, right? And that country, Colombia, is one of these guys. And here's the title at the top of the tours. So all we're doing is we're building this using uniform initialization, which makes it really, really nice to visually see what's going on here. So you could see that I've got, let me scroll up just a little bit here. So hopefully we can see them all. Yep, I think we can see them all. Great. So in this case, there's my title. Okay. Here is a country, another country, another country, another country. Okay, I don't know what happened to my mouse. It all of a sudden got really big. Let me fix that real quick. And within those countries, I've got cities and cities and cities, and here's a single city. You can always assume that there must be, if you've got a country, you must have a city. So you can assume that you're never going to have a country without a city. That'll just make your processing a little bit easier. That's it. So that's our data. And let me show you how you would work with this data. So let me scroll up and clear this a little bit. Here's the code I'm giving you. And you may not see it right off the bat, but it should be pretty intuitive once you start walking to it and thinking about it a little bit. You can see what we're starting out here. We're displaying the title. The title is part of that tours object, right? Tours.title. And then for each country that's in the countries in that tour object, so we're going to loop through all the different countries, right? Colombia, Brazil, Argentina, and so forth. For each one, I'm displaying the name. And then I'm looking through that city's vector that's inside of it. And for each city in that city's vector, I'm displaying the city. That's really it. It's really, really straightforward. Again, take a minute, understand the concept, walk through this. Before you start trying to format this data, make sure you understand how we're getting the data. It's real important. Once we do that, we can display this information. It's not going to look very pretty because you can see we're using tab characters to kind of align these columns, and it's not going to do a real good job, but at least you'll be able to see what's going on. If I run this now, it'll be the output that you should be getting as well. So let me run that project right now. That's what you should get. Tour ticket prices from Miami. You can see Colombia and the cities, Brazil and cities, Chile and Argentina. But you can see this isn't lined up nicely because we're not doing any real formatting. We're just using the tab character. Okay, so let me stop that and then let me show you the solution output. Looks something like this, which is much nicer. And I'm displaying this ruler up here. I'm doing this in a width of 70 total. You don't have to do that. That's just what I chose because it's easy to see. You can see here I'm displaying tour ticket prices from Miami centered. There's no way to center something. Remember, when we use the set width and the justification, we can only do left or right. So centering it, you're going to have to do maybe a little bit of math and figure out what's the center. Now I've got a header here where I'm displaying the country, the city, the population, the price, a line of dashes, and then I'm just lining up the data. So I've got all the countries, Colombia, Brazil, Chile, Argentina, the cities within the countries, the population of those cities that's right justified here in this field, as well as the price, which is right justified, and I've got the 2 decimal digits displaying. Okay, so that's it. Good luck with this one. Again, this project, this little challenge is more than just formatting. I really want you to understand the structures and how you access those structures using the vectors within the structures. It's really simple once you get it, and it's really powerful to be able to use those structures that have those vectors of structures within them. Very powerful, very easy to use. You saw how easy it was to declare the data. Okay, so that's it. Good luck with the challenge. I'll see you on the other side in the solution. Don't rush through this. Take your time. Once this challenge is over, we'll start working with files. Hello, everyone. Welcome back to the Section 19 Challenge 1 solution. I'm in the Section 19 workspace, and I'm in the challenge_1_solution project. I hope you found this challenge challenging. There was probably a couple of pieces that were kind of tricky. One of them had to do with displaying the country right next to that city the first time around, and I'll talk about that in a second. The other one might have been trying to center that title. So we'll go over both of those. Here are the structures again. Here's my city, my country, and my tours. I've got this simple function called ruler, which I'm just going to use one time at the very beginning, just so we can look at our alignment. And then I've got my structure, which has been initialized here exactly like I gave it to you. So the first thing I want to do is I want to look at my data, and I want to kind of look at the sizes of the data, make sure that there's nothing like a city that's got 30 or 40 characters in it. That way I can gauge what kind of field widths I want. So that's what I did. And what I've done here is I've decided to go with a total width of 70. And the reason I did that was just purely console based, because some terminal windows and some DOS windows and some shell windows, which is where we're running these programs, are 80 max. So I didn't really want them going over the 80 and then wrapping over and really making it ugly. So what I decided to do was keep the total width of the entire report to 70 characters. Okay. So 70 is our goal here. And then we've got 4 fields, right? We've got the name of the country, the name of the city, the population, and the cost. And obviously we have a title up here centered somewhere. And I'll talk about the title in just a second. So the way I decided to do this was to create 4 field widths, and I'm going to make constants from all of these guys. That way I don't have to use my numbers everywhere. I can just use these names. And if I ever need to tweak anything, I can just come here and tweak them, and it should be good to go. So 70 is the total width. My first field is a width of 20. So let's say that this is my first one here. Let's say that this is another 20 here. And then my last 2 are 15, which are a little bit smaller. This isn't to scale, but you get the idea. So this would be the country's name, right? So this would say, let's say Colombia would display here. And then the city would be over here. The population, and both of these guys, I'll just draw arrows here, will be left justified in that field width. Then I've got the population, which is a number, which will be right justified here. And I've got the cost, which would be some number with 2 decimal points on the end, and that's going to be right justified here as well. Okay, I've got a header over here, which is going to say country, city, population will be right justified over here, so it lines up. And over here, cost will be right justified. So that's sort of the structure that I've got in my mind. And I can tweak this as I go. Okay, so that's really pretty much it. Here are my field widths that I've defined. So again, 20, 20, 15, 15. We add them up to 70. So I know that I'm in the ballpark. Let's deal with that title. So I'm going to erase this real quick. And I'll scroll down just a bit. And what we want to do is we want to display the title. Now you'll notice on line 71 down here, I'm displaying the ruler. That's just going to display that series of numbers so that we can line things up. But let's talk about the title and what kind of algorithm we want. Again, we've got 70 for our total width of our report. And suppose I wanted to display something. Well, obviously the center here is 35, right? That's pretty clear. And suppose I wanted to display something that was 10 characters wide, a string that's 10 characters wide. The idea would be that I'd want to display 5 of those characters on this side and 5 on this side, right? That would center that string. if the string was 20 characters wide, I'd want to display 10 over here, and I'd want to display 10 over here. That way we know that that string is always centered. So we've got to do the math that lets us do that. And it's pretty straightforward. If you think about this, notice here, if the string is 20 large, right? We want 10 on this side, 10 on that side. And if 35 was the center, that means we really want to start printing that guy at 25, at column 25. And if the string was 10 characters big, we want to print it at 35 minus the 5, which is 30 right here. Okay, so that's really what my algorithm is going to be. Let me clear this because it's a little messy. And I'll do it one more time with an actual example. So here's the 70. We know we're at 35. And I want to display a string that's 40 characters wide. Okay, so what do? How do I figure this out? Well, I want to display 20 of them and 20 of them, and I want to line those up, right? So 35 minus 20 gives me 15, and that's where I want to start displaying that string. So how do we do this? You take the total length, which is 70, you subtract from it the length of the string that you want, which is 40. That gives you a 30. And then you divide that by 2. And that gives you the 15. That gives you exactly where you need to start displaying the string so it's centered. Okay, let's do another example. Suppose the string is 20 big. I need 70 minus 20 divided by 2 gives me 25. Does that make sense? Well, let's see. If it's 20, I want to do 10 on this side and 10 on this side. 35 minus the 10 is 25. Exactly right. So my algorithm makes sense, and it's really easy to implement. Let me show you how to do it. I'm going to scroll down just a little bit and we'll do the header right here. So what I'm doing here on line 72 is I'm determining what is the length of that title string. Well, where's the title string? It's in tours.title. I just want the length of it. Whatever that length is, I'm going to subtract it from the total width, divide it by 2. That's where I want to start displaying tours.title. But how do I do that? Well, it's really easy. I can set a width to that amount and just display an empty string. Remember that the set width applies to the next item that's being put on the stream. There it is. I'm not putting anything. It's just an empty string, but it's still going on the stream. Okay, so that should take care of centering that. And then the rest is pretty easy in this context, because what we're doing here is I'm setting my field width for the country to field 1, which is 20. Right? I'm justifying left, and I'm displaying country. So field width 1, which is 20, is going to be left justified, and right there is what I'm putting on the stream. So country, that string, is going to be left justified. Then field 2 is 20 again. Then I've got 15, 15. I'm doing the 2 left and the 2 right, just like I did before. And then I've got a new line. So that should display the title centered and my headers, those 4 names, right where I want them. The next thing I need to do is I need to do a line of dashes, right, to separate my my header from the content. And I want 70 of those dashes. I could just say, see out a big string of 70 dashes, right? But if I ever change my total width, then I've got to change that as well. So what I can do here is I can simply say, set the field width to the total width, that'll be 70. Set the fill character to the dash. And that's what I want to display, which is just an empty string, but it doesn't really matter because it's going to fill up everything with the dashes and then give me a new line at the end. That's it. Let's run this and we'll see where we're at. And there we go. You can see tour ticket prices from Miami, that's centered. I've got my country left justified in 20, my city left justified in 20, my population and my price both right justified here in 15. And if you count them, you can actually see that it's all lining up just right. And there's my dash line of 70. Okay, in this case, 70. If I change total width to 80, it'll do 80. If I change it to 40, it'll do 40. That's the nice part about using those consts. Okay, so that's it. Now we need to get into the body of the report. Before we do that, let's do a couple of things here. This is important right here. Let me go back to where I was. Here we go. I want to uncomment these 2 lines out. Let's talk about these for a second. Okay. I want to set my fill back to blank. right? Remember, I changed the fill right here, and that's persistent. So I don't want to keep it that way. Otherwise, I'm going to get dashes all over the place. So I want to set it back to a blank character. And I want to set the precision to 2 and fixed. And that's basically for this guy right here, for the price. I want to be able to make sure that I've got 2 digits to the right side of the decimal. Okay. I only need to do that one time, and then we're good to go. And now comes the logic for actually displaying the data. And this is it. This is all there really is to it. There's a couple of tricky parts here, and I'll talk about that in a minute. But let's just talk about the outer loop first. Here's the outer loop. My collection is tours.countries, right? So each time I go through there, I'm going to grab a country structure. And each one of those country structures has city structures within it, right? So that's the idea, a vector of cities. So in this case, for each country in tours country, I want to execute this inner loop. And now this inner loop, we could have done this a lot more complicated, a couple of different ways to do this. I chose to do it a simple way with just one standard out statement right here, one C out statement that kind of does everything. But the only thing that's different here is, and let me make a little room down here so I can show you what I'm talking about. In the report, we could have done something like this. We could have said Colombia, and then the cities down here, Bogota, the population, the amount, and Cali, and the population and the amount. I didn't want to do it that way. I wanted to do it where this guy is down here, right there, right next to the first city. So it looks more like a report. Here it kind of just leaves all this empty space here, which I didn't like. But in order to achieve this, you've got to do a little bit of extra logic to do it. So let me show you what I did. For each one of those cities, remember, outer loop is the country. Inner loop is we're looping through the cities vector in the country. So each time we loop in here, we're going to get a city. So what we're going to do is the only time that we want to display, let me write that again. The only time that we want to display the city and the country is that first time, right? That very first city is going to be different. The second city, I just want to display it like this. I don't want to display Colombia again, or I don't want to display Argentina again. Make sense? Okay, so what we're doing here is we're looping through the cities vector, and I've got my width set exactly like we did before, left, left, right, right. None of that changes. The only difference here is this one line of code right here. This is using the conditional operator. Now, if you remember the conditional operator, it's an if-else statement built right into an expression, which is kind of cool. So here, I've decided to use a for loop, not a range-based for loop, but a regular for loop, because I need to know when I'm at the first one. The first one will be when I is 0. So notice what's happening here. When I is equal to 0, I am displaying the country's name. That's what I want. When I is not equal to 0, that means that I've already displayed the country's name. I'm displaying cities now. Then I just don't want to display anything on that line. Make sense? So the first time through, I'm displaying the country, and then the city, the population, and the cost. The city, population, cost. The next time around, I will not be equal to 0, right? So I'm just displaying a blank. So I'm not displaying anything here, but I am displaying these 3. Okay, so it's just a nice little way to do this. That way you don't have to write multiple cout statements depending on all kinds of conditions. Okay, so that's that first one. The rest are really simple, right? Grab the city at I, or the name of the city at I, the population and the cost. We're just looping through that vector, grabbing the fields that we want. And simple as that. Now, there are different ways to do this, and we'll learn how to do this when we talk about the standard template library using iterators, which is much nicer than using these loops. But when we get there, we get there. That's it. Let me run this, and we'll verify that it works. And there you go. And you can see right here, this is exactly what we wanted. You can see Colombia's here. Then I'm printing out that city right next to it. And then on the second city, I'm not displaying Colombia again. Okay. If you did it this way, great. If you didn't do it this way, you just wrote a blank line here and then you started with the cities underneath, that's fine too. I just think that this report looks nicer this way. All right, so that's it. You've got a whole bunch of stuff to look at here. Hopefully your solution was close. If your solution was better or quicker or more efficient, or you used a different kind of looping construct, post it in the forums. You don't have to post the whole program. Just post this piece here, this loop right here, because that's really the interesting part. The rest of the data is all same for everybody. Okay, so in the next video, we'll start talking about files. In this video, we'll talk about the steps needed to read input from text files using C++ streams. In the following slides, I'll talk about the main classes and methods that we can use to read from files. And then I'll go over a bunch of examples in live code so that you can see alternative ways to read text data from files, depending on the type of data we want to read. First, we'll talk about input files and reading from them. And then in another video, we'll discuss output files and writing to them. The two classes that I'll discuss for text file input are fstream and ifstream. There are a few steps that we must always perform when we read from files. The first is to include the fstream header file. Then we declare a stream object of either fstream or ifstream type. We then connect the stream object that we just created to the file that we want to read from on our file system. File systems are very different, so we have to be sure that we get the file name and the path correct. I'll talk more about that later. Once the file is connected and open, then we can read from it. There are many different ways to read from a file. We can read in binary mode, we can read in text mode, we can read one line at a time, one character at a time. We can use methods like getLine. And we can use the extraction operator like we've been doing with cin. Then when we're done processing the file, we have to close the file. This should sound pretty easy, and for the most part it is. In the next few slides, we'll discuss the details of opening a file, checking to make sure that the file was opened correctly, reading from the file in various ways, and then closing the file. So let's get started creating the stream object. In this example, we're creating an object named inFile. And we're using the fstream class as its type. Notice that I'm initializing the object as well. The initializer takes two arguments. The first is the name of the file. This can sometimes be very operating system specific and also very IDE specific. In the CodeLite IDE, we always open our files one directory up from where the executable lives. That's why we're using .. before the file name. I'll talk more about file names in the live code session. And I'll also include a video at the end of this section that talks about the file paths used for some other IDEs. But for now, let's assume that the file is where it's supposed to be. The second parameter specifies the mode and any other properties of the file that's being opened. In the first example, we're using std_ios_in. This means to open the file in input mode, so we're able to read from it but not write to it. By default, files are opened in text mode. In the second example, we're opening the file in input mode and in binary mode. This is necessary when reading non-text files that contain binary data. We won't be doing that in this course. We'll work strictly with text files. Notice the vertical bar or the pipe operator between std_ios_in and std_ios_binary. This is the bitwise OR operator. When used with bit fields such as these, it sets both the input and the binary modes to true. At this point, the file will be opened if it was found. In this slide, we used the fstream class. The fstream class can actually open up a file for reading and writing at the same time. We won't be doing that, but if you have a file that you'll use only for input, it's more common to use the ifstream class. Let's see that in the next slide. In this slide, we're using the ifstream class as the type for infile. ifstream is used for input files only. We can create an ifstream object the same way we created an fstream object. However, in the case of an ifstream object, the std_ios_in is optional since it's already the default. So the first two declarations of infile have the same effect. The last declaration opens infile in binary mode. There's another way to open a file that's commonly seen in code, so let's take a look at that next. In this example, notice that we're creating infile as an ifstream, but we haven't provided any file name to associate with it yet. This is a common use case since many times we don't know the file name and we have to get it from the user or from some other source at runtime. Once we have the file name, we can then use it and use the open method on the stream object to open the file. So we can say infile.open and provide the file name, or infile.open, file name, and then any flags we need to set. Now that we attempted to create the stream and connect it to a file, we have to be sure that this was successful before we start reading from the file. So let's do that next. So we have to be sure that the file was opened successfully. Maybe it wasn't found or there was some sort of hardware or permission issue. There are a few ways that we can check to see if the file was opened successfully. We can call the isOpen method of the file stream object that we created. This will return a Boolean indicating whether the file is open for processing or not. If we get back true, we're good to go. If we get back false, something happened and we can't read from the file. In the case of this error, what do? Well, it depends on the application. We might just display an error message and terminate the program. We might see if we can somehow recreate that file from a backup. It's totally application dependent. In our examples, we'll simply display an error message and terminate the program. If there was no such error, then we can go ahead and read from the file. Now let's see another way that we can test to see if the file was opened successfully. In this case, we can simply test the stream object itself. If we couldn't open the file, then this will return false, and then we can decide what to do. Otherwise, it's good and we can proceed reading from the file. But let's talk about the last step first. That is closing the file. Once we finish reading from the file, we must close it. This is a simple method call to the close method. With input files, it's not so critical. But when we talk about output files, closing them is very important. Okay, so now that we know how to open a file, check to make sure that it's open, and close it, let's do the part that's the most fun, reading from it. There are many ways to read from a file. In these examples, we'll be using text files. We can read formatted data from the text file using the stream extraction operator. Remember that one. We've used it all along with cin to get input from the keyboard. Well, now we can use it again to get input from the file stream. In this example, let's suppose that we have an integer, a double, and a string in a text file, and we want to read these into our programs. You can see the text file's contents in the little box here on the slides. We can assume that infile was created successfully. Notice that we create three variables. Num is an int, total is a double, and name is a string. Now we can read from infile using the extraction operator. The first statement will read 100 and store it in num. The second statement will read in 255.67 and store it in total, and then read Larry and store it in name. That's it, simple as pie. We can have these three separate read statements on a single line. We can chain them all together, just like we did when we worked with cin. Sometimes we want to read files an entire line at a time, and we know that the extraction operators will stop when they see any white space. So in this case, we can use the getLine method. Remember that method? We used it when we read lines from the keyboard using cin. In this case, suppose our file contains the string, "this is a line." We create a string object called line, and then we use getLine with the name of the stream we're reading from and the string we're reading into. That's it. An entire line of text up to the new line will be read from the file and stored in the string named line. Reading a single line from a file isn't too useful unless the file only has one line, but usually files have many lines of text. So let's see how we can wrap this up in a loop to read all the lines in the text file. Here's the sample code. We can assume this code is in main and all the necessary header files have been included. First, we declare infile as an if stream, and we connect it to myfile.txt. We also declare line to be a string object. That's where we'll store each line that we read from the text file. Okay, so first, let's make sure the file was opened successfully. You can see in the if statement that we're checking to see if not in file. Not in file will be true if the file was not opened successfully. And if so, we display an error message and we return something other than 0 and our program terminates. Otherwise, we have an open file and we can start processing it. We'll read the lines from the file in a while loop. And while we're in the while loop, you'll see the condition while not in file.eof. EOF is a method that returns true when we reach the end of the file. So we're looping while we have not seen the end of file. At each loop iteration, we use getLine to read from inFile and store an entire line of text into line. Then we display line to the console and we iterate again. At some point, we'll reach the end of the file and the loop terminates. Then we close the file and we're done. So as you can see, this program will read a text file from some file on disk and display its contents to the console. Pretty easy. Now let's see a variation of this program that does the while loop condition a bit differently. In this case, the loop is while getLine inFile line. At first, you might think, what's going on there? Well, we can embed many of the string input statements right into the while condition. We can also embed statements that have the extraction operator in there. Since these statements return a reference to the stream object, they'll only return a true value when the read was successful. So when we reach the end of file or some other error condition is encountered, they will not return true and the loop will terminate. You can write code either way. Okay, so one more example and then we'll see some examples in live code in the next video. In this example, we're again using inFile as an ifstream object, but this time we're reading the file in an unformatted manner. In other words, one character at a time. Sometimes this is very useful since the extraction operator, getLine, and other methods depend on white space or new lines to be able to work correctly. Unformatted input reads one character at a time regardless of what that character is. The code in this example is exactly the same, except that in the while loop condition, we're reading a single character into the variable c with the get method. Then we simply output the character. So as you can see, this example also reads a file from disk and displays it to the console, but it does it in an unformatted manner, one character at a time. Okay, so in the next video, we'll head over to the IDE and we'll read some files, and I'll talk some more about those file names. In this video, we'll go over some examples of reading text files. So I'm in the section 19 workspace and I'm in the read file _1 project. And right now I've got nothing in here. The only thing I've done is I've included IOStream and I've included fstream. We obviously need to include fstream to work with files. That's all I've got. Here is my project. You can see it's open and the file that I'm going to read is not there yet. I wanted to show you how to create it. First thing we want to do is let's write the code to open the file. Then it will obviously fail because the file is not there. And then we'll put the file in there and we'll read it. Okay, so first thing we need to do is we need to create an input file stream, and we'll just call it inFile, just like we've done in the slides. And I'll initialize it on the next line. I'll open it on the next line. That way you can see that kind of syntax. So we'll say inFile.open, and here we give it a file name. Now this is the part that's pretty operating system specific. It's IDE specific. If you're in Windows, you might be tempted to do this kind of thing. C:/ and then some directory and then some other directory, maybe followed by some test.txt or something like that, right? That's the way that Windows file names look. The problem with this is, you remember that character literal that starts with a slash, that won't work because that right there becomes a character. So what we want to do, if you do it this way, you want to use 2 slashes. Don't forget, that's really, really important. You would want to use 2 slashes everywhere if you're on Windows. Now, if you're on Mac or Unix or some other operating system, then you really don't do that. You kind of just, slash, // directory names to the file. Now, the good thing about this is even if you're on Windows, you can still use this slash, and behind the scenes, it'll be mapped to the proper one. So that's what I would recommend you do. I would not recommend that you do anything like C: or D:, because that really, really ties your code to your computer. So for example, if you're trying to open a file in C:/frank/test, and then someone else tries to run this program, unless they've got a frank directory, it's not going to work. That file won't be there. So the best thing to do is just to do something like that. That way it'll look in the current directory, no matter what computer system you're on. Now, this is where the IDE issues come in, and I'll talk about that a little bit. For now, let me just leave that just like that. I want to open a file called test.txt. It doesn't exist yet here, as you can see, but we'll worry about that in a little bit. So we're trying to open that here. The next thing we need to do is we need to see if it was open. So let's say if not in file, And remember here we could have said if not in file dot is open, like that. Either one will work. This is the style I like, and that's the one I've been using a long time, and I'll keep using it. So if not in file, that means we could not open this, okay? So in this case, we're just gonna say std c error. We're gonna display an error message that says opening file, let's say. Just something real simple like that. What do we do here? I want to get out of here. I've got nothing else to do. I need this file to run my program. So I've got a couple of options. I can say return anything other than 0. 0 means the program completed successfully. I could return a 1. I could return a -1. It really depends on what number you're looking for. That means I couldn't find a file. So I'm just going to say return 1. Sometimes you'll see code that looks like this. It says exit 1, or more properly std exit. And in this case, that calls a function named exit that closes up certain things and destroys static variables and things. But right now, I'm just going to simply return 1 if I'm having some sort of problem opening the file. Now, if I get beyond this piece right here, I've got the file. It's good to go. So I'm just going to say std cout. File is good to go. I'm ready to read from it. That's it. That's the program. This will fail when I run it. So let's try it. I'm going to build and run. And it says problem opening file. How come? Because the file's not there. Okay, so let's create the file. What I'll do is I'll come in here into my project and I'm going to click on the source directory. This is what I would recommend that you do. Whatever files you create them in the same directory where your .cpp files are. Okay, so in this case, I'm going to put it right where my main CPP file is. I'm going to right click on that source folder and I'm going to select add new file. You could also do it from up here, add new file. And then I'm going to select any file and just give it a name. And I'm going to give it this name right here, test.txt. So I'm going to say test.txt. I'm going to press enter. And now you can see that test.txt file right here. And I can type some data into there, and I will in a moment. So now I've got the file. So now let's run it. Still a problem opening file. How come? Well, this is where the IDEs are all different. If I open this file up, right, this project up right here, I'm going to right click on it and I'm going to say open the containing folder just so I can open it up in Explorer here and look at it. Let me move it over from my other monitor. You can see that here's my C++ source file right here, my CPP file right there. And here is that test.txt file I just created, right? But the executable's not here. The .exe file is not here. It's in debug. It's right here. That's my exe file, the application. So when it runs, it's looking for that txt file in here, and it's not finding it. That's why with CodeLite, we have to do something like this, .. So in other words, I'm in debug. I need to go one level above, one directory above me. Now, if I try to run this, file is good to go. It found it. Usually, this is what you want to do. Most IDEs will work this way. CodeLite does not. I believe Code Blocks and Visual Studio will all work if you just type in the file name just like that. And then what you do is when you create your file, you create it where your CPP file is, and it'll find it. Depending on what IDE you're using, you're just going to have to play around with it until you get it and it opens it, and then you're good to go. Okay. Xcode, if you're using Xcode, we'll talk about that in the video at the end because Xcode is a little bit different. CLion, just a regular test.txt will also work. Okay, so that's it. So now we've got a file, we're able to open it. So that's perfect. That's the first step, right? If we can't open it, we can't read it. So I'm going to get rid of this file is good to go statement. I really don't want to say that again because I've got it. Now what I want to do is I just want to read some information from that file. So let's put something in there. I'm going to go into test.txt and it's just a text file. So I'm going to say hello. That's it. I just saved it just now and I'm going to go back to main CPP and I'll create these variables up here just so they're all in one place. So let's create a string and let's just call it line. Okay, just any variable name will do. And down here, what I want to do is, remember when we had cin, we would say cin into line. Well, it's the same thing, except we're not reading from cin, we're reading from infile. So what that'll do is it'll read one string. Right? It's going to remember the way the extraction operator works. It'll stop at a space or at end of file. It'll stop as soon as it sees some white space. Now we should have that string in line, and we could just simply display it right to the console. Okay, so let me go through this again before I run it. I'm opening the file. I'm testing to be sure that it's open. If it's not open, I'm displaying problem opening file, and I'm out of here. Otherwise, I'm reading from the file into line. Line is a string. And then I'm displaying whatever I just read. Remember, the file contains hello, so that's what I should see. Right? So let's give it a run. There's hello. So that came from that text file. Okay, so now what we'll do is, let's read a couple of other things in here. So I'm going to have an int. We'll call it num. And we'll have a double. And let's just call it total, just like we did in the slides. So now, what we'll do is we'll modify that file here so that it's got a string, an int, and a double. It's already got a string. So we'll give it an int. And let's give it a double. 200.345. So that's my file. It's got a string, an int, and a double. Okay, so now we'll come down here. And what we'll do is we can read the string, and we could do this in separate lines. We could just do it all in one. I'm just going to do it all in one to save a little time. So I'm going to read the string, then I'm going to read the integer, and then I'm going to read the total. And what I'm going to do here is I'm going to display the line. I'll just display them in 3 lines. I'll copy that one. So here we're displaying the line. Here we're displaying the num. And then finally, we'll be displaying the total down here. Okay, so all we've done now is, rather than just read hello, we're reading hello, the integer, and the double. And when I run this, I should get 3 pieces of information displaying. There they are. Hello, 100, and 200.345. Pretty cool. And if we modify this file to look like this, this will still work, right? Because we're using that extraction operator, and it's going to stop right here when it sees a white space, and it's going to stop right here when it sees a white space. So we're pretty flexible as far as the format of this file. So if I run this again, you can see I still got those numbers right there. Okay, so that takes care of that example. And what I'll do next is we'll go to read file 2, and we'll do exactly the same thing, except we'll create more data here, and we'll read these inside a loop. Okay, so I'll be right back to do that. And actually, before we go to the next example, I forgot to close the file. So I wanted to be sure that you know that we need to close this file. So I'm just going to do infile.close. Okay, that's very, very important. I got carried away with showing you how to read. I forgot the simple things to close the file. So make sure you close the file at the end. Okay, so I've switched over to section 19, workspace read file _2 project. Okay, so what we want to do now is, rather than just read those 3 data items, we want to continuously read 3 data items. And let me show you what I did to the test file. Now we've got Frank, 100, and a double, Larry, an integer and a double, Mo, an integer and a double, and so forth. So what I want to do is, rather than just read the one line, I want to read as many lines as they're there. So we'll need to do this in some sort of loop, right? So we're going to use a while loop. And let me go back to my main, and I'll show you what's happening here. Everything else is exactly the same. I have included IO manip here just because I want to display those guys out at the end in a little bit of a formatted column. That way you can see it a little better. So I'm just displaying line, num, and total a little bit formatted. So here I've opened the file and I've checked that it's open. I'm assuming it's open right here. Otherwise I can't get here because the return 1 would kick me out. So what do I want to do? Well, I want to have some sort of while loop here. I want to loop while not in file dot end of file, EOF, and that's a function that will return true if it's end of file, or no, not true if it's not the end of file. And what I want to do in there is basically display this, but first I want to read the input, right? So again, I'm reading from in file, and first I'm reading the line. Actually, it should be name, right? But we'll just keep the name line, the num, which is the int, and the total. And that should do it. So again, while we're not at the end of the file, we're reading 3 items, displaying them, looping back up, reading another 3 items, displaying them, and so forth. And then when we're done, this time I remembered to close the file. Okay, so let's run this. And when it runs, that's the information you get. You get Frank, Larry, Mo, Curly, and you get the integers and the doubles here nicely formatted because I'm using the setW manipulator. So we can do that with end of file, but we can also do that by putting that this statement right here, right inside the while. So what we can do is we can refactor this a little bit. And what we'll do is we'll put this statement right in there. I'll just move it up here, just like that. All right. So now this is a little different. You have to wrap your head around this a little bit. So there's my in file, and I'm reading those 3 items. If I hit end of file, if anything fails, if I've got illegal data, anything, this will fail, and the while loop will fail, and I'm out of here. If I'm able to read all those 3 items, remember this is using formatted input because I'm using those extraction operators. So that's it. It'll read them, and then I'll display them. So if I run this, I should get exactly the same output as before. And there it is. Okay, cool. So now in the next video, this one's getting a little bit long, so I'll cut it off here. In the next video, what we'll do is we'll read one of Shakespeare's poems line by line and display it out to the console. Okay, in this video, what I want to do is read a poem from a text file and just display it out to the console. And we're going to use getLine to do that. So I'm in the section 19 workspace in the read file _3 project. And what I've done here is I've got a poem already, and I created a file called poem.txt, just like we did before. And this is Shakespeare's Sonnet 18 poem, and you can see it's 14 lines. And what I want to do is read each line and display it out to the console. Now, if we tried to do this with the extraction operator, reading one of these words at a time, it's much trickier because, when do we hit the end of line? We really don't want to deal with any of that. The simplest way to do it is just to read one line at a time and then display that line right out. So let me show you where the main is. This is about as simple as it gets. I've got IOStream, FStream included. You can see here I've created my in file, and I'm opening poem.txt in my parents directory, which is exactly where I want it to be in CodeLite. If the file is not able to be opened, I'm displaying an error again, and I'm out of here. And I'm closing the file at the end. So what I need to do here is simply process that file. So how do we do this? It's really just 2 lines of code. It's really, really straightforward. So what I'm going to do here is just say while. I'm going to use std_getLine. And there's 2 versions of getLine, by the way. There's a getLine that works with character pointers or C-style strings, and there's a version that works with C++ strings. We're using C++ strings from now on in the course, so that's what we're going to be using. So we're using std_getLine, give it the name of the input stream, which in this case is in file. And where do I want this read into? I want this read into line. We haven't defined line yet, so let's define line. And I'll do that right here. I'll say std string line. That's it. That's where the input's going into. So what do we do? Well, while we're getting a line and it's successful, this will be true. So what do we want to do with that line? We just want to display it right to the console. So can't get much easier than this. See out, line, and I need a new line. That's it. That's really that simple. So if I run this, there's the poem. Right? One line at a time till I hit the end of the line. I'm reading that in and I'm just displaying it right back out. Okay, pretty easy, right? Now you can see how easy it would be to write a file copy utility. We haven't learned about writing files yet, thinking you know where we're going, right? We can, just like we write to std_cout, we can write to a file. So we can easily write a utility that will copy a file. And we're actually going to do that. We're going to, when we get to the output files section, we'll read this file and maybe this one or Romeo and Juliet or something, a bigger one, and we'll write it out with line numbers and so forth. That way we can modify it a little bit. So that's it. This is using getLine, reading one line at a time. Now what I want to do next is I want to go into read file _4 project. And what we'll do is we'll do the same thing, but we'll use unformatted input. So we'll do it 1 character at a time. So I'll set that up and I'll be right back. Okay, so I'm back in the read file _4 project for the section 19 workspace. And what we're going to do here is we're going to read Sonnet 18 again. except we're going to use unformatted input. In this case, we're just going to use the get method. And what that'll do is it'll return one character at a time. And we'll just display that one character out. So the advantages of using unformatted input are you don't have to worry about new lines. You don't have to worry about end of files. You don't have to worry about fancy characters and different things that could maybe break the way that you're reading because it's formatted. And it's just going to process characters unformatted. It's pretty cool. It gives you a lot of flexibility. And that's what we'll do now. So this is where we're at again. We've got IOStream and FStream exactly like we were before. We've created our in-file object and opened the file, and we've tested to be sure we've got an open file. We're closing it down here. So right in here is where we're going to do our processing of the file. How do we do this? Well, pretty simple again. While in-file.get some character, C. Okay, we need to define C as a character, so we'll do that right here. We'll say char C. That's it. It's really pretty simple. So while this is true, what do I do? Stood C out the character. And then that's it. I mean, down here, I guess we could print a new line here just so we get a little bit of space at the end so we can see a little better. But that's it. So while we're reading a character and it's true, right? We haven't hit end of file. We haven't hit some bad bits. We haven't had any hardware issues. While all this is good, we've got that C. We're just going to display it. So if we run this, there's the poem exactly like it was before. That's it. Now you're ready for the challenge. And the challenge is going to be a fun one. There's a couple of challenges actually. So I'll see you in the next video and I'll explain the challenge to you.